speakers here on this guy so we don't get that, consecutive type of feedback loop. Okay, there we go. Good morning, everybody. Thank you for joining us today for the Interstellar Initiative Grants final public briefing. My name is Sonny White here at Limitless Space Institute. I'm the Director of Advanced Research and Development. We have a great day planned today, a lot of interesting things to talk about as part of this Interstellar Initiative Grants final briefing. Interstellar Initiative Grants is a program we initiated in the summer of last year to try and find an opportunity to connect with folks across the globe that are interested in trying to do research in advanced power and propulsion that might work towards enabling some amazing abilities and capabilities to be able to project humanity further out into the solar system and maybe on to the stars one day. And so this is something we want to try and do every 2 years. We did the first solicitation last summer. Ideally, we can do another solicitation this summer of 2022. The Interstellar Initiative Grants Program has two different categories of grants that we award. We have a tactical grant, which is potentially something that ties to theoretical type of a work. And then we have a strategic grant, which might actually have some empirical mixed in. There's actually a little bit of flexibility in that as well, depending. So, but we'll be putting out another solicitation in the summer of 2022. Maybe we can even grow the partners that we have as part of this inaugural class of Interstellar Initiative Grants. We worked in partnership with the Breakthrough Initiatives, and we thank them for all of their help in the process of learning how to do the communication and connections and so forth. And then Texas A&M has been very instrumental in the contract initiation and management side of things. So big thank you to our partners that have been involved in all of this stuff. And it's been neat to watch all the performers and their teams have lots of students involved in all of this stuff, and it's been really great to see that. And that traces very directly to our mission here at Limitless Space Institute. Our mission is to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technology. So Interstellar Initiative Grants is very much an integral piece of trying to map that mission into some type of form, if you will. So got a number of interesting talks today. Just to give everybody a quick preview of the cadence of events today. This first thing this morning, we're going to have a keynote from astronaut Victor Glover. I'll introduce him in just a second. After Victor gives us some awesome comments about his experiences in human spaceflight, we'll have talks from 5 of our performers. And those formats will consist of like a 30-minute discussion from them, giving us a synopsis of all the things they've managed to accomplish. And then we'll have 10 minutes of questions that we'll try and pose questions. And we'll be paying attention to questions that come in from the attendees, type those in the chat. And then, of course, all the panelists and so forth can talk freely. And then we'll also be monitoring the YouTube comment section as well for questions to see if we can catch that. We do have a mid-morning break at 9:50 Central Daylight Time, 20-minute break in between with the first 3 performers and then 2 afterwards. We will have a virtual lunch break, about 45 minutes from 12:10 to 12:55 Central Daylight Time. The afternoon session will have some awesome comments from Reid, Wiseman, followed by the 4 remaining performers as part of our inaugural class. And again, we'll have a 20-minute break around 2:50 Central Daylight Time. So with that, I'm going to go ahead and do a quick introduction of Victor Glover, our first keynote speaker this morning. Victor is actually busy with SpaceX this morning. He is unable to join us live, but we did, the astronaut schedules are completely crazy. And so he's definitely working on trying to get to the next type of spaceflight missions and working very integral with SpaceX. But we did get a chance to record some comments from him. Just a quick introduction about Victor and who he is. Amazing human being, American hero. He's a commander in the U.S. Navy. He served as a test pilot. He's flown some amazing aircraft, the FA-18 Hornet. He's flown the Super Hornet. the EA-18G Growler. He was selected as a U.S. astronaut in 2013. In the middle of 2021, he served as the pilot and second in command on the Crew One SpaceX Crew One mission for the Crew Dragon named Resilience. And he was able to serve on the International Space Station as a flight engineer for Expedition 64. If you read through his education list, there's a lot of bullets here. Oh my goodness. He's got a Bachelor's of Science in General Engineering, a Master's of Science in Flight Test Engineering, a Master's of Science in Systems Engineering. I'm going to keep going. A Master's of Military Operations. But I just want to say we love Victor to pieces. As part of something NASA did for the Star Trek 50th anniversary, Victor Glover was a narrator for a number of the videos that they pulled together to talk about how Star Trek inspired a lot of people to be interested in the space program. And as part of that thing, they always had Victor on the bridge of the IXS Enterprise. That's our little space warp concept vehicle we developed in 2013 timeframe. So it's always neat to see him. So in some ways, we view him as the captain of the IXS Enterprise. So with that, Fro is going to share the video that we were able to get from astronaut Victor Glover. So Fro, I'm going to hand it over to you. Don't forget to click the share sound button. So.
Greetings. Hello, everyone at the Limitless Space Institute. I'm NASA astronaut Victor Glover, and it is a pleasure to be able to address you for this event. Congratulations to all of the I² grant winners, and greetings to all the board of directors and board of advisors. It is a pleasure to be able to address you. I recently have the pleasure of coming home from the International Space Station on May 2nd of 2021. The Crew One in our SpaceX Crew Dragon that we named Resilience. We landed in the Gulf of Mexico after spending 167 days and a few hours in low Earth orbit, most of that working and living on the International Space Station. It was truly a privilege. We were able to conduct hundreds of science experiments supporting things that have been going on for decades, and the science and technology that enables humans to live and to thrive in low Earth orbit. And it was truly an amazing experience. We were able to conduct 5 spacewalks as a crew. I was able to go out the door on 4 of those, and it was an amazing experience. And we also had the unique privilege of flying a new spacecraft, SpaceX's Crew Dragon, to the International Space Station, as well as home back to Earth. And it performed amazing. It was such an amazing ride up and back. And to now be able to address you and the lofty goals that you have of inspiring and educating the next generation to travel beyond our solar system and to support research and development and technologies that enable interstellar human space exploration. Wow, what an idea. I mean, to live in space, it really was amazing to be able to look out and to see Earth. But you know, to be in low Earth orbit, you could never see the entire globe, the entire ball, like you could if you were in orbit around the moon, say. And so to think now about taking the next giant leap and going into interstellar space, I can't help but to think about the title. You know, we hear the term astronaut all the time, and astronaut actually means star sailor. And as a naval officer and naval aviator, I think sailing and what it means to be able to travel through our global commons, the oceans of Earth, and how meaningful that has been to be able to sail the oceans of space and to travel to another system that is centered around some other star. Alpha Centauri, that 3-star cluster, is 4 light years away, just over 4 light years away. And so to be able to finally realize that title of being a star sailor, I think you have to be able to at least travel between one star and another. And so that would really be amazing to have humans to be able to traverse those spaces. And so it's going to take revolutionary ideas. It's going to take ingenuity. It's going to take looking beyond the horizon of what we can see and do today, the state of the practice, and making something completely revolutionary that is the state of the art and becomes the eventual state of the practice. And so that's going to take all of us working together, doing the best that we can with the people that we have next to us, to our left and right and in front and behind, and making that group work the best that they can together to accomplish such a lofty goal. That's amazing. And I wish you the best as you go out and inspire, but also as you work together internally to take care of all the logistics, the financing, the budgeting, the paperwork. There's so many things that come together to make all of these things possible at every level. And so I encourage you to keep it up, and I look forward to reading amazing things about what you have done to inspire the next generation to look up and to believe in themselves, to work hard together, and to change human space exploration for the future. Thank you.
Thank you, Fro. Appreciate you playing that. It's awesome to hear from Victor. As you can tell, he's a very energetic human being, very excited about space. He's accomplished a lot of things. And sometimes, when you read a bio from somebody and hear about all the different things that they've accomplished, it's a little humbling when you're continuing down that list and there's more and more bullets on the list. So glad we were able to get that from Victor. That's really awesome. So I'm looking forward to hearing from Captain Reid Wiseman this afternoon for our afternoon keynote comments. So let's go ahead and get started on the first briefing from Jason Cassibry. Just a few minutes ahead of schedule here, but we can go ahead and get started. I think Jason, I have screen sharing enabled for anybody, but before you get going, I will try and give you the a 3-minute warning. So I'll do it. I'll just have to kind of step in and do 3 minutes. I may have to say it a couple times for you to hear. I would request everybody mute their PCs and maybe turn their videos off as well, and that ensures that only Jason's mug is showing on top of his slides. So I think with that, Jason, I can hand the microphone and baton over to you, sir.
All right, great. Good morning, everybody. Can you hear me okay?
Yes, we got you good. 5 by 5.
Great. Okay. All right, can everybody see the slides or slide?
Yes, we got the slides.
Okay, great. Well, good morning. And gosh, I hate to follow such an excellent opening speech like that. I hope it's not too much of a letdown from that. I'll try to keep it uplifting. But anyway, that was inspiring. Sorry, I'm very sleep deprived today. But anyway, this is our final briefing on the exploration of low energy break-even fusion. And I would like to acknowledge Dr. Gabe Shoes, Sumatra Sinha, Jacob Kinsey, Alan Davis, the Propulsion Research Center, and a whole slew of undergrad students which have supported this effort. And I'd also like to thank the Limitless Space Institute and the Interstellar Initiative Grant for giving us the funding for this. This has been outstanding. So the objectives of our program were to develop neutron scaling laws for solid state fusion targets for pulsar U-pinch fusion based on rising currents. Design targets to achieve tailorable ion densities near 10 to the 26 to 10 to the 28 at peak current, and achieve validated simulations in our 3D SPF Max tool. So we had multiple milestones in the program. I can't belabor it because we've only got 30 minutes. We've got a lot to go through. So here are some pictures of some of the folks that helped with this program. I forgot that on the first page to include Mr. Andrew Walston, who assisted in plasma diagnostics, and he is a student of Dr. Gabe Shoes. So I want to do a couple of slides on just kind of why we're doing this. So when you look at, say, energy densities of various fuels versus delta V, if you go up this chart, you can kind of see delta V gets much higher and the mission gets much harder. And these are all sort of the interplanetary solar system type missions that get harder as you go out to the Oort cloud or gravitational lensing. And then there's this huge gap where there might be lots of interesting comets or things we just don't know out in deep space before you get to the next star of Proxima Centauri. But you can see the energy density of fuel, if we use the rocket equation, really starts to exclude things like chemical. Once you kind of get beyond Mars round trip missions with refueling, it gets harder and harder, especially if you start to think about doing things quickly. So the rocket equation just kind of pushes you out to nuclear, antimatter, and laser light craft to be able to do things like that, or warp drive if we ever get there. This animation over here just kind of is a an animation to take you through the solar system, just to kind of give you an appreciation of how big things really are. And the conclusion here is we really need to push the boundary. And what an exciting time to be a part of this, as you see all the funding that's going into nuclear technologies and advanced technologies. So I think that the next 10, 20, 30 years are going to be revolutionary in terms of what the new capabilities are. Another slide I like to throw out a lot. So we all kind of preach to the same choir all the time. And so we're all, yeah, deep space exploration, advanced propulsion, we're all excited about that. But not everybody shares our passion. So there are some good quantitative reasons why we should send humans out. So we're basically 20 petaflop supercomputers that require about 100 watts of power to run. And I think it's gonna be a long time before we have androids that can really compete with that. So there's just all kinds of things like higher speed and faster speed and efficiency to optimize our field work, agility and dexterity. The on-site team overcomes the communication problems. There's no communication lag if you're right there on the ground working and reacting together. There's a 6 to 20 minute one for Mars, depending on where we are in orbits. The small number of daily uplink and downlink communication passes. So this is specific to Mars, but again, there are a lot of good reasons why we want to keep working hard to try to make humans dwell in space and go farther. We've got a lot of missions to consider. So most of our missions are satellites going in low Earth orbit or geostationary orbit. We've done quite a bit with cislunar space, and of course, let me kind of hide this over here so you can see the right-hand side of the screen. And so 90% of our missions, actually I think more like 99, have done everything out to about Saturn. Just very, very few have gone beyond that, as we kind of aspire to go to the deeper parts of our solar system and go interstellar. We have just barely scratched the surface. There are so many things, though, that we can do within our solar system that I hope that we take the time to explore, because there are all these little spherical rocks out in just our solar system alone. This is a chart that kind of organizes the terrestrial world sorted by gravity, starting with Earth and going down. And gosh, if we could learn how to live off the resources, there are many, many places that we could go visit and learn from. As we look out to the interstellar space, of course, we've got Earth, which I hear is a pretty decent place to live. It's got a good temperature on average. It's exciting to know that Proxima Centauri, our nearest star, actually has a potentially habitable planet. It's a little cooler than ours, we think. The next nearest one that we're aware of is Wolf 1061c. That's at 13.8 light years. Gliese 667c at 23.6. And GJ 357d at 30.8. And I think the planet Vulcan is actually within about 40 light years. So it's pretty close by too. So I hope that one of our warp drive scientists can get all of that working so we can have first contact in our lifetime. That'd be great. So anyway, let's now talk about Sparky. All of these experimental ones were put together by Sumantro Sinha. He has worked tirelessly to try to get this machine operational and get our diagnostics working. We're very proud of the work that he's done. And he's also done an excellent job in shepherding all of the undergrad students that have come to join us. So Sparky is a 60 kilojoule pulsar with a maximum voltage of 40 kV. When it goes off, it sounds like a cannon. If you fire it in open air, it's really fun. The motivation for this work in the direction that we're currently heading. So we have a few irons in the fire in fusion, but one of them that I think is really exciting is when you do a power balance. So these charts may not mean much, so let me kind of orient you real quick. This boundary represents a boundary between it cools off and quenches and it heats up and burns. So on the left-hand side, we've got power where this should be negative. So this is not marked right actually, but this should be negative over here. And the power increases. So as you compress the fuel, it can kind of heat up. Now this is within a 20 kilometer per second implosion velocity on top of a target, which is sustaining 10 megaamps of current. So it's a lot of current flowing through here. The current will only get you up to a few hundred EV and where radiation takes over. And then you have to have compression power like a piston in a car, compressing the gas. to heat it up. And then finally, once you get up to fusion relevant temperatures, it can burn. And this is just with deuterium. This doesn't require deuterium tritium. And over here, this shows you the same contour. So, you know, down here, it gets cold and quenches, but up here, it keeps heating up. And these colors on this right-hand side show you the total thermal energy required in the system. And as you go to lower densities, the yield goes down, of course, but the required energy to do this experiment actually goes down. So we're looking at, and there are other complexities as well. This is just basically telling us where to aim the experiments, what to try to achieve, and where to aim to try to do this at low energy. So if you can get really, really high magnetic fields, I'm talking like a couple of hundred Tesla, essentially what you're doing is you're shutting off cross-field thermal conduction, and it's only radiation against the other heating power components in the reactor. You might be able to do this at sub-megajoule capability. And if you don't know how capacitors scale, sub-megajoule is great because, my goodness, capacitors do not store energy very well. They are very bulky and heavy. And a megajoule is a very reasonable amount of capacitor energy storage, very manageable. So here's a schematic of our layout. This is Sparky right here, control relays, power supply. We have a radiation shield that surrounds the experiment. And it's a lot more complicated than we realized. The more we peel back that onion, the more layers there are. And underneath the onions, it's turtles all the way down beyond that. It's a very complicated problem. But anyway, so this is basically the schematic and layout. And this is just some of the highlights of things along the way. So we use Hoffman boxes for some of our diagnostics to shield them. This is our fast framing camera, which we purchased off of this contract. This is a side view of our neutron shield. So it's basically water and borax filled to the brim. And the borax does the following. The hydrogen in the borax scatters and moderates the neutrons. The borax itself absorbs the neutrons. And then we actually learned that we have to surround it with lead curtains, which we have, because when the neutrons absorb, they kick off gamma rays. So that reaction of absorbing the neutron kicks off gamma rays. So it's a secondary type of radiation. So you have to shield for that as well. So it's quite complicated to manage neutrons, but we think we're getting the hang of it now. We for the first time on this contract captured waveform data so that we can measure the current and the voltage, and we're getting of the order of between 50 and 100 kiloamps depending on the conditions in the experiment. In order to see them, we had to add low pass filtering. We had a previous pulse power machine which was a lot simpler and smaller, and we just assumed it would be the same thing when we scaled up to the bigger machine, and my goodness, it was not. This is an incredibly noisy environment, and those transmission lines ring like crazy at high frequencies. And so we had to learn how to build filters in order to be able to actually see and tease out the thing like I just showed you, the nice waveform. This is our wall. You know, some people like to put, I guess, deer antlers or things on their wall. So we put up killed transmission lines as our decoration. These were different iterations that they tried. And we like to do things inexpensively because our attitude is we really want to try to do something that is as cost effective as it can be in trying to achieve break even. So these strips here were actually straps that were used to hold capacitors together on a pallet. And we thought, hey, transmission line. And they actually turned out to be really useful for basically prototyping and seeing what would work best. And ultimately, we used plywood to hold down basically aluminum or steel flashing, which comes off, which is used for rooftops for, I guess, water and flow control. And those seem to work really, really well. So improving the transmission lines turned out to be really important. Here's an example. And this was, I think, a product of work between Dixie Flesher and Sumatro Sinha. So Dixie's one of our best and brightest undergrads who has just done all kinds of things. But anyway, this is basically what we landed on to help smooth the output from Sparky down into our loads, which go into our radiation shielded enclosure over here. We eventually replaced these rail gap switch with something much simpler. And for now, we're actually doing it in open air. This was a bottleneck for us because while these are really nice switches that can handle lots and lots of current, they require lots of refurbishment. And so we came up with something much simpler. This was one of the iterations along the way. This is a chrome plated towel rack bar, which actually worked really well. Chrome plating, when it oxidizes, the oxide is actually still conductive, and so they last a lot longer than the rails did. And there's a blue light special at Walmart, so you can get these high current switch parts for pretty cheap there. We replaced BDOT probes with new Rogowski coils in order to measure the current. This is not really showing us much in that picture. There's another picture I'm trying to get to that shows how we wind them up using part of a drill. That was another student, Brandon, that came up with that build. So photomultiplier data. So one of the things that I'm sorry we were not able to do on this contract for a couple of reasons is quite get to the level of producing neutrons. Part of it is because of the complexity of photomultiplier tubes and the noisy environment that we're learning how to shield against. And the other is because of the radiation paperwork, which is actually turned out to be significant. And we're still plowing ahead. We're going to get there, but it just turns out that all these things are just really hard to do and they take a lot of time. This is a little bit out of place, but this is the Rogowski winding method. When we had a drill go bad, the students came up with this idea of using this as sort of like a lathe. They have another drill over here, and then they put the cable in between. And this is just free spinning, and the chuck allows it to hold it in place so they can make these really nicely, consistently wound Rogowski belts over there. Let's see, this is a repeat. I'm sorry, I didn't mean to do that. I accidentally repeated that. So this is just the slide I put together for while we wait for state approval for our radiation. And it's just because for the entire state, they have two people that do all of this for the entire state. So it's just a while. And I think that the pandemic has kind of slowed things down. So it just, you ask politely and hope for the best for eventually getting final approval to do things. Jacob Kinsey is our grad student that was on this. And one of the open problems we had was reliable triggering of Sparky. And the first thing that we did was literally use mechanical relays to turn the thing on, which is not good if you want to sequence it with other things like we want to do ultimately. So we had him work on something that was not in critical path, but important long-term, and he delivered. So Jacob built what we call a spiral generator. Now, essentially the way this acts like a capacitor, it charges up. The capacitance is easy to calculate, but you switch it in a clever way. So when it discharges, there's this wave that travels down the spiral and it multiplies the voltage. And so you go from something where you can charge, say, a kilovolt, and it outputs a triangular wave at about 50 kilovolts output over like maybe 100 nanoseconds, depending on the geometry. And so he put all these slides together and just kind of talked about some of the difficulties that you go through in making them. And so with many, many attempts, and he worked with our former Apollo technician who worked under Werner von Braun, Alan Davis, in order to get all of this sorted out and fixed. And so now he can do solid state control of these spiral generators so that we have solid state control of Sparky indirectly. So he did an excellent job. And this was one of his final configurations that he settled on how he actually winds the spirals in a reliable way. And here's some of the output where he got voltage multiplication. And he just did an outstanding job on that. So I want to talk about some of the modeling that we've done to support this. This work actually is an outgrowth from Brian Winterling, who was not directly on this contract, but has worked on his dissertation in this area in just pulsed solid state nozzles. So one of the modeling that we've done is just to try to do an equivalence between a steady state nozzle and a pulse system in order to see how it converts thrust. Now, one of the assumptions that we've learned is that divergence of this plasma actually compromises the efficiency quite a bit. This model does capture some things actually quite well, but it over predicts performance by about a factor of 2 or 3 depending. And so we can kind of quantify that later, but just to say that we do have a way of kind of estimating, given initial conditions and nozzle geometry, about what the thrust in ISP should be for things that are pulsed like this. And once we understand the departures from efficiencies, which is a thing that he's working on, Brian, I mean, we'll have a better understanding of this. But this is just kind of a comparison between an analytical model for steady state for us, which is well understood, and then the pulse system equivalent of that. So in 3D modeling, we worked really, really hard in order to try to get this, excuse me. And so this over here looks like a mushroom. What's actually going on is this is a comparison, and I didn't have time to put all this together, and I'm sorry. This is Nathan Schilling's work over here. He's another grad student of ours. There's a ring, a single turn coil back here in which the plasma, as it expands out, forms this plume shape. And this is exactly what they observed in particle and cell simulations from colleagues of ours in Japan that started doing this work. So this is our kind of like code to code verification of SPF max on magnetic field nozzle modeling. And it's doing a much better job now. It seems like there are, originally we thought longitudinal or axial winding was the only way to make this work, but it seems like there are other routes too. And now that the code is doing much better and interacting with external stationary field coils, we're starting to get good results here. This is an example of a Z-pinch implosion, and we're going to talk a little bit more about that. We had a lot of trouble in getting the interaction with the plasma with an external circuit working. Here's the simulation where we finally started to get it, and actually works much better than this animation. I just haven't had time to update the animation. But this is an example of a railgun where you have an RLC circuit driving the plasma and it shoots out the exit. So that's actually now working. And here is an animation. I guess I did have time to update it. I just forgot that I did, sorry. So here's some other test cases where we have like a plasma exploding against a stationary solenoidal field, and we would expect it to bounce, and it does do that. And then here's a comparison with a particle and cell result, and then our shape right here. And so we're working on the more quantitative comparisons. This is a plasma flowing around a stationary magnetic field. These were experiments done by Gage Shu, and they can get different results depending on experimental conditions, but we can actually reproduce where it gets deflected. And we forgot to set a wall here, so the plasma magically goes through that stationary magnet, which obviously it doesn't do in real life, but that's an easy thing to fix. The one that is most encouraging is the validation against MagLife published data. So that just happened actually this week, where we were able to get really good agreement with a MagLife experiment. So not all the elements of it, but the implosion rate and the convergence ratio is very, very close to what they observe. And here's, say, an initial condition where we've got electrodes in the plasma, it implodes. You can see how much constricted this plasma is as it gets down there. These different curves are different ways in which we measure that convergence, and it's kind of bounded by what they estimate from the experiments. And so we're trying to figure out what's the best way to estimate that convergence, because it's not a clean, obvious calculation to make, but the three ways that we came up are right within the right range. So we're very excited about that. This is the punchline to this program, and this is where we're headed. And one of the routes that we think is promising for fusion. So we have a plasma liner that we're going to implode onto a target in which we're driving a Z-pinch. This is kind of like a two-stage Z-pinch, and other people have pitched this. And what we're trying to do is specifically access this low energy parameter space right here. And so the simulation, which I was hoping to deliver and get working this week, we have a lot of interesting, challenging problems that we're facing. And it's like this every time we do a new simulation. Like the requirement is we make a simulation work without breaking the old ones that do work. And so that's what we're working on right now is uncovering all the little quirks and problems that come up and fix them as we go, until we can get to a point where we can then tweak parameters and find whether or not this thing will ignite and under what conditions it will. So we're working on that right now. But we've got this really great tool to help tell us where to aim our next experiment. So we're very excited about that. Where are we headed? We are like gypsy fusion engineers, because we keep having to move. We should just put up a tent and just go in a parking lot somewhere. So we moved from the arsenal to a lab on campus because it was the only thing available. And this building is going to get demolished soon. So we have to move again. And our more permanent home, we believe, is going to be some commercial real estate. And this is kind of our layout that we put together. Sparky's here, some other high voltage experiments we're doing, and plus some other things that we're doing. I'll be hiding over here at this little workstation. We're very excited about it. We're looking forward doing it. And if you want to know what we'll be doing in December, it's probably packing and unpacking lots of boxes. So anyway, I'm sorry if I ran a little bit long. We've had a lot of successes, a lot of setbacks, but we are very excited in the direction we're headed. We're very excited about all the other great things going on with ICE Squared and our colleagues, and as well as within Fusion in general. So thank you very much.
Thank you, Jason. Bringing my camera back online. Awesome, great job. No, you didn't get the 3-minute warning, so I was waiting to jump on you. So I see that Kelvin has a question for you.
Yeah, just
Kelvin,
a quick one. Great talk, Jason.
Yeah.
In terms of developing the neutron scaling laws, have you had conversations with Sandia?
No, we have not. Well, we've talked to Sandia before, but this is kind of a new thing that we're doing. And I think once we get to the point where we can duplicate their neutron yield, I think it's definitely going to be worth reaching out to them and say, hey, look what we did. Is this, something of value to you? So, or if we have questions about clarification of results.
Yeah, okay.
Jason, as you know, sometimes I try and write down the funny quotes that people say during their talks. And I think the one that got me was Gypsy Fusion Engineers. I thought that was quite funny. And your little floor plan, you could have put like danger and then interns and then over here, right?
we try to use undergrads as a shield for everything. So would you like me to answer that question from Roman Kizarash?
So there's two questions in there. The first one is from Rob Swinney. Oh, sorry, no, I thought that was also Rob. Yeah, so Roman Kizarash put in, so Roman's up at the City University of New York. Yes, what's the main advantage Z-pinch fusion in comparison with a direct fusion drive? And then
that's a great question, and I'm not sure that there is a huge advantage. There are a lot of really good concepts out there. You're going to hear from several of them today. So let me just tell you why we're doing Z-pinch. The reason is because so this code that I talk about, maybe I'm too proud of it, but it's taken us about 10 years in order to develop it. And the hardest part was not the burn physics. It was the electromagnetic field part of it. Holy cow, has that taken a long time to get working right. But anyway, in the process of making different cases work and making our experiments work, the more information that you have about what's going on, the more it reveals about giving insights into fixing those problems. And the reason that we like Z-pinch is not because it might be the best. I mean, in terms of like helicopter development, this might be that 1920s era thing where the umbrella was flapping up and down trying to make the car come off the ground. So Z-pinch, I think, can be made to work, and I'm not knocking it, obviously, but it's so simple, and it's such an easy way, direct way of knowing and controlling what's the field in that plasma. If we drive current through it and we have the right probes around, it's very direct measurement. And so knowing that gives us a lot of information about how to make improvements on it and how to fix it. And so I guess an advantage for us is that we have a lot of understanding about it. But once we make this kind of thing work, Z-pinch has a problem because here's the electrode and here's thermonuclear plasma right next to it. So we're going to have all kinds of problems like spallation, neutron damage. And so from that standpoint, I think that the things like direct fusion drive are going to be advantageous. And so what you want is a really healthy portfolio of lots of different concepts, because they're all probably going to have challenges and problems, but collectively we all learn from each other to figure out ultimately how to make good reactors.
Jason, just to follow up from that, I think I worked with the guys at Magpie at Imperial College for a little while. They've got a Z-pinch in the basement there. And it seems to be one of the advantages, going back to Roman's question, is you can really try and understand the hydrodynamics of how to implode a capsule. You can load non-thermonuclear capsules and really try and understand that, which helps you to prepare for what you're going to do in the future. So
yeah, absolutely.
So does anyone else have a question? I don't want to get in the way of somebody else asking a question before you ask mine. And for anyone that's online, feel free to type in your questions either in the chat or the Q&A, and we'll try and monitor those. I have a couple questions, Jason. One is, so you showed a bunch of capacitors and supercapacitors. What is that? Would that change anything that you're doing, or?
No, but you bring up a good point. The reason why I say no at the moment is because most supercapacitors, and we actually have some in the lab for fun. If I'm being honest, it's like,
why not? Right?
A 5 farad capacitor, isn't that cool? Most of them are only at, say, just 1 to a few volts, and so they discharge over seconds, minutes in some cases. But the best energy density capacitors that I'm aware of, and my goodness, if someone could say, no, you're an idiot, it's these, great, tell me, is electrolytics. So electrolytics are those cheap barrel-shaped capacitors that are on circuit boards. And they peak at about 2 kilojoules per kilogram at about 400, 450 volts. And so one of the things that we're interested in doing to shrink down the mass of the whole system is look at systems that are driven by electrolytics at 400 to 450 volts that then step up basically they compress the pulse and the voltage so that you drive a system with the compression side of it, but leverage the energy density of the electrolytics, because the high voltage capacitors that we use are very, very heavy. And so if we could shrink that mass down by an order of magnitude or more, it would really help in terms of just the economy of the scale, size, and all that kind of thing.
On you had said on fuel, you're using deuterium as your target reaction, and this question is just not lack of my familiarity, but tritium requires licensing, doesn't it?
It does. If you had tritium available and the infrastructure to handle all of that, then DT would be the way to go if you could manage the 14 MeV neutrons that come out. But it just seems like for us, like deuterium and lithium deuteride are practical choices because the cross sections are not great, but they're better than a lot of the other things like P-boron 11. So that's kind of where we're sticking with, just because the relative inexpensive fuel and abundance of it.
What about the tritium that you might produce?
Certainly
lithium 6 and alpha T reactions.
Oh yeah. So if you use lithium deuteride, you can breed tritium during the reaction because the neutrons will interact with the tritium. Although I don't know if it's that much of an advantage. The secondary reactions that come from the tritium may not be enough to really make much of a difference.
But do you need a license for that? Do you need a license if you're producing tritium?
I haven't looked into it, so I don't know. It's a good question.
Yeah, I don't know either.
Yeah.
Go ahead, Piero. You got to take yourself off mute.
If I don't understand this question, I'll just mute myself.
No, just a curiosity from a non-expert viewpoint. So that you have a fusion system, so I expect there should be instabilities. What's the stability of the system? What is the time scale for your propulsion device? Because, so in the nuclear, so in a tokamak, I expect, as far as I remember, it's about 1,000 seconds, the stability of the plasma. So what do you have there? So for your device?
Yeah, no, that's an excellent question. And fusion instabilities are sort of the thing that humiliates all of enthusiastic fusion engineers, because they're ubiquitous. So the trick that we're playing, if you look at data historically in Z pinches, they go unstable when the current levels off flat. If the current is rising, it stays stable. And I think what's going on is that as you're driving it and the magnetic field pressure is going up, it takes a while for the plasma to come into mechanical equilibrium with the pressure rising to kind of balance that. So if you're always leading the pressure, you're fine. And so what you can do is you have to find the right combination of rise time, time scale, density, and size in order to basically make it all work. And there seems to be a narrow range for that'll work. at least on paper, that seems to be the case. In the cases that we've tried, we're running into that problem at the moment. So
yeah, there's a problem with the Caltech magnetic field lines.
Mhm.
That's my, yeah, sure.
Yep.
Yeah.
Mhm.
Anyway, very interesting talk. Yeah, thank you.
A great question, Pierre. Thank you. So Jason, just a real, I guess, a closing question for me. You know, based on where you're at now, I mean, what would be like the next major chapter for you, right? The I-squared grants things is kind of carry you down this road, and you were here when we started, and now you're here. What would be like your next chapter? Now, obviously, I know you'd like to be in a place that you don't have to go, you know, cut stuff off the walls to make parts, right?
Well, so our plan is to basically finish up these simulations to try to have a credible path to low energy break even, and then look for the money to basically build, if not the full scale experiment, a subscale that allows us to test that. And I think it's going to require a collaborative thing, because like, say, for example, to produce that imploding liner, there are some companies that are really good at making rail guns in the right parameter regime, like Hyperjet Fusion, for example. Those are some colleagues of mine in Chantilly, Virginia. So it's probably going to take us about 6 months, because as soon as this is over, I've got the APS meeting to worry about with a different group that I'm with, and some other things. So we'll have to unfortunately set this aside while we do some of the other things. And I'm on sabbatical, and in January I start teaching again.
January, you start teaching again.
No, I'm kidding.
The horror. All the other professors here are lamenting with you, right? Silently. They got the stony face, right?
No, I'm kidding. I love teaching. I love students, so it's all good. But yeah, once we have that credible plan together, and we also have the ability to generate neutrons and everything is blessed by the state, then we will be positioned to go after additional funding for that particular concept. So that's the plan.
Okay, cool. Jason, that was awesome. Thank you for your talk. Any final questions from the panelists? Okay, awesome. Well, we're going to go ahead and press ahead just a little bit ahead of schedule here. So next up, we're going to shift gears, and Professor Richard Norte from Delft University of Technology is going to be talking to us. He's doing some amazing work trying to figure out how to create incredibly complicated nanostructures on solar cell components that you couldn't even see if you were holding it in your hand and looking at it. I just want to add a quick preamble. Richard has his wife is great with child, and he may get the beeper thing and have to go in the middle between slide 5 and slide 6. So thank you, Richard, for squeezing us into such a amazing time for you. Congratulations to you and your family. But you've done amazing work. Looking forward to hear from you now. And so I'm going to go on mute and turn off my camera, so you got the stage.
Perfect. Thank you very much, Sunny. Let me just get this. Can you see my slides?
Yes, I can see your slides.
Perfect. Okay, great. Yeah, thank you very much for this invitation again to give this final briefing. For me, this has just been a really amazing program to be a part of, and to really just get to see what everyone else is working on, and kind of just build this little community that we're building here with a lot of people with similar interests. So for me, it's really been really great. I guess what I'm going to be doing today is giving an update on what we've been working on in terms of light sail technologies for microchip space exploration. It's going to be a little bit of some different topics here, but I think maybe I always like to show this infomatic from the from National Geographic, and it's a really nice little collection of all the exploration we've been doing over the last 63 years. And it kind of shows you more or less, and like you've already been hearing, it's, you know, a lot of the exploration we've been doing is quite nearby. And if you go out to the outer planets, you see that number of missions really starts to dwindle down. quite a bit. We have a few of these slingshot missions out on the outside planets. And if you look out at really the furthest man-made object that we've launched so far, we're looking at something like Voyager 1, which has been going out since the 70s. But it really, if you look at this log scale graph here, you can see that we're really quite far from this interstellar travel, and it would really even be nice to be able to get to this edge of the solar system in maybe not 47 years, but maybe a year, and that would be, I think, really interesting for quite a lot of people. And if you look at how long it would take Voyager to get to our nearest star, we're thinking something on the order of 10,000 years. And so I actually got quite inspired by seeing this announcement of the Breakthrough Starshot initiative in 2016. And the idea was really quite simple and quite compelling, which is the idea that, we can essentially try to make a microchip with camera, sensors, communication systems, and then essentially miniaturize it down to something on the order of less than a gram, and then attach it to large sails that are meters large and also that are also on the order of a gram, and that if we could essentially generate 100 gigawatts of laser power, we could start to shorten times from 10,000 years to 20 years. And so I found this really interesting from a community that was really making very thin mirrors for quantum experiments. So for me, this was just a really interesting challenge. And I think one of the things that fascinated me was really looking at, for instance, if you look at this chip, for instance, this is here the kind of chips that are being conceptualized here as being the probe. The idea is to miniaturize this chip and then attach it to some sails. And how you attach it to these sails is I think going to be in and of itself a big challenge. But the idea here being that the sails would be these things that are 4 meters by 4 meters large and have to be something on the order of a gram. And it's always nice to remind people that, if you look at a penny is already 2.5 grams. So something that is 4 by 4 meters and a gram is really something incredible. And the reason I found it so interesting is because, if you look at miniaturizing a probe in X, Y, and Z, that's really something we've been doing for quite a long time, is miniaturizing components in all the dimensions. But the light sail is really this very unique challenge, right? Because you have something now, it's the only nanoscale component that needs to be expanded to meter scales. And that's what makes it really one of the top challenges for the breakthrough initiatives, for the Starshot Breakthrough Initiative. And I found this really to be a very interesting problem, because if we look at kind of conventional miniaturization over the last half century, we've been really doing some amazing work in terms of miniaturizing things. And I think that, trying to miniaturize this kind of probes is definitely in line with this kind of miniaturization we've been doing. But I think this kind of extreme aspect ratio, what I call extreme aspect ratio miniaturization, where you have something that is small in Z, but maybe really long in X or in Y, I think is really going to open up a lot of new avenues in technology. And that's really, whether you look at the mechanics or the photonics, I think whether you look at space exploration or even sensors or these kind of things, it's really going to open up a quite new, a lot of new fields in the next century. But one thing that isn't, and at least caught my attention when I started this, was the fact that actually optomechanics, which is the field that I've been working in, has really already started to look at these type of structures, but for very different reasons, but with a lot of the same stringent requirements. So optomechanics, from just a kind of a starter's standpoint, it's just essentially a cavity where you have 2 mirrors and you make a resonator with it by aligning them well. One of the mirrors is movable, and you have this strong interaction between light and matter, and light and motion. And so what a lot of people do in quantum technology, so one of the main goals is to really try to observe the quantum nature of this mirror. So the idea being that you can use the light to actually dampen the motion of these mirrors until they really have one phonon, two phonons, one phonon, maybe even less than one phonon. And it's really interesting to describe this mirror, which is made of billions of atoms, describing it in terms of one phonon. So you have this kind of quantum state that you can get, but it's connected to this noisy environment. And if you don't shield from that noisy environment, then essentially you'll decohere this state. So this is essentially what you would get, kind of a noisy environment, and that noisy environment would essentially introduce heating or phonons or thermal mechanical noise into your system. And so one of the things that optomechanics has done to the field of optomechanics has really done to try to overcome this is by essentially saying, well, why don't we make these mirrors out of super thin membranes, which have almost no clamping to the outside environment mechanically. And we should be able to also make them as thin as possible and as reflective as possible, which is difficult in and of its own. And here what we're talking about is making mirrors that are about 10% of the wavelength of the light that it's reflecting, which is really kind of a weird concept. But essentially, if you look at the requirements for this, it has a lot of the same requirements as light sails. We want high aspect ratios. We want these things to be thin and long so that they have really no mechanical connections to the outside environments. That's also why we want this sub-wavelength thickness. We want the high reflectivity so that we can have high coupling. For light sails, you want it so that you can get that radiation pressure. And optical absorption is actually incredibly important for us, because if we get even one bit of optical absorption, that essentially turns into a phonon, which essentially ruins our quantum states. So we're really very sensitive to optical absorption, even at the single phonon level. So that's I think what really drove me to this problem, because I was looking at this and thinking, wow, we have a lot of the same wants, but for very different reasons. So what can we do? And so how do we make these mirrors, these membranes? So essentially we grab a very thin ceramic mirror and we punch holes into it at a nanoscale. And by the way that we punch these holes and we design them in terms of their pitch and their size, we can design them to be ultra reflective at a very certain wavelength. So here, for instance, is the reflectivity of a bare membrane, and here is what you can do with it in terms of when you add a photonic crystal. And what you do is you see the light coming in, and it forms kind of a guided mode inside of this photonic crystal, which constructively interferes with the reflected signal and destructively interferes with everything on the other side. So you essentially make an ultra reflective mirror from something that is, sub wavelength thickness. And then the nice thing here for sails, when you want them to be low mass, is that taking away, it's kind of counterintuitive that you would punch holes into something and make it more reflective. So that's actually a really good thing in terms of the mass reduction. So, and just to give you a sense of why this is different than a solar sail. So here's kind of what a cross section of a solar sail would look like. So Icarus, for instance, was just launched a few years ago, and this is an amazing structure. I mean, this is something that is 7 microns thick and really on the meter scale, something on the order of 14 meters by 14 meters. But when you see the thickness of a photonic crystal, which is what you need for these light sails to get them to a gram, you really start to see the challenge, because it's not just that you need these high aspect ratios, but you also need this high aspect ratios, and you need to completely cover it with holes, which makes it very different than really any material that we've made so far in terms of the macro scale properties and the nanoscale properties. So here's a SEM of one of our photonic crystals that you can see really up close. And if we zoom out of that, you can see a little zoom in here of what you see here in blue is the suspended areas, the suspended membrane with holes. The purple here is the frame. And this is what a photonic crystal looks like up close. And here's kind of for scale, the average human hair width. So it's really quite small. If we zoom out, you can see that we can really start to, make these photonic crystals quite big. And these are essentially some of the largest ones that have been made to date. And so right now, what I've been working on in my lab is really trying to extend this out to much, much larger scales. So this is what it looks like. I have some arrows here for scaling, but now what we're doing is really making these sails on the centimeter scale. So this is about 16,000 times larger than what people are really doing anywhere else right now. And that's something that we've been finding is that you can actually do things at this scale that you could not do at this kind of smaller fractions of a millimeter sizes. So for instance, if I made a photonic crystal that is 50 nanometers and this size, the best reflectivity I can get out of it is maybe 60%. But when you start making them at this scale, because you now have the light interacting with so many more billions of holes, you can make a 50 nanometer thick film that is 90% reflective. So that's really a much better performance at these larger scales than you could ever do at the smaller scales. So this really does start to open up new possibilities that you just don't have at this kind of, smaller nanoscale. And so one of the materials that we work with specifically is a high tensile material called silicon nitride. And we work with this specifically because it keeps the sails incredibly flat, kind of like a taut drum. And with that, we can get reflectivities on the order of 99.6% from a film that's only 200 nanometers thick. And the absorption here is really basically as low as you can get for any material. And the reflectance band is narrow, but still quite good, and could still actually cover a lot of the Doppler shifting you'll get when these sails are accelerated to fast speeds. So it might probably drop down from 90 something to something on the order of 70% reflectivity once you start getting that Doppler shift in there. But that's still actually quite effective in terms of pushing these sails. And so in this project, just to give a sense, is that we can do these large sails, but the problem is that we're really writing all of these holes is really billions of holes. So now it took us almost about 3 days to write this entire photonic crystal here. And this whole thing probably cost something on the order of 30,000 euros for us. And so what we wanted to do was say, why don't we look at the smaller scale photonic crystals, because we think that there's a lot of advantages to now just looking at smaller scale things and looking at the dynamics of these sails when you interact them with lasers. So with the smaller scale, we can make many per chip. We can actually see the amount of the way that laser power interacts with these sails. And we can actually have an ability to look at completely all of the mechanics and the dynamics of these sails. So it's really very hard to do it on this bigger scale, because then you have to really stitch everything together and look at the dynamics this way. So one of the first things that I think has been one of the biggest issues is you have this gigawatt laser and you want to shine it on these very thin membranes, which have essentially very little ways of thermally cooling themselves or thermalizing in space. So this is actually a really nice collection of materials that's been put together by Harry Atwater's group at Caltech, where they essentially put together all the different materials that could be used for sails. And you can see kind of here that there's this relation between lower index and lower absorption, and then higher index. And so essentially with a higher index, you can get a higher reflectivity, but you also get more absorption. And I kind of added in here silicon nitride, which is the material we use, because even with the lower index, we can still get reflectivities of larger than 90%, but the absorption is really an order of magnitude lower than really any other material that's been kind of seen as feasible for these sails. So for us, this is really a big motivation. But then one question is, okay, if I make a sail out of this stuff, right, the silicon nitride, can it actually survive? And this is actually something that inadvertently I actually looked at in my PhD. So in my PhD, we were essentially using high-powered optical lasers to trap these optically trap these silicon nitride membranes. And what we found is that we basically just turned up the power until we saw these things thermally fracture. And the idea being here that we could actually put about double the power density that's now kind of required by the Breakthrough Starshot Foundation. So what they're thinking is something about half of the power density that we're using here. So it gives you a sense that this material is really quite suited for these high-powered applications. But one of the questions is, once I put a photonic crystal on it, can it still survive that power density? Because when you illuminate these sails with this light and you now have it interact with this photonic crystal, you have this very intense buildup of a guided mode inside of your photonic crystal, which essentially couples the light much more strongly with your membrane than it does here, where it just really passes through. So that was one of the questions that we started asking here in our project, because now, for instance, now let's say that I did cover this photonic crystal, this membrane with holes, and I put the same beam on it. The problem is that now if I look at the beam sizes I was using in this, the reason I was able to get these power densities was because I had made the beam much smaller. But here, if you start to have the same optical beam on a trampoline with photonic crystals, you see that it really only interrogates maybe a few hundred holes, which isn't really enough to get that high reflectivity that you need. So it's really actually not so trivial to just grab a high-powered laser and then put it onto couple it to one of these photonic crystals, because for the photonic crystal to work, you need a bigger beam so that you can really get this high reflectivity. But then if you make the beam bigger, then it makes your power density smaller. And the other thing is that with high-powered lasers, they actually have the higher the powers, you start to have more limited tunability of the laser. And with the photonic crystals, they also have a limited bandwidth. So you have to get a very good alignment of the high-powered laser bandwidth and the bandwidth of the photonic crystals. And another kind of big challenge is that silicon nitride almost works too well. So it really is not very absorptive at 1550. So even if we were able to get all of this power on there, or just expand the beam so that we can make the photonic crystal work well, it's not sure that we'll actually see any heating because it's just not absorbing very well. So we also really want to see the effects of the heating on these sails and see if it really affects the dynamics of these sails. So these are the photonic crystals that we started making in our project. So this is just a microscope picture. This is all what you see in white is all a suspended membrane and looks a little bit like a trampoline. If we look very close up, you can start to see what the actual photonic crystal looks like. So it looks like this big pad with little holes. And you can see here from the high stress that you can actually, some of the holes start to elongate near the edges where the stresses are higher, but then you see them kind of normalized out here where the beam will be. So by here, all the holes are kind of the same size. And so one of the questions we were asking, where we were thinking was, okay, well, if it's going to be really hard to get a high-powered laser that is really in line with the photonic crystal at the exact same frequency. So why don't we essentially turn up the absorption? If you really want to see the effects of heating, why not turn up the absorption by using a much more absorptive wavelength? So instead of using near infrared light that's being proposed, why don't we go to this kind of visible light? So that's essentially what we started looking at. So here's the setup that we were using. Here's this little vacuum chamber that we made for this for this measurements. As you can see here, this is kind of the viewport through here, and you can see that because these are smaller sails, we can make a little array of 5 by 5 of them on a chip. And essentially what we can do is, so you can see here, each one of those squares is one of these little sails. And we essentially were able to use this laser vibrometer to essentially look at the dynamics of these smaller sails. And we were able to do this with high vacuum to essentially mimic the vacuum of space to really see what the heating effects were. And here we were using something on the order of a 3 milliwatt laser. And so this essentially is the measurements that you get. So you really start to be able to look at the mechanics, the actual individual eigenmodes of our structures, which is something that you can see with these kind of setups. So these are really quite interesting because you can really start to look at how are the dynamics on a spectral scale looking. But for us, well, one of the things that was quite interesting was that as soon as we put this visible laser on it, we essentially started seeing this driving of the mechanics without any kind of piezo driving or anything like that. We just started seeing this driving in the motion of the membrane. So here I can actually just show you a quick movie of what that looks like. So here we have our beam. We aim it onto our small sails, and you really start to see the motion of this membrane starting to move around and starting to kind of oscillate. And we found that really surprising. And what we also found surprising, which I think should happen very soon, is that what you notice is that even after we take it off, you still see this kind of oscillation in the membranes. So now it's really nice because if we were to do this at near infrared wavelengths, we wouldn't see anything like this because it's just not absorptive enough. But this is kind of a really nice way of simulating what happens when you start to get enough coupling of the light with the sail. And so we started looking at for instance, the heating profiles of these things. So here kind of gives you a sense. These are simulations that we've done of the heating on these sails. You start to see that with the powers that we have and assuming absorptions that are well known of 0.05 absorption. So this is quite large compared to what we normally have, which is usually parts per million. You can start to see that we can actually increase the temperature of our sails to something on the order of 350 Kelvin. But that's already very interesting for us because one of the things we also noticed was that you start to see the driving of this membrane. You don't see it very well here, but essentially the frequency of our membrane is actually, the mechanical frequency of our membrane is actually moving up. But then what we started noticing is we also started noticing that at integer values of this fundamental mode, we started also seeing this mode oscillating, which is really weird for this type of structure. And we even started to see this really in the 35th integer mode of the fundamental. And that's something that we've really never seen before in our measurements. And what we start to see is that what we start to get is something that on the order of like something that looks essentially like a phononic frequency comb. So we start to see really integer values of these of our fundamental mode and integer values of our second order mode. And just to give you a sense, because I think normally when we think about strings, we think about a harmonic string, and that indeed does have these integer modes. But something like our trampoline really it's more of an aharmonic structure. So it's actually very strange to see this kind of structuring. So what we're now noticing is that this is actually really a new phenomenon that people are seeing very lately in the literature, and this is actually something that our sails are actually able to see quite well. And we think that this actually has to do a lot with the photonic crystal structure and the way that it dissipates heat. And also, what we're very sure of now is that we think that this is really starting to be some kind of nonlinear interaction between the different modes of our sail. And that's really important to know, because once we start to interface real sails with real high-powered lasers, we think this is going to really be quite a large effect. I mean, this is really a small sail now with small powers, but when you start really interacting a sail with really large powers, this could actually have some appreciable effects for steering and maneuvering. And maybe one of the things that I really wanted to highlight here that we did in this project, which I'm really happy about, is one of the big challenges is essentially how do you align these sails to another mirror? And because one of the issues is that these high stress films are actually deposited at high temperatures, which is not something that mirrors if you kind of bury it underneath So you usually deposit your mirrors, and then you deposit some layers, some sacrificial layer, and then you deposit your light sail material. But usually the light sail material is really done at these ultra high temperatures. And so now what we've been able to do is actually make these stacks and figure out a chemistry so that we can actually have a self-aligned sail with the mirror underneath. And the reason that's really interesting for us is because now that allows us to actually make optical cavities with these sails. And what we're hoping we can do is actually essentially use this as a launch pad for these sails. So instead of, what you would normally think is, let me grab a sail and let me put a high-powered laser on it and let me just push it. The idea here would be to really have this kind of intense buildup of power that allows us to lift the sails and actually allow us to start to play with the control of these things, which I think is going to be really one of the big challenges with these sails. It's not just about pushing them, but really about doing it in a stable way. So we're really quite excited about this, and this is really, I think, one of the first times people have been able to kind of get a stack like this to work. And then quickly, just on the computational side, because we've actually been doing some really nice work on the computational side. So my colleague, Miguel Bessa, and also our shared student, Lucas, have really been working hard on, essentially, there is a new a topology optimization strategy that really works with neural network computation. So the idea is really mixing neural network computation with topology optimization. And this is something that's actually coming out of the Google AI labs. And so far, they've really been using this for more structural engineering, for structural mechanical structures. So now what we've done in this project is actually assemble this for optics. So now we're essentially trying to redesign how these photonic crystals are made for reflectors. So instead of having an array of holes, maybe having something that's much more exotic. So what we've already been able to show is that we can come up with these kind of new types of designs. And what we're now able to do is really start to perform as well as some of the top topology optimization methods in terms of coming up with new photonic crystal designs.
Three minutes, Richard.
Oh, perfect. I'm then we're good. And so one of the things that I'm really excited about with this part is that one of the things that people have been really concentrating on is the acceleration distance. So how much acceleration can I get and how much distance can I get? How long can I accelerate these sails? And I think that it is a very interesting question. But now one of the things that we're looking at is actually more on the manufacturing side. So right now, I told you before that, to produce this kind of large sail costs something on the order of 30,000 euros to make just one sail. And so now what we're doing is we're asking this kind of machine learning algorithm a new question, which is, can we essentially make this cheaper? Essentially changing the size of the features that we need to make this reflective, essentially making them bigger so that we can make this in a much more cheaper fashion. And we think that already can allow us to make these sails something on the order of 10,000 times cheaper just by going to these kind of new geometries that are easier to make. So this is something that I'm really excited about because it's really thinking more about the costs of making these sails, which I think is important, rather than the operation, which I do think is important. But I think before we get there, we got to really figure out how to make them cheaper. And I think this is something that I'm actually really happy in the direction we've gone here. So essentially, I want to conclude by saying that, yeah, I think this interaction with high-powered lasers and photonic crystals is going to give rise to nonlinear behaviors. I think we're looking at really a post-Moore kind of nanotechnology with these sails, and I think there's going to be really a lot of exciting avenues to explore with this. And I think before we go to high-powered lasers and sails, we need to figure out already kind of intermediate steps for characterizing how this really works, because it's a completely new regime of light matter interaction, I would say. So we really need to kind of figure out how to do this in a proper way, in a cheap way, in a reliable way. And one of the things we're thinking about on the machine learning side is really thinking about costs rather than the actual acceleration. And I think that that's going to actually have a really big impact on the field. So I just want to, thank my collaborator, Miguel Bessa, also my lab. I also want to thank all my other collaborators, and especially I really want to thank the Limitless Space Institute and Sunny. I mean, this has really been an amazing opportunity, not just to do some really nice research, but just bringing together this community of people with similar interests. So for me, that's really one of the really nice things. I've had so many nice conversations with a lot of the members here. So it's just, thanks for the adventure so far.
Thank you, Richard. Really appreciate that. Let's see here. Need you to stop sharing. We can get back to being able to see everybody's smiling faces. Can you stop sharing, Richard, or?
Oh, sorry. Yeah.
There we go. Awesome.
There we go.
Great talk. Thank you, Richard. Fantastic. And thanks for the kind comments. Yes, it's definitely exciting, the fact that all the different work that everybody's doing and the collaboration, right? Having had a chance to dialogue with some of the other performers and so forth. I think that's it's definitely been very useful for everybody. I think we got some questions online. So before I get to those, just open it up to the other performers and the other folks, panelists in the room. Any questions? I see several raised hands. I don't know what order they were raised in, so I'm going to go. Kelvin Long, go ahead.
Hi, yeah, thanks, Richard, for a good talk. So I'm also on the Starshot Advisory Committee, and I've been involved with Starshot since 2016. Even before they went live, not as long as Phil Lubin, of course. But one of my views about Starshot is that I worry about self-similarity. In other words, that the performance of the SAL and how it responds, the physics response will not be the same over large ranges of input beam intensity. And I have, that's mainly from fusion physics experience, which I'll talk about in my talk a little bit, but interesting to see your comments about non-linearity. So I wonder if you have any comments about self-similarity of these SALs over a range of input wavelengths and intensity. And if Philip Lubin's on the call, I don't know whether he'd have any comments on that as well. Thanks.
Phil is online.
Yeah,
Question, Richard.
I am.
Sorry. So Kelvin. So the question was, how do I think this will kind of? How do I think this will work in terms of this kind of long range pushing with radiation?
Well, if you're changing, like if you're using like a I don't know, you're talking about 100, 200 gigawatt lasers, but what if you're doing experiments like with a 100 kilowatt laser or something? But you're doing it on the same SAL material, would you expect the physics response to be the same? Because you're talking about non-linearity here. You're talking about
yeah. So I do think that it could be quite different, and I think it's really this mix of how the optics and the mechanics couple together, and how they couple different mechanical modes in these structures. Because these structures are really different from anything that we've ever made as people, right? These are just like these things that are meters by nanometers thickness. It's just a geometry we don't know how that works in terms of nonlinearities and nonlinear mechanics. And I think that that's also going to need to be made into a consideration when we actually design these photonic crystals. So I don't think it's going to be as simple as just making something that's reflective, but really making something that changes, for instance, its index as it goes from the center to the outside to make it stable, or to deal mechanically with how it's pushed. So I do think it's going to be a lot more interesting and complicated than just pushing it. It's going to be really I'm actually quite excited about it as a challenge. But maybe Bill actually also has another because he's really on the high powered laser side, and I think he's got a lot of thoughts on this too.
Okay, I don't want to take up too much of your time, but so my thoughts on this are, that this is an evolutionary approach, and that the smallest objects, wafer scale spacecraft, Starshot class things, are always at the kind of, end point of looking at structures. Smaller things have the highest flux, they have the highest stresses, they have the highest accelerations. They are the most complex and difficult. And in this roadmap, you start with things which are higher mass, lower flux, and ultimately do go slower. But remember, the scaling relationship for the same launch mechanism, the same laser array, scales as the mass to the -1 quarter power. So going to something which is 10 kilograms, which is 10,000 times more than 1 gram, goes out at only 10 times lower speed. Building something that's 10 kilograms with the same array that you use launch, up to say 20% speed of light, goes at 2% the speed of light, and the flux is lower by 10,000 by the mass ratio. The accelerations are lower by 10,000. The dynamics are lower by 10,000. So again, this to me has always been an evolutionary goal, with the very smallest ones being the most difficult. I agree that, this is a very complex area, and whether you use photonic crystals or homogeneous, multi-layer dielectric reflectors, or, whatever we come up with, is going to be a challenge. But it does not stop the sort of roadmap to how you get to these problems. And you would love to have those problems. If the thing that stops you from going to 20, 30, 40% speed light is the fact that you can't make the proper reflector without blowing it apart, then perhaps you're satisfied with going at 5% the speed of light for a decade, 2 decades, whatever it takes to get to these other things. But the same launch mechanism allows you to launch tiny things or large things. And so I think it's very important to keep that in mind. This is an evolutionary as well as revolutionary process. I have to talk about more, but I don't want to take up your time.
Yeah, thanks.
Thank you, Phil. I think Remo is next on the question section there. Remo, you have the...
No, Richard, I'm curious about one thing. You mentioned in the first slides that you we're talking about the mirrors where is moving and there is a cavity inside. Usually this is a source of a dynamical Casimir effect. Do you experience something like that in your in this creation? And second, since this every technological apparatus is at the nanoscale, and usually at the nanoscale, these quantum effects come into play. Can you measure something that is moving strange from the usual expected behavior? And third, when you talk about the eigenmodes, are you talking about something that is a quantum mechanical problem or the vibration? There is something related with the 0 point energy or not, or there is no relation at all?
Okay, I'm gonna try to remember them and go backwards. So the first, the last one is these are just regular eigenmodes of the system, so nothing quantum about it, just your classical eigenmodes of a suspended structure.
It's a membrane, right?
Yeah, it's a membrane and it has eigenmodes in it.
Okay.
In terms of the quantum motion, right now we are not seeing anything like that. What we are seeing now is what we think is really internal nonlinear interactions between different eigenmodes in this structure. And but your first question is a very interesting one, because I'm also quite interested in these Casimir experiments. And so one of the things that we've been looking at is actually right now we can make these sails very, very close to another surface.
Yeah.
And so that's something that right now we're really more on the I would say micron scale, and we want to make that closer to really try to understand if there can be some kind of really strong Casimir interactions.
It appears so.
Because it's a really nice platform, right? You have this kind of flexible membrane, and you can really
Right.
get this plate interaction, which is very difficult to get when you try to align two things together. So we haven't seen anything like that, but I think we're still too far away. The spacings are still too big, but that's definitely a really big open question, and actually very big interest for us to see like how close can we actually get these things. And it's not trivial, because there's definitely a trade-off between how big we can make this plate and how close we can get it before you start getting.
Because if I presume that if they stick together, it is very complicated to separate them.
Almost impossible.
Yeah. I know this is a common problem for this kind of situation of the nanoscale. I see. That's interesting.
But I will tell you that one of the things we're really thinking about is how to in situ separate them out. If there's something that we can, some kind of posts or something that we can put in between them, such that if you do get a stiction, we could pull them. Apart.
Right, the stiction, right.
We think that will really allow us to push those spacings.
I see. Thanks.
Yeah.
Thank you a lot.
We have a couple questions from Joffrey Landis. Joffrey, I'm going to see if I can't get it where you can talk. I think it's giving you the opportunity to unmute and ask your question. I think you had several, so just wanted to let you do it directly. Are you there, Jeff?
Yeah, I think I'm unmuted. Am I good?
Yeah, we can hear you.
No, I actually was to some extent echoing the comments that other people were making. For the laser sail, I think the change of reflectivity with speed is going to be a real problem, because some of your graphs just showed an amazingly quick drop off of reflectivity versus wavelength. So I'm interested in what might be possible to do about that. Do you have a comment there?
Yeah, so I would say actually one thing that, and I've talked to Sunny about this quite a little bit too, is thinking on these shorter scales, because if you look at the Doppler shift that you would eventually get if you went to these relativistic scales, you're starting to think of it's starting to basically drop off to about 70%. But even with 70%, you can do quite a lot, and even on the local scale, you can do quite a lot. So, for instance, with the centimeter light sails that I was showing there on the wafer, for instance, if we used even about, I think 10,000 times, somewhere around there, less power, we could start to, for instance, in the solar system, start to reduce these mission times from years to really hours and days. And I think that that's actually quite interesting in terms of what you can do, because if you look at the more local scale, you don't even need to go to these relativistic speeds. You can really go much less and still do quite a lot. But in general, I still think that even though there is a big drop off, I still think that you can push quite a lot with 70%. It's a linear process. So and you're not going to get much more from 90 than you would from 70. So it'll probably go from 90 to 70 around the end, but I think it's a really big challenge. It's a really big challenge to figure out how to really engineer this all the way through.
Jeffrey, I'm going to put you back on mute. And then that Lou Friedman, you had a question. I'm just going to let me unmute you here real quick, and you can ask directly. Lou, you're on mute right now, so if you're talking, I can't hear you. Well, I will read Lou's email or question. Does the increased reflectivity due to the holes come from the laser beam interaction, or is it intrinsic to the optical crystal?
So essentially the way it works is that your laser comes in, it interacts with the holes in a way that it now starts to form this mode, this stationary mode within these holes. And that stationary mode constructively interferes with the incoming beam and destructively interferes with anything past the beam. So essentially this guided mode is essentially what interacts with your incoming beam and it gives you this reflectivity.
Okay, awesome.
Hopefully that answers the question.
Well, one more question from Roman Kisrasvili. Roman, I'm going to allow you to talk as well, so you can unmute and ask directly if you'd like.
Good morning, everyone. I have a question related to using photonic crystals. You mentioned and have shown different materials, including modern 2D materials like molybdenum S2, molybdenum selen 2, and they have been in your scale up. However, in 2010, we suggested graphene-based photonic crystal. And as you know, you see, this work shows that graphene-based photonic crystal is very useful. What is this? The layer of graphene, then comes layer of dielectric, again graphene dielectric, and then you're making the holes in this structure. As a result, you're getting photonic crystal because there is the dielectric contrast between the holes which you have in this system and this layered material, graphene dielectric. For example, you can use HBN as a dielectric. So this material much better. So and then 2D materials based on TMDC materials, and better than phosphorine as well. So I can send you these papers. They are published in Physics Letters, and I believe experimental study of that, it will be very interesting because graphene much lighter than materials which you're using, number one. Graphene much stronger than mechanical properties of graphene much better and stronger than materials which you're using there. And number three, graphene has highest reflectivity. Thank you. I will send you the papers related to photonic crystals.
Yeah, thank you, Roman.
Yeah, thank you, Roman. Just put it in the chat, and we can pull that out.
So maybe I'll just make the quick comment that one of the reasons that graphene has not been has been difficult is really because of the absorption. So you have this kind of wide band absorption of about 2.3%. Across the wide wavelength span, and that's essentially, when we're talking about silicon nitride, we're talking about something on the order of parts per million absorption, which is really quite needed. But I think the other part is that one of the things that I think people don't think about a lot with the materials is they think about the index and the absorption, but it's also the high stress. So that's one of the things that you really need in these materials, because if you have something that doesn't have a high stress in it, then you have something that looks kind of like a trash bag waving around in space. So it's really hard to align to. So what you really want is these high stress materials, but they are also more difficult to work with because they can break if you don't engineer them in the right way.
I got one good. This will be the last question, and then we'll talk about shifting into the break. Joffrey has a final question. For non-normal incidents, is there a strong angle dependence of the reflectivity?
Yeah, it's a really good question because there is a dependence on this angle, And that's actually one of the things that we want to look at next with our machine learning algorithm, is to actually make not just make a design that is more reflective, or we actually want to look at, for instance, making designs that are alignment resilient designs, something where we can really pattern or put noise on these holes in a way that even if we have a little bit of misalignment, you get kind of on average the best reflectivity you can get. So I think that it is a problem, and I do think that at these larger scales, you can actually engineer that in a way that you could not engineer at these kind of micro millimeter scale photonic crystals. So it's a really interesting question. Actually, one of the things we really want to start looking at very soon.
Thank you, Richard. Any last questions from the panelists? Awesome. Great talk, Richard. Really appreciate the update. As always, good work. Very impressive. Getting back to the schedule, just a tiny bit ahead of schedule, but we'll go ahead and eat that up by stretching the break just a tiny little bit. We had a break scheduled for 9:50 Central Daylight Time. It's 9:47. So we'll just plan on taking the full extent of the break. Excuse me, sorry. We'll be reconvening at just like a minute before 10:10, and we'll start off with Kelvin Long. Will be talking to us about some amazing work he's been doing with some software code to model inertial confinement fusion, and that'll be the first of 3 talks before we go into our virtual lunch break. So I'm going to go ahead and put up a screen share, just a splash screen, to let people know that we're still here, but we're on a break. But feel free to go get a drink or coffee. I'm going to go get a drink. But we'll be back in just 20 plus minutes. Thanks, everybody. Hey, Kelvin.
Hi,
A couple
buddy.
more minutes, I guess, and we'll get started. But
Yeah.
you got to turn the camera back on so we can kind of get people will see we're about to get back to it here in just a minute. So, is that tea or is that coffee you're drinking?
I'm afraid it's tea.
It's tea. Okay.
Yes.
I think you said you do coffee at least once a day, right?
Oh, I usually intermingle. I go tea, coffee. But I probably drink more tea than coffee.
Ah, okay. Yes, I definitely still do the coffee. I flirt with the tea every once in a while. I still like the bite of the coffee. I haven't. My wife, she'll switch to tea all the time, and a couple of folks here in the office, they're big tea drinkers. But
Yeah, come over. I'll make you a good cup of tea. Proper cup of tea.
yes. I was going to say, I think we took some of your suggestions when you and I dialogued offline about the proper way to make tea.
Yeah.
And my wife uses those techniques now, so she's got the Kelvin approved methodology folded into how she makes her tea.
And what angle do you dunk your biscuits?
Oh, now see, this is a whole other interesting discussion. What angle do you dunk your biscuits?
Did I send you a paper that time about that? The angle, the optimum angle for dunking a biscuit into a cup of tea.
I can't remember, but that sounds like
about 30 degrees, something like that from memory. I think that's the optimum angle you meant to dunk. Because if you dunk too deep, it gets too wet and it collapses.
Yeah,
if you dunk too shallow, then you just don't get, it doesn't get hot enough, and you take too long and then it collapses. So there's an optimum angle for dunking it. I think somebody did a master's thesis on that, something.
That's fantastic.
I'll publish the paper on it anyway.
That's fantastic. Cool. This is important knowledge. We need to know these things.
Yeah. Absolutely. Yeah. Hopefully my voice will hold up. I've not been well the last few days. So.
Oh, I'm sorry. Cold or because I mean nowadays if you get anything, you're like COVID. You know. Yeah,
kids are back at school, so you pick up all the children bugs. So it's usually where it comes from.
Yeah, one of our friends was getting sick, and they went to go get tested to make sure it's not COVID. And it turns out it's just a cold. But just the sensitivity we have these days, you just tend to be a little oversensitive to things. So
I've got a lot of slides. I've got about 79 slides. So
all right.
I'm a little bit worried. I might have to pick up the pace to.
Well, so we got 30 minutes followed by 10 minutes of questions, and the 10 minutes of questions, we'll just do what we can with it. I'll give you the 3 minute, and I'll try and make sure when you're getting right up against the next speaker slot, right? So, but we'll try to adapt and figure out what we need
I'll
to
keep
do.
an eye on the clock. My problem was having knowing what to cut. To be honest, I've got so much stuff. So. Running calculations even this morning. So.
Oh, that's awesome. That's a thing of beauty. So, all right, it's 10:09. I'll go ahead and do the wind up here and hand the microphone over to Kelvin at 10:10. So welcome back from our break. This is the second part of the morning session. We've got 3 talks coming up, starting off with Kelvin Long, followed by a talk from Setthivoine, and then closing with Remo Garattini, who will take us into lunch. But right now we have Kelvin Long will be talking to us about his project Helios X, inertial confinement fusion for advanced space propulsion. Kelvin comes to us from the United Kingdom Interstellar Research Center. Kelvin, I'm going to hand you the microphone and put myself on mute, and you have the sir. And I'll try and give you the 3 minute warning. I'll just step in verbally, and you'll see that. So, thank you, Kelvin.
Okay, just can you see my screen or not?
Cannot see your screen currently. No.
Okay, hang on. We had this problem before, didn't we? Right. Okay. You can't see my screen there?
No, we cannot.
Right. That's not a good start.
That's okay. We'll get it figured out.
Right.
Share the screen and then click share.
What I'm doing to save time is I'm emailing my slides over to Sonny quickly, and Sonny, you'll have to be the navigator.
I will be your chart flipping monkey. That's my job. That's what I'm here for.
I'm going to lose minutes trying to sort this out. So okay, sending the PDF over to you right now. I should have sent it to you earlier.
And I won't count. This doesn't count against your time. Don't worry about that. We'll just shift to the right side.
Okay. My fault. Okay. So and then you'll have to share your screen. Okay.
We're waiting for the zeros and ones to cross the pond and come over and come into our inbox. Waiting. And you had sent me an earlier email as well. Is a version of those slides in that email?
No.
Okay. All right. So
No.
we will wait just a couple more
I've
seconds.
sent it to you. You should have it.
Think the hamster is turning. I have an email from Roman, but that doesn't include your charts.
Apologies, everybody.
What's that?
Have you got them?
Not yet.
I sent them to your sunnylimitlessspace.org. That one.
Sunny at limitlessspace.org. That is the correct one.
So refresh your screen.
I'm forcing it to refresh. Apparently, I'm suspecting that the digital file has to go through COVID protocols. It has to go get a COVID test, be able to prove to the email servers that the COVID test was administered 72 hours before the emailing to make sure that it's compatible with the American servers. And apparently, it still hasn't made it through the COVID protocols.
Sonny, are you running an FDA-approved antivirus on your computer or not?
Right. I know it's the FDA antivirus thing is just not working. So, Kelvin, we don't have it just yet. Let's see.
Accessibility. I mean, I'm in my settings, accessibility, and it's I've had this problem before, haven't I? Firewall's off. Okay.
Can we send that through chat, Sonny?
What's that?
Can we send it through the chat?
That's a good question. I don't know if you can embed and paste it in the chat or not. So,
Sonny, you check your email again because I did email it to you. I'll just send it.
Yep, I did a force refresh. This is the second time.
Okay, while you're waiting for the slides, which I hope will arrive any moment, I'm just going to save some time and show you this model, because this is what I'm going to be talking about quite a lot in the talk, which is Daedalus. Okay, so Daedalus is this starship idea from the British Planetary Society in the 1970s, and this is a 3D printed model of it. So you can see here we've got a first stage and a second stage. So essentially what I'm doing is I'm building a code in Fortran 95, which attempts to model systems like this, and then to perturb the design space to encompass other designs. So it's inertial confinement fusion designs. So this first stage, about 50,000 tons of deuterium helium-3. You can see the big engine bell. And this is the second stage, 4,000 tons deuterium helium-3. Very small payload on the front. Well, I say small in my hands, but in reality, it will be 450 tons, 9mm, 50 tons particle assured beryllium on the front. So essentially, the problem is to try and build that in Fortran, and then to try and perturb the model so as to encompass other designs. That's essentially what I'm trying to do, and that's what I'm hoping to show you. Have you got slides yet, Sonny?
No, I'm doing one more thing just to make sure, and then I think we may have we'll do a real-time audible slight shift that'll give us a little bit more runway to work the little tweak we're trying to tweak right now.
Okay.
Do me a favor, email fro@limitlessspace.org.
How do you spell that?
FRO.
FRO? Okay,
Yeah.
got it.
Fro@limitlessspace.org.
Send the slides there straight away. Apologies, everybody.
That's okay.
I think Fro is asking what the size of the file is.
It's only about 5-6 megabytes. It's not big.
Yeah, it should come right through.
It's a PDF. So, okay, sent that. Okay. Ooh.
No worries, we'll get this overcome. It's all right. It's just sometimes technology is like this, right? So Fro, do you have anything in your inbox?
Negative, sir. I'm still waiting.
So
nothing in the
here-
inbox yet.
So let's do this in order to give us a little bit more runway to deal with this. I'm going to do a slight shift in the agenda, right? This is, so think about this, right? Technology doesn't always work. Sometimes you have to do adapt and overcome. Even yesterday in the middle of a board of advisors meeting with people from all over the globe on, our TV that we were using for that meeting actually died in the middle of the meeting. And so we were able to shift to a PC to be able to continue to do the meeting. So sometimes things happen and you just adapt and overcome and think about the things that we're trying to work towards. We're trying to enable interstellar flight for crying out loud. So there's going to be lots of stumbling blocks before we get there. So this is just a blip. So if it's okay, would it be okay if I shifted the agenda?
Yeah,
So,
yeah.
I have the slides.
Check your email again. It's definitely sent and to Fro now. Just check one more time. Refresh your
I got
screen.
them.
You got it, Fro? All right.
I have them on. Yes.
Okay. So where you're loading them up, I'll just start talking to save some time because I do apologize to everybody for that mess. So I'm Kelvin Long. Many of you have met me before. As I say, I'm trying to build this Fortran 95 code, and essentially, this idea of using ICF propulsion starts from Project Orion in the 1950s. Stanislaw Ulam, Kolinis, Everett talked about using nuclear bomb technology. Obviously, we can't do that. So the question is, can you shrink that technology down to a much smaller size? And that's the ideas of using these tiny capsules with laser beams to compress them to a fusion ignition state. So there's lots of advantages to fusion propulsion in particular, such as high specific impulse, high specific power, high thrust, high accelerations. The weight of the fuel is much lower than alternative methods because they tend to be hydrogen isotopes, high power to weight ratios compared to alternatives. And to make things simpler in my model, what I'm actually doing is building what's called a fill-free space model. So it assumes a straight line orbit between origin and destination. So there's no usual conic sections you're getting trajectory analysis. I might move to that later, but it just simplifies the calculations because I want something that you can run very quickly. And okay, yes, I can see the slides. If you go to slide 3, thank you. So I want something that I can run very quickly. And can everyone see the slides?
Yes, we have them.
Cool. Okay, I'll keep talking. And you want to put it on the large screen so people, because I can just see it in nodding presentation mode. And essentially, I want to get to a point where I can run a calculation very cheaply rather than having to use big supercomputers or clusters of computers. So this is something which I'm running on a very small notebook. Slide 4, please. So this is inertial confinement fusion. It's very different to magnetic fusion in that we're using high number density of particles compressed using a combination of long pulse and short pulse lasers to nanoseconds. The idea is to hit the Lawson criteria. So that's the product of the confinement time, the number density, and the temperature. When it gets to a certain point, you have fusion ignition. And I won't go into the details of this, but it's very complicated physics in terms of how the thing hydrodynamically collapses and disassembles. Next slide, please. National Ignition Facility in San Francisco, which I've been to several times. Wonderful facility. They're currently at 70% power. That is 70% of the power that's being generated is coming from the fusion reactions in themselves. So they're very close to ignition. It's a large target chamber, very small targets. They're actually using something called indirect drive method, which is the idea is you put a capsule inside a whole room, radiation cavity, and the idea is to smooth out the radiation so that the asymmetries in the hydrodynamic implosion are minimized. I'm more of a fan of direct drive for space propulsion, but that's what we've got to go with at the moment is the indirect. Next slide, please. So there's lots of other methods out there. I'm not going to be talking about this today, particularly to save time. But at the moment, my code just focuses on hotspot ignition because that's the most simplest thing to actually try to model. The idea is you've got Lawson criteria being hit right at the center of the capsule. That's your spherical convergence effect. But really, there's other effects such as shock ignition, which I'm principally interested in as an application to space propulsion because you can get potentially much higher gain and also minimize some of the radiation that comes out of it. Next slide, please. So I won't talk about this much, just to try and pick up some time. Theoretically, you look at space propulsion by fusion, and it suggests maybe 26,000 kilometers per second, 8.6% of the speed of light. But in reality, when you start to folding all of the losses, it brings it right down to something like, with staging, you might get up to 15, 16% of the speed of light. So it's not as fast as, say, breakthrough Starshot type technology, but I would argue that this is much more appropriate for large payload masses. Next slide, please. So there's a set of standards when you're developing fusion propulsion software. In particular, work by Craig Williams, Stan Banowski, recommended design practices for conceptual nuclear fusion space propulsion systems. Things you have to define as parameters such as payload mass, fractions, wet mass, total mission time as the requirements, operational parameters such as distance, specific impulse velocity, specific power, jet efficiency, and system characteristics such as the structure, mass, power output, jet power, and thrust. So I'm trying to fold these things in. Go straight to slide 10, please. What we can see here is work by Schwartz in the 1990s from NASA, who did it's really excellent study into fusion systems. And he was looking at, for example, the sensitivity of the mass of the system and flight time, and how this varies with specific power. So obviously you can see when you if you want to get to the stars fast using fusion, it really requires very high specific powers. On this graph, you can see up to 100 kilowatt per kilogram, but as you see, when we get to Daedalus level type designs, we're talking about megawatts per kilogram. Next slide, please. So essentially with the software, these are the three goals that I'm trying to develop: to provide a design tool that permits a rigorous assessment of ICF assumptions used in space propulsion calculations, to give a reliable assessment of capsule performance outputs and how this influences the integrated spacecraft design, and to permit proper analysis of ICF-based fusion spacecraft concepts and literature, so as to demonstrate confidence or otherwise in claimed efficacy. Please excuse my voice, I'm just recovering from a cold. So at the moment, I'm really focused on ICF, but I have plans to expand it, in particular looking at antimatter catalyzed fusion, proton fusion, such as for interstellar ramjet modeling, and even looking at nuclear pulse options and something called a Medusa cell. Won't talk about them much more today. Next slide, please. I have a philosophy as approach to this, which is to think of this in terms of a confidence level of the code. Essentially, I'm starting from a Daedalus design, and I perturb that design. Once I can get the properties of Daedalus to good accuracy, perturb that design outwards to encompass more designs, and so that within the uncertainties of the model parameters, such as the cross-section uncertainties, the ISM density, all those sorts of things, I want to get to a point where I've got a 2 sigma level of confidence. That means 2 sigma standard deviation. So within about 5% error. So that would give me high confidence in the model. At the moment, I'm about 1%, I would say. Getting to 3% is possible, but the problem is that requires very detailed subsystem level definitions on any design. And the problem is if you go too deep into any design, it then becomes problematic to apply that same software to other designs, which have different subsystems. So I think there's a level you want to go to in defining this. Next slide, please. I mentioned earlier when in one of the other talks about self-similarity, there's an implicit assumption in diffusion ignition, whether you're going with kilojoule lasers up to megajoule, kilojoule lasers to actually try to drive the system, and then capsule masses, which might be micrograms right up to grams. There's an assumption that the physics responds the same. And actually, we know in ICF that isn't always the case. For example, this is a graph from a shock ignition study from 2011, which shows that when you get to a certain laser intensity, there's a switch over in how the pressure power dependence changes. And this is, by definition, not self-similar. And I personally fear it's the same for laser power driven systems as well. But that's speculation. The way I'm designing it, it's an iterative design tool. So you run the code, but there's certain things that I want to calculate, but you also have to estimate first. So for example, I want to be able to calculate the particle bombardment shield as the spacecraft is moving through the interstellar medium. But the problem is I also need the mass of that shield to go into my mass ratio calculations. So I'm kind of in a loop. So what you do is you estimate the mass to start with when you first run the calculation. You then run the calculation. It will then correctly calculate what the particle bombardment shield mass should be. And then you take that mass and you then put that back in the input as the revised value. And then you converge over about 2 or 3 runs towards the actual solution that simulates the real design. In other words, at that point, your actual input matches what it's calculating. And there's a few parameters where you have to do that, particularly for optimization as well. Next slide, please. This is just defining classes of systems for slide 15. It's classes of systems for different types of probes that I'm looking at. Next slide. Slide 16. I mentioned Daedalus. Daedalus is essentially a 2-stage burn system, and it's 2 structures. But you might only have one structure that's got 2 burns, or you might have two structures, which is 2 burns, but one's a boost phase and the other one's a deceleration phase. There's all kinds of configurations that you could run with, and I'm trying to simulate all of those. So currently I'm running with up to 10 different configuration types, how you can optimize the system. And that's quite complicated to actually try and run.
Kelvin, many apologies for the interruption. You said slide 16?
Yeah, slide 16 that was. Yes, that's slide 16.
I think you and Fro got out of sync. Please do keep calling the page numbers out, and Fro, that way you can
Okay, got it. Got it. Okay, slide 17. So here we're showing roughly the current programmatic architecture. So essentially you've got HitBurn, which is the main calculation program, which is a Fortran 95 file. And currently the input is integrated with that program. And I do plan to separate it to a separate input file. It's just not been a priority. I hope to have done it by today, but it's time consuming. It's not been a priority. And what it does is you can choose whether to link to the subroutine, which is, sorry, I do apologize. Helios X is the main program. HitBurn is the subroutine. HitBurn is the ICF subroutine. So you can choose whether to define the exhaust velocity, the burn fraction, and the parameters of the capsule performance, or you can choose to calculate it explicitly. And that's what HitBurn does. And HitBurn is very complicated, and I haven't finished it. So most of my calculations are running with Helios X and switching off a lot of the physics in HitBurn because it's very complicated and I haven't finished that. Just a whole bunch of output files, and the main output file, summary dumps, and advisory dumps for optimization, trajectory profiles, etc. Slide 18, please. So here we can see on slide 18 the code structure. So this just shows you how the calculations run. Just starts with the star target. I'll talk about some of this in a bit more detail in a moment. The class, it does a guidance calculation. So it simply run the numbers on the mass ratio requirement, and that'll give you advice on whether you've got the right, for example, deburn propellant mass that you're running with. And so it helps you to optimize the system. You can choose, it's got things like gravity assist now plugged in, and you can choose to switch those on or off. The type of fuels, a lot of this I'll go over in a bit more detail shortly. And you can see it all for yourself. We've even got full link budget calculations now programmed in for radio communications, particle shield calculations, radiators. You can choose to have radiators on or off. If you want auxiliary radiators for the power supply or radiators linked to the jet power. Slide 19, please. And this is just showing you the process of how the calculation is conducted. I haven't got time to go through all of this because I've got to catch up. But you can see starts with the exhaust velocities, which might be fed in from the HitBurn calculation subroutine, which is calculated explicitly, or you've defined them. So if you're trying to reproduce somebody else's paper historically in the literature, you might choose to define them because you're trying to see if you can reproduce their calculations. And it goes through, and I'm even looking at things like SETI emission spectra. So if they're fusion engines at a distance, what would it look like in terms of the Bremsstrahlung emission that's coming off of it as an optical signature? Slide 20, please. So here we've got the code structure for the HitBurn roughly. This is the input parameters. So essentially, at the moment, you can, because I'm only modeling 2 stages, up to 2 stages, you can define 2 types of drive beamers or 2 types of capsules. So you have to define for the capsules the types of the radii, the densities, etc. And you do the same for the laser beamers. And I ultimately want to expand the types of drivers, you know, from neodymium glass to krypton fluoride, carbon dioxide lasers, all sorts of things. There's a lot of work to try and plug this in. Slide 21. This is the calculation process for HitBurn, which I'm not going to go over, but there's a lot of physics to do with the hydrodynamic implosion or spherical convergence, the thermonuclear ignition, and then the disassembly and alpha particle deposition of the capsule as it's disassembling once the inertial system starts to collapse. And eventually you get your exhaust velocities coming out of that. Slide 22. So just to say, you can currently put in up to 27 stars, and there's astronomical information about those stars. Option 28 is an arbitrary distance. As you'll see when at the end of this presentation, I do a calculation for Mars, and you put that in as a separate distance. It does other things such as encounter time calculations, optical interferometer size calculations. In terms of if you had a telescope in orbit around Alpha Centauri, what's the equivalent interferometer you would require in Earth orbit to give you the same resolution? This is just showing you, next slide 23, some of the examples of the calculations. How am I doing for time, Sonny?
I've got 14 minutes before I give you the 3-minute warning. So you're in good shape.
Okay, that's good. Okay, so this is just showing the stage burns, obviously to a rocket equation. Slide 24, please. Logarithmic distance calculations to work out where the vehicle is at different stage burns. 25. This is just showing you, obviously, the energy that comes out of the capsule is equal to the energy of the fuel, which is joules per gram, based on the choice of reaction you choose to use, the mass of the capsule, the fuel in particular, and then the burn fraction. And this allows you to calculate the propulsive performance parameters. Next slide, please. You can calculate also lots of parameters, metrics, such as the payload, dry mass fraction, and so forth. Next slide, please. At the moment, I've got up to 11 types of fusion reactions programmed in, starting from DT all the way up to proton-boron 11. And at the moment, I don't do daughter reactions, or self-burn. So that's something that I'm going to do in the next phase of work. So this is kind of the first look at running the different equations and the different products and reactants. And I'm also looking at, as you can see, with option 0, proton-proton reaction, because I want to get to a point where I can run an interstellar ramjet. That's a lot of coding that still needs to be done before I can get to that point. But I'm coding the architecture to get ready for that. And you can also see an option 12, which is a proton antiproton. And that's because I want to get to a point where I can try and model an antimatter catalyzed fusion system, such as I can to AIM-STAR Penn State University study. Next slide, please. Option 28 is just showing you how I calculate the power supply. Let's go to the next slide, 29. Again, power supply, the power supply, slide 29, please. Power supply is estimated for both the auxiliary power supply, which links to the radiators for that power supply, but also the fusion radiators can be estimated, which is linked to the jet power that comes out of the fusion engine. So there's 2 types of radiators that you can calculate, and you can switch them on or off. Next slide, please. And this is just showing you more of the thermal management that's in there. Sorry, I haven't got time to go over this. Next slide, please. This is just showing you calculation of debris velocity that comes out of the exhaust nozzle, and then it does something called a momentum weighting function for the reactants in a reaction, and then it uses that to calculate what the real exhaust velocity essentially should be and how that feeds into the energy release for the reaction and then the power that's generated in gigawatts. Next slide, please. Neutron radiation, it does a first look at the amount of neutrons that's coming out of the reaction, and this is accomplished through looking at the various reactivities and comparing an aneutronic reaction to a neutronic reaction based on the reactions that you've chosen. It's a little bit complicated, but it gives me a first look at what the neutronic radiation environment is likely to be. Next slide, please. It does, as I mentioned, particle bombardment shield, calculates fully the particle erosion rates and the temperature on the front of the shield. Next slide, please. It does gravity assist, assuming whether you're approaching a planet or approaching it at an angle or chasing a planet or a star. It's not so relevant to Interstellar because we're going so fast, but as I say, I want to also be able to use this for interplanetary and precursor missions. So I think then it will start to be relevant. Next slide, please. Payload to propellant ratio. This is an optimization parameter, comes out of the Daedalus study. Next slide, please. And this is something, some equations I derived, published in 2011 for working out what the minimum pulse frequency should be and the total mission time for a given mission. Those were programmed in. So these are all guidance checks. So you go into the summary file and it gives you information about how far you are from the guidance checks as an optimum design. Next slide, please. This is Daedalus. I talked about it a little bit. Let's skip over these because we haven't got much time. Next slide. You can see Daedalus, 46,000 tons propellant, 4,000 tons, second stage, 250 hertz burn frequency. Next slide. Capsule, we'll skip over that. Deuterium helium free, highly complex. Next slide. There's lots of problems with Daedalus design. I won't go into all of them, but deuterium helium free was the choice of fuel. That was controversial. There's a tritium trigger right at the center. I can't model that at the moment, but there's lots of issues which are listed on that slide. Go to the next slide, please. So what I'm essentially doing, we're getting to the modeling now, is I've started with Daedalus, which is model I. So that's the published figures in the 78 papers. II is then my first model of trying to reproduce Daedalus using Daedalus's own numbers, so not updating the numbers at all. II is then updating it according to modern numbers. For example, they thought the interstellar medium density was an order of magnitude higher than we know it is today. So that's something which I have to tweak. And that massively reduces the particle bombardment shield from 50 tons down to only a couple of tons. So that's a huge reduction. And then I then go to IV, which is actually starting to plug in things which I think are more realistic for Daedalus mission. So Daedalus was meant to launch from Jupiter. So I plug in a launch distance from Jupiter. And also you're not going to launch from Jupiter at a space station. You're going to move away. So it moves away at sort of 17 kilometers per second for a day before it fires up that highly intense engine, which would just blind anybody that looks at it. And then option 5 there is I then apply it to Alpha Centauri because Daedalus was a Barnard star mission. Next slide, please. This is just showing you my first attempt to just reproduce the Daedalus numbers. I'm getting, percentage difference on the right there. You can see it's pretty good. I'm a bit off on a few things. The main thing that concerns me is the accelerations are off and the distance too. And that's because I'm not modeling the tankage droppage en route. So Daedalus drops its tanks as it's basically used up its fuel. What I do in the code is I drop the tanks only at the end of stage burn. So that's a minor tweak on the mass ratio that's required. And I think that will sort that issue out. I plan to do that on the next iteration of work. Next slide, please. This is just showing more of this, the same. Data 78, again, pretty close to their differences. Most of the things there are less than 1% difference or slightly more. The reason the particle shield is quite different, 8%, is because well, actually, I'm not sure, to be honest. Now, I thought that was a different simulation, but 8% difference in the particle shield. Yeah, the reason is because in the reports they just said about 50 tons. So they don't actually give the exact calculation. They just say what the number is about to. Next slide, please. So this is just showing the trajectory of Daedalus as I've calculated. You can see it's a flyby probe. Next slide, please. This is just now showing you the difference between Daedalus as it was, and then me running its numbers and its 78 numbers, and then me updating it. And you can see there's minor differences, but pretty good model overall. Wish I had more time to spend on discussing this, but it will be in the final reports. Let's skip over this graph. Next slide. So this is me applying Daedalus to Alpha Centauri. So it's as the system is, with its fuel, gets there in 37.35 years compared to half a century for Barnard star. Next slide, please. This is just showing you the trajectory to Alpha Centauri. Next slide, please. Now the question is, can we do it much smaller? So resolution was an attempt to just take the Daedalus second stage, and then we could do a reverse engine thrust, or you could serial stage it, but you basically don't use the first stage anymore. So next slide, please. This is showing two versions of resolution. The first one, VI, is a flyby probe, second stage only, and you notice it only has 2,000 tons of deuterium helium-free fuel, 150 tons payload mass, and I'm running at 100 hertz pulse frequency compared to 250 for Daedalus. So that's a vast improvement for a flyby probe to the nearest stars. The resolution B there is a rendezvous model. It's much bigger, 16,500 tons of fuel, and it does it in. So I'm looking to get in under 100 years. Next slide, please. This is just showing some sensitivity studies. Next slide. Next slide. Next slide, just skip over these sensitivities to catch up. This is a resolution, what it might look like in flyby mode. These are beautiful graphics produced by Michelle Lamontagne, a friend of mine in Canada. And next slide, 55. This is a flyby model of resolution. You can see it's operating at jet power 1.2 terawatts, 3.43 megawatts per kilogram. A thrust of 0.26 meganewtons, gets there in under 100 years, carrying 150 tons mass of probe. Next slide, please. And this is just sensitivity studies. This is the beauty about developing the software. You see the code is that I can run these sensitivity simulations to actually try and work out what things should be. Next slide, 57. This is the rendezvous mission, gets there in 100 years. And you can see the jet power is 1.2 terawatts, specific power 3.43 megawatts per kilogram. And it's traveling at just under 5% speed of light. Next slide, please. So I then went to 5-stage parallel thrust system, as it's called Endeavour. Next slide. You can see it's got this Quintec engine system. Next slide. Some more sensitivity graphs I haven't got time to talk about. Go to the next slide, 61. And we can see here that Endeavour gets there in under 100 years again. 9.16 terawatts jet power, 5 megawatts per kilogram. Gets there in under 100 years. And this is again 100. This is now 150 hertz pulse frequency, so not as low as resolution, but much lower than Daedalus. And this is much more practical in terms of where we can envisage pulse frequencies to be in the future. Next slide. The problem with that is long burn time. So I moved to Pegasus, which is a 4-engine stage system. Next slide. I was also concerned about neutronics and the bremsstrahlung from the radiation of the capsules. So we started building these radiation shields and moved to a 4-engine stage system. Next slide, please. You can see these 4 engines, beautiful graphics from Michelle. And you can see this gets in under a century once again. Jet power, 7.3 terawatts, 5 megawatts per kilogram. This is 150 hertz pulse frequency. Next slide. And you can see all of those on slide 66, all the Daedalus and resolution Endeavour trajectories. So go to the next slide. So we're getting towards the end, so I'll try and slow down a bit, just a little bit. So here we have Vista, because I wanted to end on an interplanetary system, because I'm mainly looking at interstellar systems. But Vista is an excellent study from Charles Orford, Lawrence Livermore. And I thought, well, let's try and apply the model to an interplanetary mission. This is a Mars mission, which would be much more of interest to the astronauts that are involved with this meeting. It's, uses an excimer laser, 5 megajoules, 166 kilometers per second exhaust velocity, 30 hertz pulse frequency, 100 tons payload, 6,000 tons wet mass, only 3.7 tons of deuterium tritium fusion fuel, but it also has 4,000 tons or so of augmented expellant fuel to go with it to increase the thrust, which I didn't have in my code already. So I've had to spend sort of a day trying to program that in, which is good because every time I apply it to more designs, I discover there's more stuff that's not in the code there that I have to program into it. So, power to mass about 20 kilowatts per kilogram, 1.5 kilograms per second mass flow rate. Anyway, the reason it's just funny conical design is because you're trying to optimize the jet efficiency of the system and the neutronics from the radiation. You go to the next slide. So it's meant to get to Mars round trip in 100 days, which means get to Mars in around 50 days. This is now showing you, if you look on the bottom right, paper versus Helios X. The Helios X is my calculations using my code for Vista, and the paper is showing you what it should be according to this 1987 paper. So as you can see, I'm getting very close to the Charles Orff numbers using my code, and I don't even have a subsystem level mass definition, so it could be improved. And you can see on the last table in the middle, that's my parameters, and I get to Mars in about 50 days. So it burns for about 24 days, and then it cruises for about 19 days, decelerates for about 6 days, and then it gets there in about 50 days to Mars. So that's pretty incredible. And I'm pleased that, I'm able to reproduce the Vista numbers, although I know that Charles has updated the design since. And I've also looked at other systems, but I haven't got time to present those today. So if you go to the next slide, so this is the output of the work I'm producing for LSI, essentially. I'm giving them a copy of the code when it's finished, which is the Fortran files and the output files with a nominal deck, so they can run that nominal deck. And anyone can get access to the code via request through LSI. They're going to get a copy of the code manual, which I'm writing, and a huge executive summary report, which details all of the calculations I'm doing and looking at several designs in the literature, including the Vista, which I mentioned, Hyde from 1983, which is a brilliant krypton fluoride laser study, and also what I'm going to talk about next very briefly. And I'm producing 3 papers which lays out some of the physics that's gone into this. This is just showing you the models. Okay, this is just showing the models I've looked at. Next slide, please. And slide after that. You've all heard of Discovery 1 from 2001 Space Odyssey, which is a beautiful device. I would love to see a version of this running in ICF mode. Next slide, please. Charles Orff, Stan Bronowski from NASA Glenn did this wonderful study, 2001 Space Odyssey, called Discovery 2, where they designed a magnetic fusion system version. So what I'm planning to do next, literally shortly after this meeting, is to actually try and code up Discovery 2, but as an ICF design. So that would be really interesting. I'm going to try and use as many parameters close to the Charles Orff study, as the Craig Williams study as I can, such as the Brayton cycle radiators, but obviously switch things out because they're using a magnetic fusion engine. And it'd be interesting to compare those studies to see how ICF does on a like-to-like basis. Next slide, please. So in conclusion, my summary slide, I think I've made really good progress with the code. I'm not as far ahead as I'd like to be. I was pleased to hear Jason earlier talking about 10 years to write a code. I've only been working on this really for the last year. So, I've got some way to go, but it's doing really well. There's things I can improve, such as mass budget definitions and stage tankage drop along the way. I need to improve my understanding of some of the literature published designs so I can better model them, because some of the designs are not so clear in terms of what their assumptions were, and continue to expand it to a wider design space. And there's further work for improving the scope of the code, such as I definitely need to include daughter reactions. That's planned in the next phase of work. More complex vehicle designs, and sub-methods of ignition. Once the hit burn is complete for hotspot ignition, I want to be able to code it up to be able to apply to other types of ignition methods. And so finally, I just want to acknowledge Rob Swinney, Michelle Lamontagne, Adam Crow, Adrian Mann, LSI and Breakthrough Initiatives who have been involved in this work in a little bit, or have been supporting me throughout this endeavor. And I'd like to dedicate this talk to Winchell Chung for the Atomic Rockets website, who's been a fantastic inspiration in developing the Atomic Rockets website, which a lot of us use. And he's not well at the moment, so I wish him the best of health for the future. And with that, my last slide, I will leave you with this, and I hope I caught up. Thank you.
Thank you, Kelvin. Fantastic. Absolutely fantastic. Jason put a note in the chat. We were talking about code. He said, Kelvin, you just work 10 times faster at doing code. That's my conclusion. And I also want to say you work 10 times faster at doing charts than anybody else. You just went through 72 charts, and my 3-minute thing still didn't go off. So you had to, there we go. It's finally going
Okay.
off. So
I just assumed I'd lost 10 minutes at the beginning, so I apologize. So.
That's okay. That's all right. We're adapting the timeline a little bit. This just probably means we'll have a slightly shorter launch, but that's okay. We're all about the technical stuff. So thank you for that. I think you definitely saluted the phraseology that kind of has grown up around this concept. Go incredibly fast. You went incredibly fast on those charts. That was awesome.
Thank you.
But anyway, what kind of questions we got from the group? Awesome presentation, Kelvin. Thank you. Questions from the panelists? Pierre, I couldn't tell if you were talking or not. It looked like you were. Jason, go ahead.
Yeah, I've one. Excellent talk, by the way. I really enjoyed it. You mentioned something earlier, and I didn't understand it. I was just hoping you could clarify. It was you had mentioned that shock ignition reduces the radiation output, and so I just wanted if you could clarify what you mean by that.
Yeah. So basically, obviously, when you get to hotspot conditions in an inertial confinement fusion capsule, once you start to get, you get your alpha particle deposition, and you get a lot of high energy neutrons coming out from reactions, 14 MeV neutrons, but you also get a lot of Bremsstrahlung emission, and that irradiate that if that gets out the capsule, that starts to irradiate your structure, right? So point of inertial confinement fusion is to combine it as long as possible to get as most out of that reaction. But once it starts to disassemble and the density drops to the whole thing, those 14 MeV neutrons start to escape, and that radiates your structure, so that you get fatigue issues, all kinds of things. So that's why you need radiation shields. Shock ignition is very unusual in that it has very thick ablative shells. And so the idea is, instead of for example, when superthermal electrons are generated, so your laser hits your electron plasma frequency, and obviously you get your reflection, and the laser can no longer contribute towards the implosion. But what happens is you get superthermal electrons, which are generated in a normal capsule, and they will get deposited into the fuel, and that will heat the fuel, which is not what you want because you're still trying to RODR collapse the system. But what shock ignition does, because you've got very thick ablator shells, the electrons get deposited directly into the capsule, and so they help to improve the RODR effect, right? So because they get the deposit of energy, and what happens is also because you've got thicker shells, any 14 MeV neutrons, they get captured in the helium. Because you've got lots of helium, so you get a high density of helium layer towards the outer edge of your fuel, but also the Bremsstrahlung, the X-rays that come out, they get caught in that shell, and so it helps to keep it together for longer. And one of the things I mentioned about shock ignition capsules is potentially they give a lot bigger gain, like because the power spectrum is a lot bigger. So for a NIF type capsule, 1.8 megajoules, you might only expect 10 megajoules output or something, but for shock ignition type capsule, calculations suggest you might get 150, 200 megajoules output. But that's based on 1D simulations. Once you start switching on, looking at hydrodynamic effects in 2D and 3D, you get all these sort of Rayleigh-Taylor instability effects and Kelvin-Helmholtz effects, and they all kick in, and that starts to ruin the symmetry a little bit. But the indications are that shock ignition is much better for space propulsion potentially.
I have a question basically to Kelvin.
Hold on, Roman, stand by, sir. I have a couple other people in front of you. I apologize.
Okay.
Got to go in order here. Phil Lubin, your hand was raised, and then I got Creon and Jim Gimzewski, sorry, to go through. And I don't think we're going to be able to take all the questions because we're running a little hot on the schedule. So I want to try and get back to closer to the timeline. I apologize. Kelvin, you may have to answer some questions on the chat at some point. So if we don't answer your question, talk to Kelvin on the chat, and he can be dialoguing in the background as well. Go ahead.
Okay, Kelvin, great talk. Really enjoyed it. I was wondering if you could just comment on some paths forward to doing testing of the basic inertial confinement fusion portion, and what you see as sort of realistic in the next, say, decade to test out some of the core physics for either laser driven or particle driven ignition.
Yeah, so what I would say is, so my I never used to be able to say this, but I'm okay to say this today. But I used to work in the nuclear weapons world. That was my day job for many years, and one of the problems is a lot of this information is still classified, right? So, but it is public knowledge that there were the Halite Centurion tests, which actually explored the use of capsules under different driver conditions of different masses. The details about those are classified, so I can't talk much about it. But I feel that one of the things that could really happen, I think, is if some of that data was opened up, and so that we could use some of that data in our codes, for example, to help validate some of these ICF models. Now, obviously, NIF has the luxury that they can use that data because NIF is also used for underwriting, the stockpile, which is great. But it'd be nice if some of that stuff can be used for ICF in the applications we're interested in, such as power generation for the cities, but also for propelling space vehicles. So I guess what I'm saying to you, Phil, is that there's already a lot of experimental validation that exists, but unfortunately it's behind the wire. So I think, yes, there are experiments we can do. Like, what's the next thing on from NIF, right? So are we going to build, instead of a 2 megajoule facility, are we going to build a 10, 20 megajoule facility? Is that something that's going to happen? I would personally support that. I think it will solve a lot of problems, and it's really interesting physics. But I think there's also a lot of data which is potentially available to us, which is already experimental validation of our models, which unfortunately a lot of people don't have access to. And I feel that's, people like Charles Orff at Lawrence Livermore is a great guy to have in our community because he still has access to that community. So maybe there's conversations that could be had.
Charles passed away, unfortunately.
I didn't know that. Sorry to hear that.
Yeah, I used to work with him actually at Lawrence Berkeley Lab. Yeah, unfortunately passed away.
Thanks for the bad news. I didn't know that.
Yes, sir.
Jim Zimzewski, I think I have you up next in the queue for a question. I think we got time for maybe one more question after that. Set, I think that means you have to wait. I apologize. So, Jim, are you there?
I actually have a question as well, actually.
Well, let me, so Jim, you have, I've got you unmuted if you want to unmute and ask verbally. Okay, all right, Jim, just type it into the chat thing, and then I think I apologize, Seth. I think Roman had wanted to ask a question. And Roman, keep your question short for me, would you? Keep it short.
Okay, let me unmute myself. Kelvin, hi Kelvin.
Hi,
So it's basically a question to Kelvin and as well as to Jason. You know, what is the ratio of radiation shielding with respect to the ratio of the apparatus by itself? Because shielding from neutron shielding, it's very, very important in all such kind of devices. So this is a question. And comments is that recently discovered new two-dimensional materials, HBM, based on boron. They are atomic thick. They can be used as a result to decrease the weight of shielding.
So are you asking what's the ratio of radiation shielding to dry mass, or what's the ratio reference
to dry mass?
Oh,
yes.
It's very small. I mean, I can't tell you offhand, but it's not a dominant factor in the design. The thing that's dominant for basically for interplanetary missions in terms of fusion, the dominant mass is the power plant. And that is what drives the performance. And for interstellar, the dominant mass is the propellant, because you're trying to get to very high energy. And these are the things that dominate the mass. Obviously, payload mass fractions are very small for interstellar, like 1% or less. So I would say radiation shielding, it is important and you need to have it. But, you know, there's clever things you can do to minimize it. And, you know, insulation layers, clever capsule designs, if you're talking about ICF in particular. I mean, I can get you the numbers and email them to you, but I haven't got them to hand.
All right, thank you, Kelvin. Awesome job on the presentation. I'm going to try and move us into the next slot, so we're only a little bit behind schedule. Set Beyond You is going to be our next presenter. He's presenting to us about the development of a physics-based model for high-power peristaltic magnetic nozzle. This is a fusion concept, very interesting. It comes to us from HelicitySpace in partnership with Caltech and University of Maryland, Baltimore County. Set, you have the con. You're on mute before you start, just so you know.
Thank you very much, Sonny. Can I share my screen? Can you see this?
Yes, we got it full screen.
Great. How do I minimize this? Minimize that.
Yeah, we can't see any. Sometimes the video thumbnail from Zoom stays over there. We can't see that. So.
Oh, okay. Yeah, because I was seeing the thumbnails and trying to get rid of it. Yeah. Okay, great. So thank you, Sonny. Thank you, everyone, for attending this briefing. And I'm happy to represent the HelicitySpace Corporation, collaborating with Caltech and the University of Maryland, Baltimore County. I'd like to thank Limitless Space Institute for supporting this work. Excuse me, I'm sorry. And the Department of Energy for also supporting a portion of this work. All this actually is part of a larger project and collaboration with academics, academia and national labs to develop this new fusion concept that we call the Helicity Drive. And this work here is really supported by Limitless Space Institute for developing a portion of it, which is the modeling of the magnetic nozzle, peristaltic magnetic nozzle portion. So the project team here is mainly the Caltech team. So Professor Paul Bellon there is helping us with the magnetic nozzle design and concept. He invented this in the 1970s. Setthivoine is his postdoc, working on the calculations, and then Professor Carlos Romero Talamas is the mechanical engineer at UMBC, who's helping us with the hardware design, and his new graduate student, Natalia Marian, has been fantastic at building, fabricating, and testing. We've also had the help of senior undergrads in their final design projects, and they've been extremely useful and very helpful. It's amazing to have such a great team. So the basis of the whole project is really this new fusion propulsion concept, which we call for short the Helicity drive. I'll explain a little bit later why it's called Helicity. It's a pulse magneto-inertial fusion concept. So it's aimed primarily for a space propulsion and power system rather than terrestrial power plant from the ground up. So when we conceived of the concept, we tried to think ahead as to how to apply it for a system that is as light as possible, and as Kelvin mentioned, as high a specific power as possible, given what we know today. We exploit three key ideas, A, B, and C. Something we call magnetic plectronemes to confine the plasma that's been newly discovered in the laboratory. We use magnetic reconnection to preheat the plasma. So when we merge a number of these plectronemes, they preheat the plasma to high temperatures, which reduces the actual compression ratio required to raise the energy density to fusion condition. So if you run through all the calculations, you get the triple product that scales uniquely with a number of objects that merge at the beginning. So n to the raised to the power 3/2 in this case. So that's quite different from all other prior fusion concepts, because the triple product now has an extra control node, operational parameter, in addition to the usual, plasma current, magnetic field, plasma size, and compression ratio for magneto-inertial fusion systems. And the idea is you can roughly compensate a little bit for uncertainties in the confinement time. As you scale up, you can have more guns instead. Also, you spread the input energy over n guns, so the energy density per gun can remain constant effectively. And it also means that we could potentially accelerate the development path of this concept, because it's analogous to cylinders in a car engine. Instead of increasing the size of a single cylinder, you can use the same cylinder and put those in parallel effectively. So the philosophy why we're also aiming for fusion propulsion concept is that really any fusion concept, at some point you need to get net gain. But what can you do when you get net gain? Now, the idea is that even with modest net gain, you should still be able to push a spacecraft. It might not be the most efficient, the best propulsion system in the world or ever. However, it would be a fusion propulsion system. That's even before you achieve sufficient gain to be able to recirculate some of the power to make it self-sustaining, which is the goal of a power plant. At that point, you need very large gains to recoup all the inefficiencies of the subsystems. So the idea is, let's try and aim for a minimum viable fusion propulsion engine. And according to these basic calculations, the performance is very similar to existing calculations for nuclear electric propulsion. So in the comparison with other rocket propulsion, the specific thrust, which is key for going fast, and the specific impulse, which is key for being fuel efficient. Ideally, of course, you want to be on the top right. So things like inertial confinement fusion is on the top right. Kelvin, showed that you can have very, very large specific powers at high specific impulse. Magneto-inertial fusion and magnetic fusion, which is direct, steady state, and self-sustained, is roughly on the middle right, which is great. But the question is, how small can you go? So in the concept where you just use electricity on board, make a short fusion pulse, and then inject it out the back, no recirculation of power or anything like that, and you have the same electrical power input, the Helicity or the fusion propulsion system is effectively an augmented electric propulsion system, and the performance is roughly similar to nuclear electric propulsion. Now, as the gains go up, so you go to larger and larger engines, you can start recirculating some of the power, absorb some of the heat, turn a turbo electric generator or direct electric conversion or something like that, make electricity to supplement the onboard electricity, the input power. At that point, you really start to get more than what you put in, and it becomes very interesting until eventually you reach the blue stage where you can recirculate all the power and it's completely self-sustained, and then you are in the top right. But the key idea for this concept is that we can scale reasonably easily from these kind of kilowatt levels of thrust power all the way to gigawatt levels of thrust power, simply with the same plasma gun, and just increase the number of plasma guns. That's really the key for the rapid development of this concept. Now, there's of course been lots and lots of different fusion concepts, and what's so different about this one? Why is it new, and why do we focus on this one? There's three reasons really. We like magnetic inertial fusion because it's roughly a Goldilocks approach in terms of confinement time versus the density of the plasma to reach the Lawson criterion. For magnetic confinement fusion, it's steady state, which by the physics definition of steady state is that the time to heat the plasma has to be much larger than the energy confinement time. So most of the input energy is lost out, and you're fighting electron confinement time. And the only way to really increase tau is to increase the size of the machine. That's, or increase the magnetic field strength and so on and so on, but effectively increase the size of the machine. So you're going vertically up at a given constant density. Inertial confinement fusion is the opposite. Basically, you don't really care about the confinement time itself. You just have to be able to compress everything on much shorter timescales. So basically, you need very, very large input powers for a given energy. And basically what you're doing is you're increasing the density to the right, so you're on the horizontal line. Magneto-inertial fusion is somewhere in the middle. You want to be able to compress roughly on some kind of energy confinement time. Now you can call it magneto-inertial or magnetized target fusion. It depends whether you're on one side of the confinement time or the other. But roughly, you're supposed to be a bit more efficient in terms of the input energy compared to the other two. Now, because of that, in principle, we have reduced reactor size and cost, reduced magnet size and cost, reduced driver size and cost. So in principle, it should be cheaper and simplified engineering. So this curve in the middle shows the fusion system, prospective fusion system cost versus the actual fusion density. And magneto-inertial fusion is somewhere along the minimum. Our concept is a little bit more dense due to physics reasons, but we're still, in principle, should be more compact and smaller and cheaper than the large state-of-the-art fusion system. Now, in terms of fusion propulsion concepts specifically, one thing we can do is compare the specific thrust power predicted by all the various concepts as a function of the density that the horizontal axis for all these three charts is density. And steady state are the black circles, pulse systems are the gray circles, and then the radius of the circle is roughly the size and the mass of the fusion concept. And you can see that the steady state ones are reasonably large, hundreds of tons to thousands of tons for the various fusion propulsion concepts. There's a couple of them that claim to, like the colliding beam FRC, claim to have tens of tons. The laser fusion ICF ones are very large, tens of thousands of tons, and they're very high densities on the right of the system. Now the pulse systems and magnetized target fusion and so on are somewhere in the middle, but they're reasonably heavy. They've got large masses. Now, one thing which is interesting is also the pulse rate, is that for ICF or a lot of magnetized target fusion concepts, they assume tens of hertz or hundreds of hertz pulse rates. In our concept, we assume about 1 hertz if it's self-sustained, to try and make it as simple as possible. It's going to be a trade-off between the pulse frequency and the amount of heat that you produce and the power, thrust power that you would get out of it. At the lower, so the green and the red values where you have very small engines and no recirculating power and so on, you're limited by the input auxiliary power charging the capacitive banks. And at that point, the pulse rate is actually very, very low. So this is the way we do the calculation. We scale up the fusion performance. There's effectively just 3 classes of engine we call small, medium, large. And effectively the fusion augmented electric propulsion system where you have some auxiliary power, you generate electricity, the plasma, and then plasma will be raised to fusion energy conditions and energy density conditions, and then converted to thrust. There's no recirculation of power. That's the simplest, if you want, fusion propulsion system you can have. That's the green curve, scaling with the number of guns, and you don't get a huge amount of fusion power because the pulse rate is reasonably low. However, you can think of it, if you put 100 kilowatt electric in, you get roughly 50-ish kilowatt thrust out, and then the rest is in radiation heat. So it's not too bad. And then you just increase the number of guns, increase the size of the engine, and then you get this N2 3/2 scaling of the power output. Now, once the power output is sufficiently large that adding extra power conversion systems is worth the extra mass, then at that point you can recirculate some of the power, and then you really start to get much more thrust out, and that shows this really steep increase in the red curves in terms of propulsive power output. The M design point effectively reflects and shows where the extra mass is worth it, basically. And then, of course, as the power conversion system recirculates, is sufficient to self-sustain the whole engine. You don't need the input power whatsoever. It's just a backup system. And at that point, you're fully self-sustained, and then we're very similar to other fusion concepts. All these calculations are done with various conservative assumptions, pragmatic assumptions, and some optimistic assumptions, which are often based on experimental data as well. These are the potential mission level figures of merit. The smallest ones are really designed to demonstrate that a fusion propulsion system can work. Is it going to be competitive with respect to state-of-the-art propulsion systems? We don't know yet, but these calculations in this project will help refine some of the subsystem numbers. The medium ones, we think that for a cislunar freight cycler would be very useful. It won't be very fast, but it can be very fuel efficient in terms of taking heavy payloads on a reusable cycling trajectories. For reasonably near-term missions. But the large and self-sustained one, of course, are the ones which will be very interesting for many high-energy missions, in particular interstellar missions. Within 100 years, the largest engine in principle could reach Alpha Centauri in a flyby mission, assuming it would accelerate non-stop. So that's really probably at the limit of what our concept could do in terms of the engine, unless we seriously optimize some of the subsystems. These are reasonably conservative numbers. Some people want to know exactly how the Helicity drive works. These are the 4 steps, so it's a 4-stroke engine if you want. We take plasmas, n number of plasmas at the beginning, merge them together under Helicity conservation and magnetic energy dissipated into heat. We form another single plasma object that is hotter. And then you compress it using this peristaltic magnetic field that I will get to and talk about as part of this project. And then you can see how the triple product scales and with a number of platinums and the various density ratios. And there's a comparison with the shear flow Z-pinch to show that we can reach similar triple products, but with less compression because of the preheating. It's pulsed operation. I want to highlight this is not a steady state, thrust system. It's really pulse magneto-inertial fusion system, which operates in the formation stage, the merging stage, the compression stage, and then the exhaust. In the exhaust, you mix it with propellant to increase the thrust and reduce the specific impulse. There is a physics basis behind all this. The plectroneme, so we talked about A, B, and C. The plectroneme was discovered in a laboratory in 2 experiments, independently and separately. The MOCHI experiment at the University of Washington and the SSX experiment at Swarthmore. The 2 key differences, SSX discovered these plexonemes first that were predicted back in the 80s theoretically as the end result of a tilting spheroMAC. A spheroMAC is tilt unstable. So you need a very close fitting walls flux conserver to be able to stabilize these spheroMACs. If you start playing with the aspect ratio and the distance of the walls to the spheroMAC will want to tilt. So most people would abandon the idea of looking at spheroMACs once it's tilted. SSX continued looking at what happened to the spheroMAC after it tilted and saw that the theoretical prediction turned out to be correct, and you get a twisted double helix rubber band instead of a single torus. But it was compact. At that point, it was self-stable, completely stable. Still had nested flux surfaces, rotational transform, and because it's tilted already, it doesn't go any further. And it has a very long aspect ratio because you can stretch now to very, very long lengths. MOCHI discovered the same thing serendipitously, this time, but without any close-fitting walls. It's really in a self-stable jet that you can think resembles an astrophysical jet coming out from an accretion disk. And we observed this double helix that confines a plasma in a very stable fashion over hundreds of Alfvén times. It's stable to the king, stable to the sausage, and all these stabilities. Reconnection heating has been experimentally observed in the laboratory for compact toruses merging together, spheroMACs, FRC, spherical tokamaks, and also SSX has measured plectoneme reconnection heating as well. And this is the database, the worldwide database of temperature, ion temperature as a function of the dissipated magnetic energy, magnetic field in these experiments. Now, MOCHI only had one plectoneme, so there's no merging, but we're building an experiment to actually test this merging with up to 4 of these plectonemes. The reconnection heating is really attractive because it's very high power. It's very efficient. And it's a direct heating of ions, and it's internal, and you don't need perfect geometry compared to things like compression heating, where you need ideally the perfect implosion. And directly heating the ions brings a lot of advantages. Now, peristaltic compression is something that Paul Bellin invented in the 70s, where you would have a tapered set of coils, and this is what we've built. And this animation that you see is the result of the code coming out from this project, actually. The advantage for this compression is compared to things like a liner compression, there's no moving parts, so you can control the pulse rate more easily. It's constant energy, so you don't have to increase the currents in the coils in a steady state set of coils with constant geometry. And it's a simplified geometry, and it's eminently suitable to a propulsion system. So of course, like any new concept, there's quite a lot of uncertainties, and we'll really talk about the physics and the details of the compression. There's also a larger program that the company is working on to be able to look at the engineering and the business side, but the physics, of course, being key. You know, we're in this phase right now, phase 1, which is building the Eclair experiment, which is subsequent to all the previous experiments and results that were done at all these various institutions that we worked in, and to bring all these concepts together. Now, the magnetic nozzle is clearly important because there's a trade-off to be done between the compression ratio that we need and the number of guns that we have. The triple product scaling here you can see, so the N triple product scaling compared to the initial triple product scales with the number of guns to the 3½ some of the reconnection specifications, and then the compression ratio raised to some power, and the compression scheme C effectively. So that's roughly the scaling of the triple product. And a lower compression ratio means that we can have a greater range of specific power, but a higher compression ratio means that we can have a lower number of input guns, basically. So that's the trade-off that we need to do. These basic calculations, of course, need more realistic considerations for the nozzle design, inductances, mutual inductances, and all these things that has been part of this project and has resulted from this. The compression scheme was published in 1979 by Paul Bellin and demonstrated on a little tabletop device that was about 50 centimeters long, maybe 100 joules of energy, just a little system that would sit on the table on the bench. Just to show, and he measured the magnetic field along the axis of this tapered set, and it compared well with that system calculation. So what we're doing basically is we want to be able to scale this to kilojoule systems, and we're building it, and then later eventually scale it all the way up to a megajoule system, and then coupling it to the actual plasma itself. There are various free parameters when in the inputs. Really, it's a number of coils that you want to choose, the radius of the coils and the shape of the tapers, the number of turns per coil, and then the compression scheme itself. That exponent raised to the power c is a choice that we can have, which determines how the coils are arranged, and you can choose them to either compress at a constant flux, a constant geometry, or a constant, effectively perpendicular temperature to parallel temperature, like in the mirror ratio, or a constant length. So that's purely a radial compression only. That's very similar to a Z-pinch, which is C equal 2. So in fact, these calculations, when we put the C equal 2 and compare it to the flow through Z-pinch compression scheme, we get exactly the same numbers that they do. So. And then the output is then the position separation of the coils. And then we get the scaling of magnetic field, the scaling of the mirror, the dips, so the hollow and the ends between the two peak, and then the volume compression ratio. At the start of the project, we were quite ambitious. We want to do a density ratio of about 100 or so, just to be able to cover our backs. Right now, we probably have to be less ambitious and go for probably a compression ratio of 40, at least 10s, factor of 10 would be ideal. The reason we had to reduce it basically is because of the voltages. To go to a density compression ratio of 100 in a very short time scale would need megavolts of voltage. We weren't too confident at operating in megavolts, so we probably have to reduce that density compression ratio. The design formalism, really, this is the key chart in terms of how to design this magnetic nozzle. These are the inputs that we have. We can choose. We can change these numbers. So we iterated many times to be able to reach these numbers that were a trade-off balance between feasibility in the lab in terms of what we want to build and the output numbers, which would be the magnetic field ratio and density ratio compared to these. The circuit characteristics are then modeled out from these input numbers, the shape of the coils, the number of the coils, the kind of field that we want. These are the equations for the circuit equations for this transmission line, effectively, including all the mutual inductances and the capacitances and resistors, and with the termination resistor, and given some kind of input pulse. So these equations effectively then output your circuit characteristics, so your time scale, your LC time scale, and then the velocity of the pulse traveling through these transmission line. And that we have to compare to our experimental results and the simulations to be able to see what kind of time scales and velocities for these pulses we need, from which we get out the capacitances that are required, the peak voltages, the peak currents, and the stored energy that we have for the given magnetic field that we want. These outputs have been iterated over a long period of time to be able to get to some numbers that we're comfortable with. So right now, 10 or 15 kilovolts is something we can build and operate in the lab with kiloamps of current, that's fine, and about 10 kilojoules of energy, which is an order of magnitude, 2 orders of magnitude greater than the tabletop device that we have. We've started to build the hardware. So this wasn't directly part of the project, but it's a great output of the project. And that we're funding internally, is to be able to build the nozzle themselves, test it, stress test it on the bench first, and then eventually integrate it into the Eclair experiment. The output is being coupled to the plasma simulations, that are being done with Los Alamos National Lab. The project with the plasma simulations has ended, but we just received a new grant from the Department of Energy to continue and expand the simulations for the next 2 years. We're including not only MHD simulations, but we're also going to go into particle and cell simulations, and then coupling the results of the output of this code, and then back and forth and iterate with these two. So this is really nice and ongoing. And it's one of the fantastic results of this project was the output was convincing, so that the DOE and peer reviewers would allow us to continue working, collaborating with Los Alamos to refine the concept. Some of the realistic considerations that the code has allowed us to look into is the effect of mutual inductance between all these coils and finite dispersion effects in this realistic system, which we assume the scaling of the magnetic field with axial position under compression as a WKB scaling, but of course the simulations go back there.
3 minutes, Seth. Sorry.
Oh, sure. Oh, wow. Maybe I should speak faster like Kevin does. Yeah, so you can see that basically, depending on the type of input pulse, the width and the separation and the timing and the amplitude and so on, for realistic mutual inductances, clearly you can see that the outputting magnetic field is not as great as maybe factor of 10 lower than the WKB projections. But this code really allows us to be able to design and iteratively design the electrical systems to try and see which system we want. We've already started fabricating. We've settled in on the design of the coils, and literally started building and cutting and assembling the coils and doing test assemblies and so on. Right now, not in vacuum yet, but these coils will go into vacuum. The support structures like these brackets and then the arms, rails will be modified. Right now they're just plywood. But at the moment, we come across some issues, typical of any fabrication. Things like ceramic washers break, like 1 out of 10 ceramic washers break. So we have to make sure we're more reliable in doing that. These copper coils are designed to be bitter designed to be able to take some of the large fields on a short time scale, but they can warp sometimes, especially the large ones. So we have to redesign them with more fixes. And then some of these 3D printed H brackets, they break. So we're doing the PLA and higher inlet density. When we assemble them all together, it looks fantastic, because this is eventually what will go into our vacuum chamber. And then we'll be able to shoot the plasma through it and then observe this compression through that. And this is really, the length of it is about 60 centimeters. No, sorry, about a meter long. The total mass is about 6 kilos. The total energy we're putting in is about 9-10 kilojoules. So the specific mass is about 0.7 kilograms per kilojoule, which actually compares well to all the specific power calculations that we did earlier, the back of the envelope calculations we did earlier, where we estimated about a kilogram per kilojoule for these coils, all the way up to the large and extra large fusion, self-sustained fusion propulsion system. This is literally what we're building. This CAD drawing and rendering is literally based on the engineering drawings of the systems and subsystems, the vacuum chambers, and everything that we're going to be putting into this. It's actually under construction. We're as you see in the coils, this will be made in a private company, and we're going to be assembling all this and putting it together and hoping for first plasma this time next year. We're coupling to plasma simulations. These are the preliminary ideal MHD simulations to be able to show these plasma jets coming out, merging together within this coil system and then coupling into the coil designs. These were the simulations just to overlay roughly what it looks like, and then we're actually in the middle of designing the double pulse drivers. There's two ways of doing it, either as a pulse forming network or two separate capacitor banks that we're going to fire separately. They have advantages and disadvantages, each of them. We're going to build a bench test version first of both designs, literally test it, and even with a waveform generator to be able to control these input pulse shapes. So the project is really successful and moving towards this Eclair experiment. We built these realistic codes. We started to build hardware. These results really helped us close some fundraising for building the Eclair experiment and obtain this new DOE grant for continuing expanding the simulation for Los Alamos. There's been issues that we've been working on, mechanical and electrical ones, and we're working on those and addressing them one by one. It's been a revelation. We're writing up the manuscripts for submission to peer-reviewed journals and documenting everything into a final report. The successful collaboration between HelicitySpace, Caltech, and UNBC is continued now with internal funding to finish this fabrication, finish the simulations, and integrate it with Eclair. So with that, thank you very much, and hopefully we'll be able to profit from these unprecedented benefits of the concept. Thank you.
Hey, thank you, Seth. Fantastic job on the presentation. Before you stop sharing, could you go back to slide 22?
Sure.
Just wanted to give you an opportunity to show the people the amazing animation there, and just go ahead and press play. It's a thing of beauty.
So this is really preliminary. We're still working on the simulations and coupling it to the plasmas, and some, it goes unstable at the end. So that's one thing that we have to look at. It's stable at the beginning up to about there, and then once it merges, it goes unstable.
This is what you got from the LANL code, right?
Correct. Yes, this is a simulation of the Los Alamos code, MHD simulation.
Awesome. Cool. Yeah. Thank you for that. I just wanted to check that, and then I would, on the lighter note, I'd like to encourage you to build on your acronym legacy of using the acronym Eclair. I would Eclair. I think you should have scone or fritter as one of your future iterations. So find some way to work that into.
We'll try and keep that in mind. Yeah, absolutely. A dessert-based fusion propulsion system.
Right. So okay, you can just stop sharing your screen. We can open it up to questions.
Eclair also means lightning in French.
Ah, okay, all right. I'm just taking the savage American interpretation of it. You have a much more noble view of it, right? I'm like, well, why don't we use fritter? That sounds like a good acronym.
Well, it does look like an Eclair as well, because it's like the soft parts are surrounded by the.
Right. Good stuff. What kind of questions we got from the panelists? While they're thinking, I do have one. Piero, sorry, Mr. Chan, go ahead, sir. You got to unmute yourself.
I have just a small question, short one. May I?
Oh, yes, go ahead.
May I?
You go ahead and ask your question, yes.
Yes, now in the previous talk, Kelvin's pointed out the physical principles of the absence of the scaling variance is very important. So then you showed us a model 15 centimeter long, right? Am I right? Or something like that at the given point, one of the slides. So my overall questions, are there critical length scales of your device, or a minimal or a maximal for it to work? Because your calculation estimates will depend on critical length scales, depending on the intensity of the fields. So the state, the stability of the plasma state, I think does depend on these length scales. So your device has to be between an upper and lower length scale, I assume. So just to have an idea, so what do we expect concretely? Because you have also a picture with a human.
I think you broke up.
I think we lost Piero there. Could you glean what he was saying and answer the question? Otherwise, we'll just go on to the next one.
Sure. So it's a great question. So the question is about length scales, and in terms, what is the impact of the length scales on the concept and the scaling up to a fusion system? So it's a great question. Now, from an MHD point of view, as long as you fit the dimensionless numbers, you can scale it up. But in a realistic system, length scales become very important. Now, in this case here, we rely on helicity conservation principles, where the dimensions are critical. So in this case here, the plectroneme shape of the plasma, the double helix, is very similar to a Taylor state. It is a Taylor state, in fact. It's like a spheromac and so on. And it all depends on the aspect ratio of your volume, the cylindrical volume that surrounds the plasma. And that cylindrical aspect ratio has to be larger, an aspect ratio larger than 1.67, effectively. If that cylindrical aspect ratio is longer, we have the plectronemic Taylor state. If it's shorter than 1.67, then a spheromac is a minimum energy state. So then you get back into a torus situation, which is why there was that transition. If a spheromac is left on its own, i.e. the aspect ratio is larger than 1.67, then the spheromac will tilt because it wants to go to a lower energy state. And that low energy state is then confined in the cylinder to be a double helix, effectively. Now, let's work backwards from a fusion, magneto-inertial fusion system. At the most compressed state, which is the smallest plasma possible, we still want it to be a plectroneme. Therefore, that aspect ratio has to be 1.67 or larger. That's what we start off from. And then what we do is then that has to be a fusion system, a fusion energy conditions, and then you expand it out. So this is the magnetic compression system, and expand it out back to the plasma guns at the formation region. And the formation region is based on our experimental result, our past experimental results. In our past experimental results, we formed a 1 meter long plasma that had a plectroneme inside it with an aspect ratio of about 25:1. We've also done that with an aspect ratio of 3:1. So we know that at least between 3:1 and 25:1, we can get these plectronemes. And the idea is we want to be able to compress it and still remain a plectroneme. That's why we still have this scaling effect all the way up to fusion conditions. But that's a constraint that we work with.
Great answer, Seth. I think next up we have Phil Lubin, and then hopefully if we have time, we can get a question. I think Roman's the last one in the queue. So, Phil.
Yeah, quick question. Really interesting talk. Have you or Los Alamos analyzed the instabilities you expect in the nozzle? I saw the ones outside, but in the nozzle. And then second question is, what is the private sector interest in this? Is it space or is it power or other?
So for the first part of the question, we are not there yet in terms of looking at the stability inside the nozzle. That would definitely be a major effort on our part. There's the stability. So there's two aspects to that stability. There's a self-stability, because these plasma jets that we formed are self-stabilized. They're a bit like a Z-pinch or a screw pinch that is self-stable through the kink and sausage instabilities because of helical shear flows that are being generated. So that was experimentally observed, predicted, and it worked. And we get these stable jets that are radially balanced. So there's got to be a self-pinch to compensate for the radial pressure balance. And that somehow is very stable. And as we add more current, basically the whole thing should compress down, just like a Z-pinch, effectively compress down to higher densities. Then when we add the extra external fields, the impact, now the external fields are much slower than alpha n timescale, much slower. So in principle, because the external field is reasonably symmetric because of the coil designs, it should act effectively as a magnetic wall, magnetic flux conserver. So the plasma should be reasonably stable. But that remains to be seen, and the simulations will start to inform. And then next year, once we get the first plasmas, we'll be able to address that directly. To get to your second question, the private interest we've seen has been pretty good, actually. Primarily, we've been aiming for the propulsion market, precisely because compared to other companies and other concepts that address the energy market. So the energy market is huge. Everyone knows that. It's the world's #1 market. And fusion would be a great answer for that. But there are many companies working on it, and all these companies to do fusion will need to get to very large gates before even being able to commercialize the concept. We flipped it around by saying that for a propulsion system, we design something for a propulsion system first. Even at low gains, we can start selling an engine earlier, compared to waiting until we get huge gains to be able to turn it into a power plant. And the requirements are a little bit different, and the advantages and disadvantages of putting it in space and doing on Earth is a little bit different. It taps in also into this fantastic new space race that's happening right now. And we want to be able to provide a potential solution for propulsion system, in the next decades, to be able to say, hey, a fusion propulsion system, we all know is the answer, whether it's ours or whether it's an inertial confinement system and so on. But let's work on it today, get a minimum viable product up there, and see where we go from there. The first jet engines, only lasted half an hour before they blew up, basically. But it worked and it showed the promise, and now we can cross the ocean that way. So people are very excited by that, and I think the private interest is just growing.
Hey, Seth, thank you for that awesome comparison there, right? Reminder of previous technologies in terms of how they climbed the maturity hill, if you will. Roman, I'm going to have to apologize. I'm going to have to press on a little bit. If you could type your question in the comment section, and then Seth can address that. Seth, you have two other questions in the comment section, one from Sumantro and one from Bill Studak. If you just maybe type in some answers if you want, and make sure it's available for everybody to see, so they can, people can benefit from the answer. So with that, I think I need to go ahead and press on to the next presentation we have, and this is the last presentation before we do our lunch break. So next up we have Remo Garattini from University of Bergamo. He's going to be talking to us about traversable wormholes. He's been doing some very interesting work in partnership with Piero Nicolini. And Piero, I noticed you had problems with the audio. If there's going to be a point where you talk, maybe turn your camera off. That may help with the bandwidth. That's a trick sometimes that works. So with that, Remo, I'm going to hand it over to you if you want to share your charts, and I'm going to go off video.
Can you see it?
Yes, I see it.
Okay, fine. And now, okay. Can you see also the whole screen, the complete slide?
You are in presentation mode. Yes.
Okay, fine. Okay, thank you, Sonny, for this third meeting. And now, my purpose of this talk is to present the progress we have done from the beginning to this last part of this adventure. And so for many of you, there are a lot of slides that are been presented before, also in the first and in the middle term meeting. So I apologize for you, but I have to present for everybody. Maybe it wasn't that was not presented to the other two sessions. So indeed, for the first one, maybe Kelvin will recognize exactly this one. I borrowed from the BIS of November 2007, so with the old data, but it is very interesting also to see what I have in mind. I mean, if the target of this project is to go into the deep space, we have to face with the problem of the speed of light, and of the limit of the chemical propulsion. So as you can see, unless you have something very, very specific, like this part, I mean, pure photon rocket, fusion matter, antimatter, negative matter, and so on. This is for the very, very far future. you are more or less here in this part of the project. Okay, there is something here, but this is not available for human transportation. So the problem is concentrated also. Every problem is concentrated here. Although we have a speed of light as a barrier. So this is a very important constraint to go into the deep space. So the problem is that in which way can we go on to overpass this problem? Okay, one proposal is a traversable wormhole that I'm interested in. Another proposal could be the warp drive. This is not in this project, but it is in my interest, of course, because there is one point in common that I will describe later. So let's begin with the definition of traversable wormhole. Traversable wormhole is a connection, if you want, between two distant parts of the same universe, or if you want, you can cross one universe and you arrive into another one. But let's stay in our universe. That it is very, very interesting to stay here. So a wormhole is a shortcut, and if you cross the wormhole, you have the ability to cross and to reach far distance points into the universe without violating the barrier of the speed of light. This is very interesting. So the problem is that how can we build a traversable wormhole? Does it exist? And which kind of equations we have to solve? One example is given by the Schwarzschild wormhole. And the Schwarzschild wormhole is the very simple worm, but the problem is that it is not traversable. And so we need to do something more to have a traversable wormhole. One prerogative of the wormhole is that you need negative energy, and this is obtained by solving exactly the Einstein field equations in an orthonormal frame. And if you solve the first equation, what you obtain is that exactly you can extract the geometry of your space, and solving the first equation, you can have the form. Indeed, this function, when you find this function, you can find the shape, the so-called shape function. So how the space is curved. There is another very important equation to be solved. This is the redshift function, and gives you exactly the delay in time from one station to the other station, from one observer and the other observer. And last but not least, there is also another equation connecting the tension, but this is nothing but the opposite of the radial pressure that I prefer to use here. And finally, there is a conservation equation. When you solve these three equations, you can have information about your traversable wormhole. The previous equation is it's built by means of this line element. This line element is the fundamental point to begin to study traversable wormhole, and you have some properties to satisfy. These properties are the asymptotic flatness and for the shape function in the, if you want, upper and lower universe. I mean, for this exactly here, you are here in the upper universe, or here in the lower universe. There is if you want a transition from the upper to the lower in this way. Note that for a traversable wormhole, there is no preferred way to cross it. So you can go also in the reverse mode. Very different from a black hole, for example. Well, oh, sorry. Okay. Well, a very simple example is this one. You have a constant one, redshift function, is a constant throat. This is very similar to the Schwarzschild throat. And this is a traversable wormhole. There is one particular point that even if this is a traversable wormhole, the average null energy condition, that is a measure of how much negative energy you need to have a stable traversable wormhole, goes to infinity. So even if this is a very simple traversable wormhole, you cannot use it to cross the universe. So we have to use other models. Another very famous model is this one. This is presented in the pioneering paper of Morris and Thorne. Also, this is has been found by a solution from Ellis and also from Bronikov. Indeed, this is also known as Ellis-Bronikov traversable wormhole. It mimics, if you want, a flat space in spherical coordinates, except from the presence of a minimal length. So when L go to 0, you have you obtain only a sphere, because this is the element of the three-dimensional sphere. So in Schwarzschild coordinates, you can translate from these coordinates to the usual Schwarzschild coordinates, and you obtain here the same metric but in a different expression. And the throat condition is satisfied. This is an essential point to have a traversable wormhole. Well, there are some features of this wormhole. This is known also as zero mass wormhole. The proper mass, so the mass divided by the proper length, is not 0, but it depends on the part of the universe you are. And so the total energy, so that the difference between the mass, the global mass, and the proper mass is finite and is not 0. You can also calculate a proper length, and also you can calculate also the radial pressure and the transverse pressure to obtain all the information you need to build this wormhole. The problem is that you need exotic energy. Exotic energy in nature does not exist, except for one for one example. This is the Casimir energy found theoretically by Andrew Casimir in a calculation for 0-point energy in QED. And the physical situation is very simple to understand. In flat space without boundaries, you have all the wavelengths that fill the space. If you put a boundary, so inside the boundary there are less less modes inside than outside. So the effect of the radiation from the outside is to push the boundary together, and so you can have a problem, an attractive result. Indeed, when you do the calculation, you can find that the energy density is negative, and so this can be used as a source for exotic matter, because you have also always the equivalence between mass and energy by means of the Einstein relationship E = mc square, very famous. And so you have a potential source that you can use from the laboratory. But the problem is that this is very tiny. So as you can see, if you try to put some numbers, you have something that is very, very small. But anyway, this is a source, and we can use it, and we can we can try to use it, and we can try to think at the source more seriously. In which way? For example, we can try to solve the semi-classical Einstein field equation. So you have a stress energy tensor renormalized, in the sense that you deal with this tensor coming from matter fields, for example, photons, scalar fields, fermions, and so on. You use the quantum field theory tools to take under control the divergences, and so you obtain some finite results that you use as a source. Then, for example, if you try to use the usual result of the Casimir energy, that is negative here, you have also a result on the pressure, radial pressure, and on transverse pressure. What you obtain is a wormholes, but that is not traversable in principle, if you think that this is the shape function that you can extract. Anyway, this is not the whole story, because if you try to think that your energy density is not fixed, like here the A is treated like a parameter, and and this measure the distances of the plates fixed, or not dependent on the radius. If you allow that this distance is moving, so is a variable, now you can find something different. Because if you use an equational state that relates the wormhole throat with this fundamental length, that is measured by this quantity, and this is a Planck length at its square, you obtain a very interesting solution for omega = 3, and you obtain a general solution, a new, if you want, solution that is a mixture, if you want, or a superposition between a constant throat and something that is similar to the Ellis-Brunico wormhole. And for the special value of omega = 3, you obtain this one with the corresponding stress energy tensor. Well, you can calculate, for example, many special things, like the proper radial distance. You can try to estimate some possibility of travel between two distant stations, like in reference. Sorry, it is a reference 9. I mean, Morris Thorne, American Journal of Physics. Well, if you put some numbers, you find that, for example, there is no difference between the proper time and the time observed by another observer. And, for example, to cross the distance between the two stations located at this point, you obtain a total amount of time of this size. Okay, this is very interesting. a possible generalization of the previous result has been done in the generalized absurdly benign traversable wormhole. And what is obtained here is that we use the Casimir source once again, but at fixed distant plates. And we can see that for a plate separation of nanometers, you obtain a throat that is very huge. So if from one sense the previous result gives you a solution interesting, but it is very small, it is Planckian, because there is 3 here, and this is the ratio between the throat and the Planckian size. On this side, we find something that is very huge. So we are on the opposite side. So we need something that can be fine-tuned. And this is the purpose of the whole research of this year. And my purposes at the beginning was also to use many sources like the squeeze state, metamaterials, and so on. This part, for this to this purpose, I at the end of this or the conclusion, I will spend some words about this because this is important if I will have time. Well, note also that all this kind of investigation is valid also for the warp drive, because a warp drive needs an exotic source. So if we have success in this direction, we have success also for the warp drive. Fine. So the intermediate target we have produced is another paper and another more formal, but this is also important in collaboration with Piero, who is here with us. And this is necessary to have consistency from the formal point of the study of the eigenvalues of this operator that are fundamental in the quantum correction. From the Yukawa-Casimir point of view, I have to say that the Yukawa is a potential that proposed by Yukawa itself, but it is necessary to describe non-relativistic strong interactions between nucleons. So it is a very short potential, the short distance potential. And it is also interesting because this is can be used to see deviation from the Newton potential. This is also investigated in deviation on the Casimir effect if some, for example, Yukawa modification comes into play even at the Casimir level. This kind of potential has been investigated earlier here in this. It was a communication at in the conference, but now this has been published here in European Physical Journal C. And what we have studied is a modification of, for example, of the Alice-Bronico wormhole by means of a Yukawa damping factor. In this way, with this limit, we can recover exactly this kind of wormhole, but the same has been done also for the Casimir wormhole. Indeed, I can skip this because this has been presented. These are only some properties of this kind of Yukawa wormhole, but I'm interested to present these forms that are modification exactly of the original Casimir wormhole by a Yukawa factor in different position, and you obtain different results for 3 profiles of this. Note that if we want something that is at the order of 10 to the 11 meters, we need a plot separation of picometers. It's very small. We can use an equation of state to avoid to calculate the redshift function, and what we obtain is that the redshift function can be put to 0 if the equation of state function is of this form. For example, for the profile 3, we have a divergent solution with very large R, and so we have to discard this kind of solution. We can also think to have a superposition of this, but the result at the end is seems to be the same, very huge. So you need something that is not useful in practice, also very can be created also in principle, only in principle. Well, this is not the whole history, because we can do also the reverse procedure, and we can think that the energy density is a mixture of 2 Yukawa profiles, and if you can find here, to have the correct properties, if alpha is set to this point, to this value, we can have a finite value for R very large. We can set a 0 redshift function, and the shape function is a mixture, if you want, of these 2 energy densities. And what is interesting is that at the end, if you want to have something that can be used, you have a mixture of attractive and repulsive potential. This is not very unusual, because if you can fine tune the potential that appear in this kind of proposal, you can find that that can be used to have the correct size. Indeed, if we force to have a value that at the throat is comparable to 1, for example, to 1 or 3, it doesn't matter, but to a finite value, without a proper choice of the parameters, you have always this kind of throat. But if you see that this kind of function rescaled in this way must be constrained to 1, well, the things are different, because the throat can be fine-tuned to a smaller value. Indeed, it is sufficient that this quantity approaches 0, vanishes, and then this throat can be smaller. So in a sense, you can fine-tune the parameters. And this is 1.1 result. The other result comes from the including the quantum fluctuation. This is the idea. When you have a source, for example, the Casimir wormhole, the Ellis-Bronikov, well, you can find you can see what happens to the quantum fluctuations. Well, you need to study the Schneerowitz operator that comes into play when you introduce a quantum fluctuation. And what we did, me and Piero, is to show that this kind of operator is consistent only in a weak sense, but it is useful. It is enough to have a correct eigenvalue problem well set up. Fine, this is good because in this way we have the possibility to find the eigenvalue, so we have the possibility to insist in this direction and to see what happens when to the old classical solutions we introduce also the quantum fluctuation. So this is the work in progress. This is of this last period. So the idea is to introduce in the original Casimir source
Remo,
also the quantum. Yes.
3-minute warning.
Sorry, what?
3-minute warning.
Okay, okay, enough. So we introduced the Casimir quantum correction to the Casimir source, and this is the form. And what we obtain is that we have an effective shape function that takes into account also to the quantum source. The problem is that this depends on one point, the renormalization point. What we obtain is this. Note that if we fix the renormalization point to this value, we have the possibility of having very large throat. And I draw your attention that we started for the Casimir wormhole from very small Planckian throat. So this is very interesting because quantum fluctuation seems to help to have to modulate, to have a better throat at the final level. Of course, this must to be compared with other regularization, renormalization process to see if we have this behavior even for other processes. Well, the same procedure can be done also with the D treated as a constant, and in this framework it is possible to have also the quantum correction concentrated close to the throat, so we have another constant, and this is what we are going to do. And even if the shape function is divergent like the original one in a cubic way, this is not a problem because we can use the generalized observed benign traversable wormhole technique to have a cutoff at a certain point and to have finite results. Well, my team is very simple, is myself and Piero, and the idea was to apply this final work in progress also to the other profile. A simple word on this, on metamaterials. So there is a very large, I say a huge literature on this argument, but the problem is to find two arguments that are combined with the Casimir energy, and there are. What is interesting, and I did some calculation in this direction. I prefer to not present here because they are very preliminary, and it seems that metamaterials can be used to have an enhancement, so a modulation, a real modulation for having a throat that can be traversable. And even if this project for the LSI is now approaching to an end, I'm going to insist in this direction because I'm very curious to see what happens. And I hope to convince also Piero to stay with me for just a little bit and see what happens also for this kind of situation. Now, I would like to thank the LSI for this grant, and in any case, thank you very much for your attention. And as usual, I prefer to end in this way. This is my outlook. Always, always.
Fantastic, Remo. Fantastic.
Okay.
Great presentation. Always pushing my math skills and making me go back and remember all my general relativity. So thank you for that. I do want to say you had an acronym in there, the GABTW, right?
Yes, it's generalized absurdly benign traversable wormhole. Otherwise, you have a very long outside of the screen.
Yeah, I want to challenge you to make that acronym something like some kind of a dessert, right? Seth already has eclair worked into his, so find some kind of acronym that works a dessert that factors all that in, right? So anyway, sorry. Great presentation. Any questions from the panelists? And if you could stop sharing, Remo, that'd be great.
Yeah, I had a quick question. Remo, I won't claim to have understood it all. You've gone beyond me, I'm afraid. There's a slide you had where you said the two terms were the same. I'm just trying to find the slide.
Yeah. Let me.
I didn't see that they were the same.
Yeah. Here, this one.
Yeah, because one's got an e to the 5 in the numerator.
Yeah, you can do the calculation. The interesting point is that if you do the calculation exactly, you can see the difference is here. There is no. Yes, the difference is here, more or less. Is this numerical factor is due exactly from this point. Comes from here.
Okay, you factored it in when you've.
Is
that an expansion? I'm not sure what you've done, but yeah.
This one is.
It was fire potential.
Is this one?
Okay.
This, the phi of r is this one with the omega equal to 3.
Mm-hmm.
You put there and then you integrate. I did this with Maple.
Yeah.
And you obtain the result. And this is based about if you want to see better, this is related to the proper radial distance calculated here. The main integral is this one.
But you were saying there was no difference between the time and the proper time.
Exactly. There is it is more or less not difference. Okay. It is approximately equal because 1/4 and 1/3 are not so much different.
Okay. Yeah.
Awesome. I think we had a hand raised from Tom McGuire. I think I saw earlier. Tom, I've got you allowed to talk if you want to unmute and ask your question. In the meantime, there you go, Tom, go ahead.
No, yes, I mean, I don't think you probably missaw it, but thanks for the shout out. Great presentation. Lots to absorb. Thanks.
All right. Thanks, Tom. There was a question from Rob Adams. What is the significance of assuming omega equal to 3?
Yeah, this is very important assumption, and this is due to this point. Look at the stress energy tensor of the original Casimir calculation. The ratio between the energy density and the tension, or if you want the radial pressure, is exactly 3. So if you satisfy this ratio that is satisfied exactly here with omega equal to 3, you are really using something very, very close to the original Casimir source. Not only because in the literature, if you try to find something, there is first of all, except of this calculation, there is nothing. And usually people say, okay, there is the Casimir effect. So, okay, the Casimir effect produces what? In this case, I've done this calculation, and this calculation, if we want to have a connection with the original Casimir source that has this structure of the stress energy tensor, we need to have omega equal to 3. Otherwise, we are doing something else. So omega equal to 3 is a physical constraint, if you want, really physical. But the goal target could be exactly to have also the other part of the stress tensor confirmed. If you find here the calculation, you have something different. There is something that, but maybe there is an explanation, because it is likely that this effect is due to the curvature. What we have included in this calculation, because we are using something that is changing with the radial distance, is not fixed. And so there is something we are no more in flat space. That's the real reason. And this curvature has a price here.
Cool, awesome. Thank you, Remo. I think so. It's 12:22. If there's any more questions, people can feel free to put them in the text windows, and we'll be trying to keep track of those as we continue to move forward. I want to go ahead and shift gears here. Thank you again, Remo. Fantastic talk. Love it. Awesome. Appreciate it. We're going to go into our virtual lunch break. It's not going to be the full 45 minutes. I apologize. I'll give us until 1 o'clock. Originally, it was supposed to be until 12:55 Central Time. I'll stretch it to 1 o'clock. Reid Wiseman will be here as our keynote after the lunch. And so we'll get a great opportunity to get some awesome comments from him. Looking forward to that. And then we've got, for everyone that's online, when we reconvene basically at 1 o'clock Central Daylight Time, we'll have our keynote, and then we'll have our 4 remaining performers talk, 2 and 2 with a 20-ish minute break in the middle. So I'm going to go ahead and put up the splash screen so people can see that we're still here, but we're on break. Feel free to mute your computers and turn off your screens, and then we'll reconvene. I'll probably bring the loops up just a few minutes early in case anybody wants to chit chat before we get started. But great job, everybody. Great morning session. Awesome. Looking forward to the second half of the day. Hopefully everybody can go grab some nom noms. So, or an eclair. Grab an eclair.
Sonny, I have to jump to home because my institute closed, and so maybe I will be just a little bit in delay for the second part. Okay. But I will be.
Copy. Use wormhole.
Okay. Bye.
Let's see you.
Bye.
Sonny, quick question for you.
Yes, sir.
Yeah. You want us to stick to 20 plus 10? Because it looks like you're going 30 plus 10.
Yeah, everything in the schedule is 30 plus 10.
Okay, great. Thanks.
So for you, that means it's 50 plus 10, right?
Talk fast.
Right. Yeah, I was going to say, Kelvin set the high water mark, man.
I know. Yeah, I was.
72 charge. What was in that tea, Kelvin?
It did go incredibly fast.
Yeah, right. You did that. Go incredibly fast.
Hey, Sonny, you've all logged in as a participant rather than a panelist. Is there a way you guys can switch him? I sent him an email, but
yeah, I certainly can.
I'm gonna grab some dinner.
Attendees.
Yeah, he might just be logged in but not present at the moment.
Okay, I promoted him to a panelist.
All right.
So
great, thank you.
Let me make sure he's in the list here. So Yuval is now as a panelist. Yuval, you want to test your microphone and camera?
Yeah, he might be off.
Okay, just let him know he's been promoted to panelist.
Okay.
And if that doesn't work, we can send another email invitation thing later. But he's in there now. So
all right, great. Thanks, Sonny.
All right, thank you. And Richard, I see you're still with us. So no phone call that the baby's coming right now. Come meet me, right? So
we're all good here. Gonna do dinner.
Okay. All right. Awesome. For everybody online, we're going to step away for just a few minutes. As I said, we'll be back at 1 o'clock for the afternoon session. So be right back. For everybody online, we're actually not back from lunch yet. We're just doing a quick technical test in preparation for our presentation right after lunch. Fro, go ahead and run your test.
All right, let me run this test real quick. Share screen. We're gonna share screen 2. I'm gonna say share. And then I'm gonna do this full screen. Now I'm gonna reduce this. That's
I got the presentation. I see the big slide.
all righty, sir. Give me one sec. Right there. That's what I want. Oh, this is usually what you do, Sunny, on when we have our tag ups, correct?
What's that?
You put like the view on the right hand side to the right.
Yeah, and I as the viewer, when I'm looking at you showing slides, I do not see that zoom thumbnail thing that kind of appears over your slide. The only thing that gets streamed to YouTube is the PowerPoint with your thumbnail on the top right. So in other words, the speaker's camera gets embedded on the top right.
Understood. All right, so are you able to see the first slide there?
Yes, I got it.
All right. All righty, so I think we're a go.
All right, man, cool.
Thank you, sir.
Am I going to put back up the other slide now?
Yes, sir, please.
All right, everybody online, thank you for letting us do the test. Sorry for the interruption. Back to lunch.
Oh, perfect.
Don't forget to unshare your screen, Fro. Hey, Fro.
Yes, sir, I got it right here. Sorry about that.
Share and mute.
Unshare and mute. Stop video.
All righty, just a couple more minutes and we'll get started here in just a second. Hey, Kelvin.
Oh, hey, Sonny. So, how's it going?
Going pretty good. It's going pretty good. Reid is here in the building now. They're getting him set up over in the other room.
Okay, good.
We'll get started with him in just a minute.
Cool.
Great job on your talk, man. 72 slides. Woof. I was like, man, that's awesome. And it was not like you were just next slide, next slide. You were digging into each one of those things. I was trying to keep up. It's like, he's challenging me. I have to keep up.
I'd like to have explained them and so forth, but you know, I'm not proud of it. I think it was. We have a word for it in the army, but I won't say it on the.
This is being recorded for all posterity.
Poor performance, blah 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 blah. Whatever.
I thought it was good. I liked it. Right. I think you did a great job. And you know, the whole little speed bump with electronics, right? That stuff just kind of happens, right? You know, it's,
absolutely. I'm not sure if I showed you this. I've got it in a frame.
Yes, you have, and I am so green with jealousy. That is absolutely outstanding. I love that.
Gene
That
Rodenberg.
is fantastic. So, hey, John.
Hey, how are you?
Oh, doing pretty good. Doing pretty good. If Adam's going to present during yours, I muted him during the lunch break. He was, I think he was off doing some stuff and didn't realize his microphone was open and he was singing for us. So I figured I would put him on.
What the heck? Honestly, I made sure that I was muted. Are you sure about that?
I'm so sure, man. I was like, yeah. All right, come on, Adam.
I had to nip into MIT myself over the lunch break, so and attend to talk, but I'm back, so back on time, and we're starting in just a couple minutes, right?
Yeah, just a couple minutes. Yeah. We'll get back to it.
I guess you guys reset everything, and so the mutes came off or something because I was muted. I muted myself. That's funny.
I'm so paranoid about that. I'll check that mute button 100 million times, man. I remember back in the dawn of the internet meetings in the early 2000s. We were meeting with some colleagues, international colleagues. I'm just going to just keep it generic, right? International colleagues at Lockheed Martin. And so we're going through this presentation. And so we're dialed in via phone, and then we're getting material through the computer, like presentation material through the computer. And so we're going through this stuff, and our international partners were talking to us about a contentious subject. And some of the people on our team didn't necessarily agree with them. And so they made some comments about, do you believe just, some, because all the phones were on mute. Well, as it turns out, the desktops that we had, they had microphones inside the box.
Right.
That no one knew about. And so I'm sitting there and I hear somebody make this remark and I hear it on my computer and I'm like, dude, they can hear you. And you hear, did somebody have a comment?
Oh, man.
Tactical error.
Yeah.
So,
Hey, Sonny, did you guys watch the William Shatner launch yesterday?
I watched it afterwards. I did not get a chance to watch it.
Did you listen to his little, when Jeff Bezos eventually stopped the nonsense with the champagne, just listen to what he had to say?
Right,
it was amazing.
Right. Yeah, it was really cool. I did.
And he was talking about going from life to death and, just incredible.
Absolutely.
Hey, Kelvin, I listened to, I even had to go back on YouTube and play it again. That was like, he took all 6 months that I spent in space and he just encapsulated it down into just a few cheery sentences, and it was melting my heart. I just thought that was amazing.
It was so natural
as well.
In the moment. It was brilliant.
I saw it, and it's incredible to see how emotional he was.
Yeah. So proud of him.
That's really neat to see that, right? And absolutely amazing. So now, I guess now that we got Reid here, the amazing Captain Reid Wiseman. Welcome everybody back from the break. This is going to be the afternoon session of the Interstellar Initiative grants. We have another treat for you. We've got Reid Wiseman's going to talk to us today about some of his experiences in space. Let me tell you just a little bit about Reid before we get started. He's a captain in the U.S. Navy. He got an opportunity to fly F-14 Tomcats, so I am absolutely positively green with envy. I have to say, I would speculate that Tom Cruise wants to be Reid Wiseman when he grows up. Reid did 2 deployments to the Middle East in 2003. He became a test pilot, worked on programs such as the F-35 Lightning, F-18, P-45 Goshawk. He spent some time with the Strike Fighter Squadron 103, where he got a chance to fly the F-18F Super Hornet. In 2009, NASA wisely chose him as an amazing astronaut. And then in 2014, he got to serve as a flight engineer on the International Space Station for Expedition 41. I think he also really did a good job of trying to communicate through social media about what that experience was like. And I got to think, for somebody that's a military person, a pilot, that was probably a little bit of muscle memory they weren't used to. So kudos for trying to go through and share that kind of experiential thing. He commanded Nemo 21, the Aquarius Reef Habitat. And then of course, he currently serves as the chief of the astronaut office. So as if all those other accomplishments didn't make you feel this big, which it makes me feel this big, let's just go ahead and pound that dirt flat, right? So he's got a Bachelor of Science in Computer and Systems Engineering, a Master's of Science in System Engineering. And we also love him here at Limitless Space Institute because he's on our board of advisors. So Reid, so happy you got a chance to come chat with us today. We're going to hand you the microphone and you can take it away. I'm going to go on mute and remove my video and just we're just going to sit here and enjoy.
All right, thanks, Sonny. My goal here, and no, you all can turn your cameras off if you want and just sit back and relax. I just spent about 20 minutes with Sonny and I need a nap. The things that are going on out there that everyone is doing are just blowing my mind. There will be no equations in this presentation. My goal was just to be pretty lighthearted and just take a quick snapshot as kind of where we are in human spaceflight. And y'all were already touching on William Shatner. And so I want to take a pause for 20 or 30 minutes as we're talking about sending humans further than we could ever even imagine and solving energy problems around our own world with the work you all are doing, and just take a look at where we are in 2021. So I'm going to start with a very quick video that we're located. Limitless Space right now is just outside the gates of Johnson Space Center. I don't know how many of you have been here. And just going to take a quick 3-minute video of what's going on at Johnson Space Center, kind of a look back and what we're doing right now. And then I'll talk about a few things that I want to hit on.
Real quick, before you share, make sure you click the share sound. Fro should know that, just making sure.
All right, I will highlight share sound. Fro is right here. And then Fro, which one do I want to share? Screen 2. Fro worked with me for 12 years. So it's like being back home with Fro here.
We stole Fro.
Presentation. What would we do without Fro? Okay, let's see if this plays. All right, so I'm going to keep sharing my screen. Let me see. Maybe I've made it start over. Okay, so let's just look at 2021. Every time I do a talk these days, people I think mistake the 1960s for the golden age of human spaceflight, and I really want everybody listening, if you just got a chance when you're talking about where we're going in human spaceflight, let's just take a look at 2021. Most of you probably already know the story of this year, but to me, it's worth pausing for a second as humans on this planet and just taking a look at what we've done. I'm going to start in April of 2021. There were more human launches and landings than ever before in that month in the history of humanity. So we have 2 Russians and an American, Mark Vandehei, over in Russia. There's their Soyuz launch in the far background, launching from the Baikonur Cosmodrome. We also brought Kate Rubins back to Earth. You saw her in that video a couple of times. She is a infectious disease scientist who was studying Ebola virus when we hired her. That was her second space flight. And then really fun for me was launching the second crewed flight. You all got to talk or got to listen to Victor Glover this morning. He was on our first long duration SpaceX flight, and this was the second crew there. We've got a Japanese astronaut, a French astronaut on either side of Megan and Shane Kimbrough, 2 American astronauts, and they are still in space right now. They're docked. When I leave this presentation, I'll go over to Johnson Space Center and talk about our go for undock, which should happen sometime around November 4th, 5th, or 6th, weather dependent. This is their launch. I wanted to highlight this briefly. I don't know if any of you live on the East Coast, but they launched from Cape Canaveral in Florida. You can see their plume there at liftoff, but then it turns kind of that bluish white color. They launched into a rising sun, and people that were in Washington, D.C., all up the coast, Virginia Beach, Baltimore, New York, they were on their morning commute and just saw this crazy highlighted rocket trail in the sky, and it was magnificent for all those folks to see Shane and Megan Tamanaki launch into the space station. It was a crazy launch. Then just a month later in May, that capsule right there, you can see a rescue diver is attached to the side of that. SpaceX welcomed home Crew 1, and Victor Glover, who you heard from this morning, was on that capsule. There they are inside, right when we got the hatch open, incredibly clean. Everybody did fantastic. Shannon Walker, Victor Glover, Mike Hopkins, and Soichi Noguchi, another Japanese astronaut, took that vehicle up there and brought it home safely. They landed at night, which was really interesting to get to be out there for a night landing. The amount of stuff that comes off this vehicle as it's coming back from space, when the parachutes come out, just the amount of fabric and different fibers and materials that were floating around in the ocean was actually somewhat interesting to me to see from the rescue boat. And then June 2021, most of us probably missed this event, but to me it was very neat. It was a launch of 3 taikonauts from China, and they went up and basically outfitted and started a long duration space flight on the Chinese space station, which if you actually look, it looks an awful lot like ours, the US and Russian space station, all the way down to the blue handrails. But they lived up there for quite a few months and they just returned to Earth. And then in July of 2021, to me, it got very interesting because we started our suborbital paying passengers with Richard Branson there taking Virgin Galactic up on its first truly private mission for a suborbital flight. And then just a few weeks later, Jeff Bezos, which somewhat was a marketing flub, I think, in the end, but it was a very successful mission. You can see their booster has just returned. And one very cool thing there is Wally Funk was on that mission. She's there looking at the booster. And she was supposed to be in the original astronaut class, and then that never went through when they went with all men. And so it was really neat for Wally Funk to get her chance to go into space. Then in September, we launched Inspiration 4. We really with SpaceX on a St. Jude fundraising mission, and Jarek Isaacman, who I knew when I flew in the Navy, he funded that, being the billionaire that he is. And that mission was 3 days, fully orbital. They actually went to an apogee higher than the Hubble Space Telescope, higher than the space station. So their view of Earth was quite spectacular. They also had a few issues on that capsule. They had some bathroom issues, and I think overall they learned that 3 days in space, although it's magnificent, it's probably the wrong number of days to be in space. So if anybody buys a ticket on one of these vehicles that's going orbital, I recommend 4 or more days, because you really feel terrible for the first few days you're in space. But that was a very successful mission. And now we're into the month that we're at right now. Russia just launched a really interesting crew, which is a movie star there on the left, and then Anton Shkaplerov, who I know very well, and then the director is on the right. And right now, I just talked to the crew yesterday, and the director is up there directing them through all of the movie castings with the Russian crew members, and they're actually filming a no kidding motion picture on the International Space Station. So we'll look forward to seeing that later, probably in a year or two. And then, as we were talking about right before, really awesome as a Star Trek fan growing up. Used to watch a show with my brother, and just getting to see William Shatner on that flight yesterday and getting to hear his comments of how tiny that atmosphere was. Very special, I think, for all of us. It was neat. Looking just a little bit into the end of October here, probably October 30th or 31st, or maybe November 3rd or 4th, we'll launch our 3rd SpaceX crew to the space station. We have Raja Chari as a rookie commander, Tom Marshburn, and then Matthias and Kayla. Matthias is a German astronaut, and we look forward to seeing them on the space station. And then I do have to just fast forward into February of 2022, since Cam Gafarian runs a couple different great companies, and he is running Axiom, and we will send our first fully private research mission to the International Space Station with Axiom 1, commanded by Mike L.A. And so it's interesting just to pause in my life, especially so focused on human spaceflight, and just look back at 2021 and what has been going on this year. The number of suborbital private missions, orbital science missions, orbital private missions. We've never seen anything like this. This is a step function in human exploration for sure, and it will only build in the years to come. This extreme enthusiasm, I saw it in 2017 and 2021. Brian Kelly, who runs Limitless Space, he chaired the selection board in 2017. We had 18,000 applications. And then in 2021, we had another 12,500 applications. So in our last 2 cycles, we selected about 20 total astronauts, and we reviewed over 30,000 applications of highly qualified Americans. And these are the greatest people I have ever met. And our country is strong, and these people are really doing great things. But obviously, none of us want to stop at suborbital or Earth orbit. And so for those of you who live in Texas, if you have not taken an airplane or driven your car down to Boca Chica, right near Brownsville, you have homework. You have got to go down there. It is the Wild Wild West. SpaceX is building Starship and their giant booster down there. And if you have not driven down there, you just have to. As a human being, you have got to go see this facility. There's no gates, there's no security. You can drive your car right up to the base of this rocket and take a picture of it, and it is incredible. Just this one picture does not do justice what Elon and SpaceX are doing at this facility. They're creating their own methane. This is a methane burning rocket with liquid oxygen, and just the entire facility is incredible. Every single weld that gets made on that vehicle, I love this. Every single weld on that vehicle, the welder circles it and then signs their name underneath of it with the date. And any weld that fails, they know exactly why and who to go to. But then every welder has ownership in this rocket when it launches. Their name is all over it. They love seeing all of these welds that they did. It's just little tiny things like that empower the entire workforce down there. And they do it left and right. It's really an amazing place. So please, if you have not made it to Boca Chica, you just got to go down there. It's incredible. And then over in Florida with the Space Launch System, this is a NASA project to create a very, very powerful booster. to get us out to the moon and to get, I think, 43 metric tons off the planet and into lunar orbit. And that vehicle is fully assembled right now. The first uncrewed test flight should go here in, I would say, February, March of 2022. And then we'll look to put humans on it 2 years later. So humans suborbital, humans low Earth orbit, and very, very soon through SpaceX and NASA, humans back to the moon and then on to Mars. Sunny and kind of the buzzword around here at LSI is go incredibly fast. And so it is hard to go incredibly fast when you're putting humans on rockets. But I just wanted to take a look at some of these numbers. Blue Origin, founded 21 years ago, and they're flying humans for pay. SpaceX founded 19 years ago, and they are truly disrupting everything in the entire industry, whether it's government payloads, private payloads, or humans. They're disrupting the entire landscape right now. And then Virgin Galactic, although it really started in scaled composites, Virgin was founded in 2004. So 18 years later, they're flying humans. And then because I work at NASA, I definitely have to compare and contrast that with NASA, founded in 1958. And then 11 years later, Neil Armstrong stepped on the lunar surface. 11 years, folks. That can't happen anymore in today's world. That is just absolutely amazing. That right there is incredibly fast. And the reason in this crowd that I just wanted to take a second to reflect on that is, we, talking to Sunny, all of you, we're on the brink of some major, major discoveries that are going to be another step function in just power and in sending humans beyond our solar system. I truly believe that. And never underestimate the will of a motivated nation and the tax base to make these things happen. And that is what made Apollo happen. It took competition from the Soviet Union, as you all know, but 11 years we made all of those leaps, and that was incredible. And then I want to just take a second to look at the human element of spaceflight. This is what William Shatner touched on so well yesterday. I think it is interesting that as humans, no matter how quickly we are moving forward, in my perspective, we're always looking back. So I want to play a quick video. I don't need the audio to it. This is my launch morning. It's only about 2 minutes long. People ask me what was the hardest thing about flying into space. By far, the hardest thing was saying goodbye to my 2 young daughters, knowing that I was boarding a Russian rocket and I was going to be away from them for a little over 6 months. That was the guy who built our Russian rocket. He just leaned over and said, "Hey, everything's going to be fine." And then up the ladder we go. And you do all these simulators, and so you kind of understand everything. But when you walk up to that living, breathing rocket and it's filled with liquid oxygen and kerosene, it is a totally alive animal. You climb on board that rocket, and about 2 hours later, the pad is clear, you're fueled up, and it's off to the races. The Soyuz that I flew on, Russian-built rocket, that's my family. The only thing lighting them up was our rocket exhaust. That's my brother, my best friend, my mom in the lower left. You can even see one of my daughter's heads. Brian Kelly was with them all, taking care of them. Soyuz is a totally liquid rocket. It's smooth as silk, a little bit bumpy. The thing that really blew my mind on this ascent was how quickly we were through the sound barrier. You could hear the wind building up over the shroud covering us, and then it just seemed like seconds after liftoff, there was no wind noise as we were through the sound barrier. It's about a 9-minute ride into orbit. You're 0 miles an hour on the pad, and when the engines cut out, you're at 17,000 miles an hour. And I'm pretty much a firm believer that regardless of what we design to power us once we're in the vacuum of space, we're pretty much always going to leave the planet like this. We're going to leave the planet in some sort of liquid fuel booster, and it's going to feel a lot like this. But after 9 minutes, you can see this euphoria as a Russian, a German, and an American have survived ascent. And then we had a GoPro. This is 7 years ago, but we had a GoPro. That's a little stuffed animal from my daughter. And then this was the first look outside. I know that you all believe the Earth is flat, but I can tell you from personal experience, the Earth is actually round. It's hard to believe how many people give me grief about that. But that look right there, that's 1.2 million feet. And William Shatner yesterday was at about 300,000 feet. So nearly 4 times as high. And I can't agree more with what he was saying. It's those blues, that tiny atmosphere, and no photograph does this justice. When you get to look out with your own eyeballs and your brain processing this image and moving around the Earth at 17,500 miles an hour once every 90 minutes, it truly blows you away. Like 6 months in space, I still could not grasp how beautiful our planet is. It didn't matter whether it was a hurricane, a lightning storm at night, floods, a crystal clear day, an eclipse. It's just everything that is going on with the Earth. It is live and it is totally beautiful. So that right there is the extent of what I've ever seen. But our Apollo astronauts, you know, they went out to the moon and they couldn't stop looking back at our Earth. I love that picture. You all know that picture of Earthrise, but it's beautiful. When we send our rovers to Mars, we turn the cameras back and we find Earth. And there is Earth and the moon. I think the moon's about 3 pixels in that picture, but that is totally awesome. And then my personal favorite photograph of all time is this one. Although some of the Hubble deep fields rival this one to me, but this is our Earth Moon system right here. I'm not sure if you can see my cursor, and then the rings of Saturn. That picture blows my mind. I used to tell everybody my favorite planet by far was Saturn because I love looking at it through a telescope out back with my kids. But for sure, when you leave Earth and get to look back at Earth, there's no question which planet is the most impressive, and it's the one that we live on every day. And then in closing, shout out to our LSI partners, because I think we'll be riding this vehicle pretty soon. Might be 50 years, might be 10, might be 100 years, but we got to do it. All right, so that was about 22 minutes. I really appreciate you all humoring me. I wanted everybody to reflect on what 2021 is, because I think 15, 20 years down the road, we will look back at 50 years of humans flying in space, 60 years of humans flying in space. It was this year, I think, when everything changed. And it is an awesome time to be a part of human spaceflight, whether you're at SpaceX or Blue or Virgin or NASA, where my deep passion is with the government work that we're doing for the U.S. taxpayer. This year, kind of everything changed, and the landscape is totally different. So, Sonny, thanks for giving me a chance to talk. I'm happy to stay on for 5 minutes of questions, or I'm happy to beat feet and let you guys get back to.
No, you're great. We will take you up on some questions that just some questions from the panelists. First, I just want to say, hey, thanks for coming. As always, love listening to hear you talk. It is absolutely inspiring. And it's neat to see the videos where you're sharing that experience. I completely agree with you. I think that's very true. We're definitely seeing a golden age in space exploration, right? The 60s was a unique chapter, but this too is a unique chapter. And I want to add my voice to echo you. Boca Chica, you really should go. I took the family down there to Boca Chica, got a chance to tour the facilities down there. And as you say, it's like, wow. I mean, you can tell history is being made right there. So that's definitely put that on the to-do list. See if you can't convince the family to go down. You go down there with you. It might seem remote, but I think it'll be worth it. So
yeah, you hit on a really important part. It is not Disney. It is not the family destination that I would look to take my kids for a week-long vacation. But if you can get down to Brownsville and see that place, you got to do it.
Right. Oh, that's awesome. So I got, hey, for the panelists and folks that are online, if folks got some questions for Reid, feel free to lift them up. I think I've already got Phil. Go ahead, bud.
Yeah, great talk. Thanks so much. One of the things that's concerned me for many, many years is the risk-adverse nature of NASA. I was actually a finalist in the 1980 astronaut class, and had spina bifida that was discovered. But I'm really worried about this because, as you can see, NASA is being pushed by private space rather than being pushed internally in certain areas. Other areas NASA does fabulously. For example, robotic missions are amazing. But on the human space side, I think there's just a real risk-adverse nature to it. We've lost astronauts in tragic ways, and that has been very difficult for the public. But honestly, this has really held us back. And I wonder if you could address this issue, because many people who look at something like SLS, just kind of shake their heads and say, wow, it's been decades and it's still not off the ground. So
let Let me inject.
go
Let me
ahead,
inject one thing. So Reid is a NASA employee, and he loves SLS. So I'll say that for him.
Yeah, no, I love SLS too. I do, but I'm very worried that without a real, we can do it and let's do it. Even if it blows up, let's do it.
Yeah.
And
that's Sonny, thanks. Sonny's trying to keep me out of jail. I completely agree with what you're saying, and we talk about this all the time. Are we risk averse? Honestly, yeah, we are risk averse, but we are working very hard to change that. It's hard to change any giant government organization, but I just want you to take one quick look at the commercial crew program. I think that right there was a risk that NASA took to build up. We realized this risk aversity internal. We needed to do things cheaper. We needed to do things faster. And they said, all right, let's pay Boeing and SpaceX, and let's see if they can get people off the planet cheaper, safer, potentially. And I thought that was a huge risk on a programmatic side, and it has paid off enormously well. Boeing is coming online, still a little bit behind, and that's, I hope they're flying next year. SpaceX has completely crushed it. And then for Space Launch System, I would say there is risk adversity there, which certainly hurts us, but there's also loads of political pressure. When Constellation got canceled, that program changed and shifted. And so whenever you add in the political will across different parties through multiple years and funding taxpayer dollars into different centers and government contracts, that just drags all of that out. And the commercial crew program kind of got us out of that rut and looking at things a little bit differently. But there's still a place for these large government systems. SLS to me it's our sure bet going forward. Like what's going on at Boca Chica is amazing. And I'm rooting for them every day. I clap when they blow up and I clap when they succeed. It's just incredible in both ways. I went down there and serial number 10 had just blown up and there was a big rubble field and I was climbing all over it. There's no hypergalls. And they said, I asked them if I could take pieces and they said, sure. And so I put like a few cannon plugs in my flight suit pocket. Like I love that. It's awesome. But at the same time, we need the horse we can bet on. And for now, that is definitely SLS. So I love having this kind of two-pronged approach that we're doing. I think it's okay. And I do think this younger culture is much more aware of risk adversity. And if we never fly, that's the safest thing we can do. And that's a total failure of the system. And so the younger folks are definitely pushing to get things moving. And SpaceX is pushing us too. And that's pretty neat to see.
That's awesome. Yeah, thank you, Reid. Thank you, Phil, for the question. Kelvin, you're next, bud.
Yeah, hi, Reid. Nice to talk to you. I wanted to be you growing up. I still want to be you growing up. So much respect to you. I have a question about the current era. I loved your kind of overview, particularly last year. You referred to Apollo and the competition with the Soviet Union at the time, and that competition, how it led to us going to the moon. And I mean, I might argue that the current era started in 2003 with the loss of STS-107, because that led to, multiple administrational reviews about the space program. Are we going back to the moon? Are we not? Changes of administration, investments. And then we had eventually the government investment in SpaceX in particular, which really pushed things forward. So, one is kind of starting from conflict and it breeds competition. The other one is disaster breeds competition. I'm just wondering if there's another way where, if NASA had, twice its current budget, where you don't need either of those, and you could try and explore space constructively and with our partners that doesn't require this conflict or these kind of disasters.
I love, Kelvin, the way you just asked that question. Yeah, looking back on my own life, why am I an astronaut? It's truly because of Challenger. Like that is burned into my mind as an elementary school student when that happened. It changed the course of my life. So my career was built out of disaster. What I want to highlight on briefly in your question is, I think competition is good. I think adverse competition is good. But what I think is absolutely required is vision. And if you want to do something huge and you want to do something, whether it is government or SpaceX, you've got to have a vision, and what changed at NASA recently was Artemis. When Jim Bridenstine named this kludged together moon program, Artemis, we're going to the moon, we're doing it in 2024. Even though we're not going to make 2024, it was the first time in 10 years that I'd worked at NASA and I saw vision direction, motivation, workforce clarity. We made more progress in the 3 years that he was our administrator than in the whole 7 combined, and probably in the last 30. So there's a great inscription on this, I think, the science subcommittee in Congress, and it says, "Where there is no vision, the people perish." And I think that is what is required. Elon Musk gives a great vision for SpaceX. We're landing people on Mars. I think NASA has done a great vision with Artemis. We are landing people on the moon, and then we're going to solve some issues that we've got, and we're going to go to Mars. That vision is required. And then if you can put some time pressure on it and say we're doing it now, I think that is the perfect blend. So that's my answer to your question. I love that question.
Thanks, Kelvin, for the question. Thank you, Reid, for the answer. This is fantastic. And thank you, Reid, so much for giving us some of your time today. I just want to say something that just like Kelvin said that he wanted to be you when he grows up, I'm going to go ahead and say that I think Tom Cruise wants to be you when he grows up. So with that, hey, thank you, Reid. Appreciate you coming and spending some time with us. We're going to switch gears now and get back into some of the performers' presentations. Next up, we have Phil Lubin from UC Santa Barbara. He's going to talk to us about his project called Directed Energy for Revolutionary Space Propulsion and Power Projection. Phil, you have the con, and I'll set the timer and give you your 3-minute squeak when the time comes.
Okay, can you see the screen? Can you guys see the screen? Yes, you can. Okay, very good. All right, let me just set my timer here.
Can you hear me, Phil?
Yeah, I can hear you now. You were muted there for a moment.
Okay.
All right. Let me just start my talk timer here.
It's not in presentation mode, Phil.
Yeah, I'm going to put it in full screen. All right, can you see full screen? Yes, no? Yes. Okay,
Gotcha, it's good.
Yeah, great. All right, so this is one way to go very fast, but it's also a way to do many other things besides go very fast. In addition to propulsion, it's a way to project power over vast distances and very large quantities. So as we'll see, this is a roadmap, and the roadmap, while we are often stereotyped into little things going at relativistic speeds, should not derail you from understanding what the roadmap is, of which one of the off-ramps is little things going at relativistic speeds, but it is not the only reason we started this. Our NASA funding started in 2009 as part of the NASA Space Grant Program, and then we got funded as part of the NIAC program from a 2014 proposal, and then we've had 3 NIACs associated with this, one in collaboration with JPL, one in collaboration with Cal Poly, and then one just UCSB. So if you look at what we've done over the years, we have about 500 technical papers written, mostly on early universe studies. It has nothing to do with this, and about 60 now on directed energy systems. We recently won a NASA Luster program for looking at putting small-scale directed energy on the moon for running rovers and PSRs. We have an NRL program for a DoD demo. And Breakthrough has funded us in the past as part of the Starshot program, and now we're working on another Starshot program for communications. There's lots of stuff online if you want. Look on our website. We have a TED Talk from last year. We published a paper recently in February on fast solar system transportation, so I'll come back to that in just a bit. And then we do a lot of photonics and optics publications that are very technical. They'll bore you to sleep. So if you can't sleep, read our papers. Some recent ones here, if you're really into bidirectional fiber amplifiers for phased arrays, locked remote beacon, which is just a fancy way of saying we're making things in the lab that can drive spacecraft. Take a look at that one. These are all 2021. These are with LSI funding. We now have some amazing results to show you. If you thought last time was amazing, this time is literally 1,000 times more amazing, because 1,000 times is what we achieved in increased sensitivity. Lots of simulations, very, very technical stuff, radiation effects on relativistic spacecraft, survivability of metallic shields, running various particle codes, some AI work we did with model optimization, This one in particular, this fast solar system transportation, I would urge you to look at it. It's an ACTA, or just go to our website, www.deepspace.ucsb.edu, and look at our papers. They're all there. Lots of stuff on challenges to communication systems, and then the paper on the roadmap to interstellar flight, as well as a follow-on for ESA. So a lot of material. I'll try to make it relatively as painless as possible. We do a lot of stuff. So we have the blessing of being able to be completely scalable from things that are directed energy systems that fit in your hand to proposing systems that would fit in a city. So it's really a question of economics and scaling, but they all are self-similar in a sense. So this is where we differ dramatically from many other approaches. Building, as a child, I always wanted to build a small nuclear weapon so I could have a bigger firecracker. But then the more I learned about nuclear physics, I realized I can't build a small nuclear weapon without a large laser array anyway, a large laser system like at NIF. So I had to put that away for a bit. I still want to do it. We've now built laser amplifiers that have greater than 100 dB of dynamic range, which is just unprecedented. And I'll show you the data for that. We were able to simultaneously transmit an enormous amount of power and receive an incredibly tiny amount of power. And that incredibly tiny amount of power is used for phase locking the system. So this is a spectacular achievement. And it's the greater than 100, it's just so far we haven't been able to figure out how large it is, but we're already getting down to a photon limit there. Okay, so system is working as expected in the sense that we've published papers saying we could do this, and now we're doing it. And it's working at about the photon, very close to the photon limit, which means that we're becoming photon starved. One of the things we'd like to do for the, we're at the end of the LSI program, but we're not at the end of our vision of accomplishing this. So one of the things we want to do is seek additional funding for kind of a 5-year concerted program, probably culminating with a lunar mission to send power to the moon and put a beacon on the moon as a part of a feedback system. And I'll show you some pictures of that. So I'm just speaking for our group. The group really does the work. Lots of incredible people. Peter Meinhold, Bertrand Srinivasan, Peter Krogan, John Suin, Sasha Cohen, Brian Phillips, Nick Rupert, and then a number of undergraduates. In fact, we've had hundreds, literally hundreds of undergraduates work with us on directed energy. It is a fabulous way to blow holes through things, and they figured that out pretty quickly. So we have a vision for the future, and it starts, down here, which is where we are now, laboratory testing, showing that things work as we say they will, or finding that they don't work as we say they will, and then figuring out what the problems are. We build lots of and develop lots of technology, including our own amplifiers. We build almost everything in our lab for financial reasons, and because we can do it faster, better, and cheaper, way cheaper than others can do it, and a lot faster too. We're also doing custom laser photovoltaics for demonstration programs, and also for driving ion engine tests. And then we're working on very, very tiny sort of wafer scale spacecraft. But please do not put us in a box, which is only wafer scale spacecraft, because it's not true. Our vision is to go along this roadmap from laboratory testing ultimately to things like powering LEO and GEO assets to keep them in orbit longer, or to give them more power. Power beaming to the moon is one of our roadmap exits. Rapid transit to Mars, which I'll show you in a bit, fast human transit, and then ultimately outside the solar system onto interstellar flight at relativistic speeds. It's all a question of scaling. This is where we differ dramatically from other technologies. We can have things that are the size of your finger, and in theory we could have things that are the size of the city, and they're all sort of self-similar in this way, and they're replicated. They're basically identical versions of each other, just make lots of them. So this is where an economy of scale comes in. There's lots of other applications, from doing things like, having a helicopter on Mars, which there is one now, but it has to come back and rest and get some sunlight to recharge. We could, in theory, keep it up indefinitely by using directed energy from the RTG on board, the kind of, the mother rover, if you will, to the helicopter, either on Mars or Titan, as an example. Space debris mitigation. We can take out space debris and we can actually do machining on spacecraft in space, which some people would not like. The problem is we can't get rid of the lawyers who control space debris problems, although we could actually get rid of the lawyers if they were in orbit, but we probably shouldn't discuss that. It's also very useful for planetary defense. We have about 20 papers on planetary defense applications, including comet deflection and asteroid deflection. We just published some stuff yesterday that you may have seen on planetary defense using another technique, but I'll not talk about that today. Anyway, lots of other applications, solar system-wide LiDAR, for example. Just give you a quick example. We were asked by NASA to look at the following question: could we get humans to Mars and not fly by, but land on Mars using this technology? So the basic idea is you project power to a spacecraft, and then you use that power to convert back to electricity and drive an ion engine. So it's like nuclear electric propulsion without the nuclear on board, so the mass goes down dramatically. And so we looked at this, and NASA has to look at 45 days. We showed, at least on paper, and this is in this ACTA paper that we published in February, that in theory we could do it in 30 days, and again, including going into orbit around Mars. So that's a spectacular aspirational goal. It is the same system you'd use for relativistic flight, but used in a different mode. You reconvert the power to electricity on board and then drive an ion engine. That does not work for getting to relativistic flight. It does work for getting high masses at modest speeds, say 100 kilometers per second or so. If you really wanted to ask how fast could you get to Mars, if you really pushed it, you could get to Mars in 2.5 days, including acceleration and deceleration at 1G the entire way. So you wouldn't even know that you're going, except for the flip point halfway when you start to decelerate. The problem is this uses direct photon drive, much like our relativistic systems. You get up to about 3,000 kilometers per second, by the way, at midpoint, but requires vastly higher power. So it's more efficient. If you're content with getting humans to Mars in a month, better off using reconversion to electricity to drive an ion engine. Someday, if we want to get humans to Mars in 2.5 days at 1G, you could do it. I picked 1G because humans don't like to run at 10 Gs the whole way. I think humans are kind of useless, to be honest, in terms of long-term development, but that's another discussion. We're kind of big, bulky, and fragile. Okay, so this is from Sheeran et al. As a paper we published in ACT Astronautica. It came out of a long NASA study that we did as part of a proposal. So this is looking at various missions from Mars, flyby Mars in 45 days, going out to Jupiter in a year, Pluto in 5, flyby Voyager in 10. And these are the indirect mode. So this is not the relativistic mode. This is converting into electricity on board and then driving an ion engine. So very conservative from our point of view, very low acceleration rates. But the one I want you to focus on is not these, but is this one, because this is a demo mission that could be accomplished. This is a CubeSat mission that could get to Mars and would fly by in 120 days. So it's a demonstration that you could use this technology, and it does not require an enormous financial input. It requires an array, a laser array, which I'll get to in a moment, that's about the size of current astronomical telescopes, 10 meters in diameter. And it requires a power of about 1 megawatt, so like a small company. Those are very practical. The CubeSat has a wet mass of 10 kilograms, and then a flyby mass of 4 kilograms. You thrust for about 5 days, and then it goes off by itself. So the laser's not on for 120 days, it's only on for 5 days. The power to the ion engine is very modest. It's only 600 watts. The collector on the spacecraft is only 40 centimeters. So these are not exotic, relativistic missions. These are very practical missions to prove out the technology. We would love to find somebody like a NASA to invest in this technology to get to that point. Okay, these are the ways we currently get out there. Currently we're in chemistry mode in general. We do have some ion engines that are using solar electric. So we can take light and either from the sun convert it to electricity to drive an ion engine like the Dawn mission and a number of other missions. This is becoming relatively routine now. Or you could have directed energy, which is just light, but directed in a more focused manner effectively, a more just you have a smaller beam and either convert to electricity to drive an ion engine or use direct photon drive. And this is the one that gets to relativistic speeds. This one will not. The secondary mass is too high. This is a particle accelerator. If you go through the math, it doesn't work. It's in our papers. This one does work and in theory gets you to relativistic speeds. Again, this technology has all of these possibilities. And so, please, when you think about this, this is not just this technology, which I know we are literally stereotyped into. It opens up an enormous parameter space. So on the sort of path to the stars mode, which again is small things at ultra high speeds, we're kind of here today. We hope to be here in a border, say 10 years or so, where we could send out something and shoot it to the moon. And then I would say kind of 30-ish years, if we really went for it, we could be at relativistic speeds. But the arrays have to be big, of order kilometer or so. But I remind you that 60 years ago, when we were working with early photovoltaics, if someone asked you to build a 1 kilometer photovoltaic farm, you would have said not possible, but now we routinely do it. Okay, so one way to think about this is I need a gigantic flashlight, a gigantic laser, and if you try to do that, I don't know how to do that in one gigantic laser, but what we do know how to do is take many smaller laser amplifiers and build the equivalent of a phased array that's used for radar systems, but in the optical near infrared. You can't just take a bunch of laser pointers and combine them. That you can do, but it doesn't give you the coherent beam combining that you need to get a small interference pattern on the target. So what you want to do is coherently combine by having a master oscillator and then many amplifiers. So this is how phased array radar works. You have a master oscillator and then amplifiers on each patch. So synthetic aperture radar works in this way. So we've done this now and it works very well. We're operating currently at 1064 nanometers where there's a transition line in ytterbium, which is very efficient. We start with an oscillator, master oscillator, which in this case is a small fiber laser. It's about the size of your hand. We then build amplifiers ourselves, which I'll show you in a bit. These are about 50% efficient from electricity into photons. You amplify, you phase shift, and then through a fairly complex mathematical technique, you do phase convergence on target using a beacon at the target to phase 2. And then you do a lot of complex mathematics to get it to work. But so far it's working as we expected. So we've published a lot. And again, just look on our website. There's a lot of very technical papers that show real data with real equipment that we build ourselves. So this works. So one of the reasons that starting on the ground is hard, I'd much rather be on the moon or in orbit. One of the reasons I start from the ground, since someone's unmuted there, is that the atmosphere is turbulent. So to accomplish this from the ground, we're going to have to overcome turbulence, which is normally done using adaptive optics and astronomy. But we have to do it to sub-nanoradian precision. And that's very hard, but we've shown that you can do that given for a kind of a good site, like a high altitude site used for astronomy. So we've shown that this works. And if you're interested, you can look at our papers. At least it works in the laboratory where we introduce perturbations from the atmosphere. We'll be going outside soon. So the topology is fairly complex. So what we're doing is building the equivalent of a supercomputer, and then we take a lot of small processors and synchronize them and then compute. Except for us, we take a lot of small laser amplifiers, start with a master oscillator, which we call a seed laser, split it, all done in fiber, amplify it, emit, and then phase lock to the target via a back-going beam that we then conjugate and send the beam back out through the atmosphere, correcting for the atmosphere. I would much, much rather not have to do this. I'd rather be in orbit or on the moon, but that's much more expensive. And so we'll do all we can from the ground, and it appears we can do it from the ground, but it's not the ideal place to do this, but you have to start here. So our approach is the one that we actually outlined in our very first papers on this. It actually goes back to really 2009, but if you look in our 2015 papers in particular, you'll see the basic topology written out, and it provides a complete phasing solution. And it is really exactly as we proposed, except now we have the data to prove that it works. So this is what it looks like in our lab. We build real equipment in our lab and take real data, and we've got a lot of data, as you can see in our papers. So this is a 3-channel system. It's not, quote, weaponized yet. I'll show you that version in a bit. What we're working towards is a modular system. Each of these little circles here is about the size of your hand, about 10 centimeters in diameter. And then this is a 1 meter array, and then you would mosaic them into as large an array as you need. They're all identical, so you can mass produce them. It really comes down to an economics problem at this point. So I'm not going to bore you with this, but this is where we spend most of our time. Rather than making up PowerPoints, we actually get data. So we've now managed to phase lock to 1,000 times better than we presented in May, and even in May. We also when we talked to Sunny in, I guess it was August, our goal was to get to 1,000 times better. So that was, I don't know, three months ago. So we've now done that. We're down at about 60 picowatts, which may not make much sense to you, but it is about 5,000 photons in a 1 microsecond aperture, because we close our loop at about 100 kilohertz, primarily for atmospheric reasons, by the way. So if we're on the moon, we could do this even better, but we're already doing it at relevant rates for atmospheric closure. And we therefore are at a position where we're just about photon starved, and we're able to work in a photon starved regime. Now, we don't have to be photon starved. We could increase the beacon power, but we're trying to see how low we can go. And you can't really go much lower than this, because if the uncertainty in this number is basically counting statistics. So the square root of 5,000, is approximately 70. Which means we can get to about 1/70th of a wave. And that's precisely what we do. We get about to 1/100th of a wave in reconstruction. So we're essentially photon limited now. Our proposed phasing solution from, literally 10 years, but at least 6 years ago, you can look at our papers on it, seems to work. And it works in reality as we had proposed on paper. Now there's much, much, much more to do. So I don't want to oversell this, but at least in the lab, we're getting to where we want to be, which is near photon limited. This is what it looks like. Probably don't care. You don't care about that. Probably don't care about that either. Although if you're into bits of resolution, we are greater than 37-bit dynamic range, which is an amazing statement. We run in a fully bidirectional mode. So you can be blasting out power to blow holes in things, and at the same time, receive power at sub-nanowatt levels. And we actually use the laser as a maser. If you're familiar with masers are used in space communication for amplifiers for receiving weak signals. We run our laser as both an outgoing amplifier to go to high power and an incoming amplifier simultaneously to amplify incredibly weak signals. So just imagine, it's literally a billion times a billion photons per second coming out, and say 1 million photons per second coming back in. It's incredible. rather blown away that we can do it, but we've shown it works. We're able to synthesize the beam. So basically the idea is you're taking a bunch of laser amplifiers, you're forming an interference pattern on the target, and that way you can form a beam that's very small and very high flux. So I'll just show you some movies really quickly. This is for different filter functions, and you can see that with no filtering, we do okay, but things move around a bit. But when we do a 5 megahertz low pass filter in the electronics, this is all done with FPGAs and synthesized radio techniques. 2 megahertz works. By the time you get to 1, it kind of works, but you're right on the edge of stability. You'll see this thing move around a little bit, and you can see this moving. So anyway, this works if you're interested in looking at our papers. We're building lots of stuff. So this is where we go into the weaponized version of this, things which don't look like a rat's nest in a laboratory. So this is a laser control electronics board. It's about the size of your hand, very thin. This is what we're building out now. These things are all identical sub-elements. They go into clusters. The clusters go into hexagonal close packed arrays that then go into other arrays. It really is now, as I mentioned several times, an economics issue. So this is some of our latest hardware that we took yesterday. A lot of the stuff is 3D printed and then CNC and laser cut. So it's relatively economical, and it all works so far. And again, almost all this stuff is built in our laboratory with a few exceptions. We don't dope the fiber ourselves for the ytterbium fiber, and we don't build our own drive laser pumps, although we could, but it's just not worth our while to do that so far. Everything else we build. And these are just different cooling solutions. So we're working on this already. It's already being built, and we'll keep you posted. One of the things that we said we would do, and we're just a little behind schedule here, but not too much, is we're going to be building a cluster of receivers that can be distributed either as, say, 1 on each, or 3 on one, 1 on the other, 1 on the other, in different ways. You can move this synthetic aperture array. You could separate these by meters, by hundreds of meters of a football field, or by kilometers or 10 kilometers. We've shown that we can phase lock out to 50 kilometers now, which is vastly bigger than we need for interstellar flight. But we don't know what the limit is. We went to 50 because we could do it in the lab, but I don't know. Wouldn't be surprised we could go to several hundred, but we don't need to. Okay, we also have short range goals. So again, this program, because it's scalable, can be used for very practical things, not just for going to Mars or sending power to the moon or going to interstellar capability. But here, NASA asked us to look at, could we send power from the edge of a crater into a PSR to run a rover? So that's what we're doing. We have a program from NASA, which is a 2-year program, which is a really fun program for us to do precisely that. So we have a tracking system when we can send power to things, blow holes through things. So the undergraduates love it. This is what I'd love to do. So if you know anyone who wants to do this, we have the ability to design and execute this. We'd like to put a beacon on the moon, which is a small phasing laser, which would be about 10 watts of laser power, and send it back to the Earth. So it's not going to blind anybody because the flux of the Earth is very, very low. Then what we do is we use that laser on the moon to lock our elements that we built with the LSI program, 3 of them spread out into a 100-meter circle, just 3, and send power back to the moon. And then on the same spacecraft, we have an IR camera, which will take a picture of the moon, and we will show you how the moon got its spots. So we will produce an interference pattern because it's a sparse array, 3 elements spread out, we will have spots rather than one concentrated spot. I'd love to do that experiment. We've been talking to Intuitive Machines about doing that. Beam sizes and fluxes, if you're interested. If you had a 1-meter array of the type with our small elements, each 10 centimeters, each exact as I showed, I know a couple of minutes I'll be done. We could send about 1/4 watt per square meter to the moon. If we had a 10-meter array, we could send about 2.5 kilowatts per square meter to the moon. So this would be a killer application for solving the lunar night, because there would be no lunar night. We would send power to the moon during the optical lunar night. You would have an infrared sun, if you will. If you had a 1 kilometer array, you'd get 260 gigawatts per square meter. And if you had a 10 kilometer array, so these are interstellar capable, you could put 2.5 petawatts per square meter. You could write your name and make it in glass on the moon by melting the lunar regolith, which we've actually done in our laboratory. It doesn't require this much flux. Really, this is what we'd like to do, is execute a 5-year roadmap to the next set of programs, which is build meter class arrays, work on the photovoltaic integration for the ion engine class missions and for the lunar missions, power rovers and various craft, and then do sparse arrays for sending power to LEO, MEO, GEO, and lunar. So very logical, very cost-effective set of desires that we have. This is a wonderful program for inspiring students. We've had more than 100 in just the last 5 years. Over the last 10 years, we've had about 300 now, many of them working on planetary defense issues. It's a wonderful way to engage students, children. We've had very young children work with us. We're very careful. We've never hurt anybody. And it engages the public imagination. So I'll stop there. I have 20 seconds left on my timer, and I'll be happy to answer any questions.
Fantastic, Phil. Fantastic. And it's like Kelvin came in and set the high water mark, and you're like, yeah, what? I'm bringing it, buddy. Good job.
He had more slides than I did, just to be fair.
If you want to go ahead and unshare, that way we can.
Oh yeah, sorry about that.
Smiling bugs. You know, I try and write down quotes that I hear from different people as they're talking, and I've got a few, but man, you gave me a bunch during yours, man. I love your opening. What was it? When I was a child, I wanted to build a small nuclear weapon. You are Sheldon Cooper, right?
Yeah, I'll tell you a funny story. My son, I have lots of, I teach courses on weapons of mass destruction, and my son asked me, where do I get plutonium, stuff like that. I said, well, you can just for fun email Livermore. So he sent an email to Livermore and said, I need to get some plutonium for a project. And he told me what he did, and I said, oh, okay, this could end well. We'll see if we get a knock at the door. But I passed it on to other people.
That's funny. So, okay, we've got some questions already lined up here. Let's see here. Hold on. Sorry. My phone was fussing at me. Richard, I think you're up first in the queue. I'm assuming it's going to be top to bottom. So Richard, Kelvin, and Charles.
Yeah, awesome talk. Yeah, thank you very much. Yeah, so I had a question about, actually 2 questions. So one of them was just about, you said that now power is not a problem, but so I was going to ask, what are your thoughts on the ability to expand the tunability of these things, and do you see any major advantages to being able to tune it? And then the other one was about the receivers for these energy beaming. What kind of receivers are kind of the best ones right now, and what are the big limitations?
Sure. Okay. So tunability of the laser to help people that are building reflectors. I'm not sure you know anybody that's doing that, but yeah. So in theory, we can tune, and the real complication is more of a technical one than a theoretical one. Yes, we can tune. In practice, it is hard to tune over wide ranges because we're using transition lines for the amplification, and those tend to be, modestly narrow. So if we wanted to tune over, say, if we're going at 20% speed of light, we have to tune over roughly 20% of the center band. So that's hard, not impossible, but it's hard. So it could be a goal for the future. The other approach, of course, is to build broadband reflectors or some compromise in between. So I don't know. you and I have talked offline, there are different ways to look at this. I wouldn't take off the table tuning. It's purely a technical state-of-the-art issue. There are wideband tunable lasers for other applications, but the high power and the amplification is the problem at the moment. Second question, yeah, we do work on photovoltaics for both DoD program and then for our NASA Luster program. The best devices currently are in indium gallium arsenide devices, which have efficiencies. So our Luster program is centered at 976, whereas the LSI program is centered at 1070 nanometers. So, and that difference doesn't seem like much, but it actually turns out to be significant. So for InGas at 976, we're working with Boeing, and we expect to get in excess of 50% conversion efficiency. With InGas at 1070, we've tested some cells that they've made for us in InGas, and we get aboard 40% efficiency. Currently, they think they can do 45, maybe a bit better. And that, it keeps getting better. There's no reason you can't do really high. Recently, we've started working with some custom silicon devices and gotten 28% at 1070, which is pretty remarkable. And so now we have the ability to build kilowatt electrical arrays of specialized silicon devices. The advantage there is the cost of silicon is much less than the cost of indium gallium arsenide.
Okay. Thanks.
Thank you, Phil. Thank you, Richard.
Yeah. Non-technical question, Phil. I'm just curious about how young are the kids you're working with in the schools, and what sort of ages, and what are you doing with them?
So, I have children, and I'm used to children, and I am, by nature, a risk taker. I used to race motorcycles, and I really was an astronaut candidate, and they did find I had spina bifida when I came down to Clear Lake for the final interviews. I am very careful in the laboratory. So I work with children, as young as, 5, 6 years old, but, very, very carefully. Kids are used to laser pointers, and, they know that, if you stick a laser point in your eye, or even an LED flashlight in your eye, it can hurt, just like looking at the sun. So we kind of go through the process of talking to them about it. We don't, put them in the lab and say, hey, turn on this kilowatt laser, go at it. Not at all. We don't do that. Most of our students are undergraduates and graduate students, who are quite mature. And then we have a program that brings in a lot of high school students, and they're can be quite mature, and some of them, of course, are not. And so, we have to be careful. But the dangers of lasers are real, but they're often overstated. So I'll give you one example. I was in a laboratory that is a DoD laboratory, and I was going to give a presentation. I said, hey, where's your laser pointer? Because they build high power direct energy systems. I said, you're not allowed to use your laser pointer. I said, why? I said, oh, it's not eye safe. And I just lost it. So, a laser pointer, a laser is different. It's narrow band. It can have a long coherence length, but, really take an LED flashlight and shove it in your eye, and you can hurt your eye. So it's just a quantitative question. So I show students, the maximum permissible exposures, as a function of wavelength, and talk to them about eyes and eye safety. And it's just really overblown. It's the whole risk adverse, stuff I was talking about earlier, but you have to understand risk, and then you have to understand how to mitigate it.
Yeah, so I got 2 young daughters, 4 and 7. I take them out in the garden sometimes with the laser pointer, and they almost turn it into a lightsaber. So I have to be very careful.
Well, I was going to say earlier, when we were talking about space flight, 1, life is fatal. 2, you have a 1% chance in your life of dying in a car accident. And 3, if you look at the number of astronauts who have passed away in flight, we've had about 600 people in space, and I don't know what the total number of losses is, but I'm guessing it's, less than 50 would be my guess. Is that, you have maybe a, 8% chance from the very beginning of the space program, to dying. And that's, so maybe it's 8 times higher than being in a car accident over your life. but it's not a catastrophic risk. And we take risks all the time. You know, you go to the store, you take a risk.
Cool.
Personal opinion only. Okay.
Thank you, Kelvin. Thank you, Phil, for the answer. I think last question we can take is Charles, if you can be quick with it, please.
Sure, yeah. Phil, really appreciate your work, and your making things real is really very, very much appreciated. I was just wondering about contrast to spectral beam combining, and if you could provide some thoughts on how your approach compares to spectral beam combining, and if that might be a viable alternate method in your mind.
Yeah. So spectral beam combining is being used currently in tactical weapon systems, and it does work quite well. There, you're less concerned about coherence than we are. So we're trying to coherently combine to produce an interference pattern. So it's extremely important that you be able to produce that interference pattern. Now, in theory, you could do it with spectral combining by having multiple interference patterns that are independently cohered. But it would be a complication. I'm very open to different ideas. Sometimes people think, why don't you just build a bigger laser amplifier? And we can. You know, we work with people that work with kilowatts. The problem is currently, we don't actually need for most applications to go to too high power per sub-element. And our sub-element size being 10 centimeters is actually set by atmospheric perturbation scales known as Fried length scales, which have to do with turbulence in the atmosphere. So you can't go above about 10 centimeters without doing higher order perturbation corrections. But if you're on the moon, you can go to very large apertures, and there you might want to go to, say, meter class apertures, and then you might want to go to higher power. We're working on a 100-watt version per sub-element. 10 watts per sub-element at a kilometer gives you sort of interstellar capability already. If we go to 100 watts, then we'll have 10 times more power. Currently, going to kilowatt is problematic, but it's just purely a technical issue which can be solved. It has to do with moding. That's known as SBS problems in fibers. There's no intrinsic reason we couldn't go to long coherence length and have high power. Currently, we don't need the high power. Spectral combining is mostly used for high power for tactical systems where you want it in a single fiber. I'm happy to talk to you offline about the DoD side of that, or other things. So.
Cool. Thank you, Phil. Great talk.
Thank you.
Thank you, Charles, for the question. I definitely liked one thing you talked about, writing your name on the moon. Right? Anyway, we need to switch gears and get on to the next talk. Next up, we have Charles Chase from UnLab. His project is called Asymmetric Potential Vacuum Fluctuation Forces. So with that, Charles, I'm going to hand the microphone over to you, and I'll start the timer once you get started.
Let's see. Can you guys see my slide okay?
We got you.
Okay. And I'm just wondering if there's a way I can move the thumbnails on the side. Let's see.
If you hover the mouse over the picture, it should also bring up a tiny black bar at the top.
Yeah.
And that would allow you to move that. We can't see your thumbnails, so you don't have to worry about them bothering us. We can't see.
Yeah. Okay, great. Thank you. So yeah, our grant is a little bit different from turning things into reality, although I think we have found a very interesting theoretical result that our next step is to demonstrate it experimentally. And what we've been looking at is how can we generate forces from vacuum fluctuations, in particular using asymmetric potentials that are found in resonant tunneling diodes. So we do put energy in the system. So it's not like we're getting something for free, but we end up with a propulsion approach that is like a solar sail in that it has infinite ISP. And this is the team here. My collaborator is Yuval. from Technion, and Micah and Kobe are the ones who are doing all the heavy lifting. And I think we might have the largest time difference in our team between Micah on California Pacific time and Yuval in Israel. We have about a 10-hour time difference. So anyway, interesting fact. Let me see. Why is it not going down?
I try page up, page down. Is that or the up, down,
Yeah.
arrow?
It's my computer. My is all of a sudden frozen. Let me stop sharing. Sorry about that.
No worries.
Okay, it works when I'm not sharing. Let me try again. Okay, can you see it now?
Yes, we can see it.
And let me go back to full screen, and yeah, it's working. Okay, just a little quick background because not everyone is familiar with the vacuum fluctuations. It has a lot of different names, but it's really the ground state of the quantum harmonic oscillator and in quantum electrodynamics, and you just can't get rid of the h bar omega over 2. It's always there, the ground state. Also in Planck's law, there is, where that really came from in the first place. There's also the ground state that's always present. And of course, people talk about the Casimir force and the exclusion of the modes inside between the cavities, potentially generating very large forces, a pressure of 1 atmosphere, a 10 nanometer separation, though no one has actually measured that. And in QCD, the vacuum is used to predict where mass comes from. So 99% of a proton's mass is from vacuum fluctuations. And, there's lots of observed phenomena attributed to vacuum fluctuations, spontaneous emission, the Lamb shift, et cetera, et cetera. And you can model it using fluctuation dissipation theorem as fluctuating dipoles. It really converges to the van der Waals force between individual dipoles. And with the Casimir force, you have the waves, the retarded waves that also enter into the calculation. But, I always like to point out that the reality of the vacuum is not really a done deal, though pretty much every paper these days says that, the vacuum is responsible for all those phenomena. You can derive the Casimir force, the Lamb shift, with never using the vacuum. You can use radiation reaction and come up with those effects. And of course, the vacuum energy based on the cosmological constant is very small, but QED predicts, and this is a Planck scale cutoff, 120 orders. This is the famous 120 orders of magnitude difference that we see. But you can't come up with a consistent theory of QED. You can never get rid of this h bar omega over 2. So it's really not totally known what is the vacuum, I would say. But we want to generate forces from the vacuum. So what does that take? And so, you can just make a very simple energy argument. And if the vacuum has symmetry, translational and rotational symmetry, and it's in thermal equilibrium, there'll be no net force or torque. And that's independent of the physical model details. It doesn't matter if you're using QED, fluctuation dissipation, what you're assuming. It's a simple energy argument. So you need to break one of those two assumptions of symmetry or equilibrium. And so we're breaking the non-equilibrium assumption by having an asymmetric potential that breaks equilibrium. And, there's also appears to be quite a bit of evidence that the vacuum symmetry can be broken and the vacuum is actually mutable. And of course, actually in curved space-time, there's not translational symmetry in the first place. and an object accelerating in curved space-time is not in thermal equilibrium, but those are much smaller effects. So we're trying to take advantage of this non-equilibrium. And this is our approach here, where we have a asymmetric potential, like is in a resonant tunneling diode. And what we're plotting here is the wave function, the probability, and it's asymmetric as it goes through this asymmetric potential. And we hypothesize that this will interact with vacuum fluctuations and introduce forces on the nanostructure that we can use for propulsion. And so the value proposition is, again, propellantless propulsion. And, like a light sail, acceleration to near light speed, limited to vacuum friction eventually. And, in this, So, there are several different embodiments of diodes, resonant tunneling diodes, that provide the sort of characteristics of an asymmetric potential that we're looking for. And these are some examples here. We did, under the program, a fairly exhaustive look at different diodes, and whether it's a double barrier here. This is a very interesting work out of Sandia, where it's photon-assisted tunneling. This operates up above 1 terahertz. They use it for harvesting low-grade heat, generating that into a current. And then, we've based some of our analysis on this triple barrier array that is made in Japan. And this just depicts on a wafer. We envision being able to make these on a wafer, and we would there'd be forces in these different directions depending upon the way the current moves in the device. So, does that sound like pulling yourself by your own bootstraps or not? We are putting current into the device, but there are some very interesting recent vacuum fluctuation experimental data that shows that vacuum symmetry can be broken. And our friend Garrett Modell at University of Colorado recently published a paper on optical cavity induced current, where he thinks that the energy that he's generating in his diode is coming from the negative vacuum pressure that is in a Casimir-sized cavity, so that causes zero-point energy flow. And his thesis is that the time that it takes at certain energies, higher energies, higher frequencies, that the time it takes for the electrons to transit his system is shorter than the time that it's coupled to the fluctuations of the vacuum. And his data is really very interesting. So this, if you look at the size of the Casimir cavity thickness versus the current that is generated, and this is without any input energy, it clearly depends on this cavity thickness. There's also recent work on fluctuation-induced currents from graphene. This is out of Arkansas, actually, and these the fluctuations in the graphene, which they attribute to vacuum fluctuations, are again generating a current. And I just wanted to point out, Garrett has just recently had his patent granted on these type of devices, September 28th. So that just recently happened. Not that I have patents on several things that, who knows if they actually can be made into reality or actually reflect the truth. But as further background, there's been evidence of vacuum fluctuation asymmetry or pressure, negative pressure from shape, structure, material, and potential. And these world line calculations, and I just want to thank Sunny for pointing out this wonderful approach spearheaded by Holger Gies on making these calculations. Here's a sphere and a plate, and the negative vacuum distribution is clearly asymmetric. Here's a measurement of the vacuum inside these holes, showing a kind of similar asymmetric shape. Shanhui Fan from Stanford has shown that changing the chemical potential changes the Casimir force. And people have looked at the Casimir force between differing materials and how that generates an asymmetry as well. And then, another factor is, can we couple to the vacuum? So it's key to us to be able to couple to the vacuum. And that's what people do when they're making measurements of vacuum fluctuations. Here's some fairly recent papers, direct sampling of electric field vacuum fluctuations published in Science. And what they do is they couple two different pulses, you can see in the little black one, to the vacuum fluctuations, and then they deconvolve that. And so it's kind of the difference between that, they attribute to the vacuum and a measurement of the vacuum itself. And if they incorporate area, they come up with an actual magnitude of the vacuum of about 20 volts per centimeter. These folks, the correlation measurements use a similar technique, measuring the vacuum, a terahertz vacuum, using a nonlinear crystal. And people make hybrid states with the vacuum in a cavity so that you have different chemical reactions that can happen, and you can detect a change in conductivity, for example, via coupling with the vacuum. So it appears that you actually really can couple to the vacuum. And so to look at our device and to see if we can generate forces, we first started with the original Lifshitz calculation approach that led to fluctuation dissipation theorem, and looked at different dielectrics and the forces between that. And the interesting thing is that, if you have a device that is made of, say, a metal and a dielectric, the vacuum the reflection and transmission is going to be different, asymmetric, if they're held at a constant distance. So we're not using the vacuum fluctuations to generate an attractive or repulsive force, but looking at the difference in the force. And so that kind of indicates that there's some asymmetry there in the force. And then another thing that we looked at in a little more detail is calculating the wave function, the probability of asymmetric versus symmetric modes in different devices. So this is a device that is symmetric, and you can see all the different modes, and these are modes coming in both directions. So we have the modes it being excited in both directions. This is a resonance structure. You can see the tunneling through the barriers and the resonant in the device. And so if you have a symmetric situation, all the modes are symmetric. But however, if you make the device asymmetric, in this case, we use thickness rather than a potential difference to illustrate it, that you get asymmetry. The modes propagate, the probability of finding them is different on each side. And so that difference in our mind has to go somewhere. And it happens at the resonant frequencies, not at the non-resonant frequencies. So, in our mind, the conservation of momentum requires that there be a force here because of that asymmetry that's generated in the situation. So we've taken this further, and using a technique that was developed by Lawrence Ford, who's out of Tufts University, who's done a lot of work on the radiation pressure of quantum fluctuations, a series of papers. A couple of things he's shown, for example, is that the vacuum fluctuation increases barrier present penetration when you take that into when that is present. And then his most recent work was vacuum radiation pressure fluctuation on atoms. And the velocity fluctuation was found to be 800 meters per second based on the vacuum radiation pressure, which is greater than the thermal motion at low temperatures or photon recoil. So we took his approach, which is based on the scattering cross-section, the stress tensor, and a temporal sampling function, which governs, how long is this interaction going on. And we applied that to the diode I mentioned previously, which is this triple barrier diode. And so what we did is we used their experimentally determined value for the field inside the device, this 3.6 times 10 to the 4 volts per centimeter. And using that, we were able to calculate for one diode, which would be the force, which is based on the area of the diode, 0.02 square microns, is about 2.2 piconewtons, which is, really quite measurable these days. We can measure down to femtonewtons pretty easily. So, but does it scale to anything? So we just did a simple calculation of a fab on a standard wafer where you thin down the substrate and assume about a 10% coverage of devices. And you end up with getting a really appreciable number of newtons per kilogram out of something like this, 9.3 newtons per kilogram. Now, of course, we made some assumptions. We assumed that the vacuum fluctuation is coupled to the field, which seems to be very valid based on measurements that people have made, that the coupling lasts longer than the transit time through the diode, which governs this temporal sampling function. And, that seems to be valid based on some of the work that Garrett has done. And then in this case, the reverse modes were neglected. And when we looked at our modes going through a device, that seems to be a very fair approximation as well. So this is a really exciting result. I mean, I must say, this changes everything. If we can actually use the vacuum to generate a force by putting a current in a diode, it'd be, wow, that would be something. And so we also calculated, as the size of the field changes, what happens. I won't belabor that. And, so in thinking about an actual device, it's interesting to consider that, like at room temperature, above 7 terahertz, the vacuum fluctuations dominate the energy in the Planck distribution. And it's down below 2 terahertz at 70 K. And, it's almost, it's very negligible. It's extremely dominant down at 4K. So we would like something that interacts with terahertz sort of frequencies of the vacuum. And, here's just a simple depiction. And this is kind of the series of tests that we'd like to do. We'd like to look at a simple asymmetric potential resonant tunneling diode, where you have the tunneling here. And, we think there's going to be momentum in this direction from the modes. To enhance it, we think just like Garrett did, we can use an optically sized cavity region that would have a negative vacuum fluctuation pressure that would help increase the asymmetry and draw the vacuum to the negative pressure. I was worried that was Sunny telling me time is up. And then further.
No worries.
Okay, all right. So, further, in addition to, so here's our diode, here's our negative vacuum fluctuation pressure. We would like to have a coupler that couples in the vacuum fluctuations that are centered at the resonant mode of the diode here, the resonant tunneling diode, because we want that frequency that generates the non-symmetric asymmetric mode to be key. And and we want that to be up at kind of the terahertz region where they dominate over the thermal effects. So we'd like to have a coupler, and people have shown couplers that do that. And people have made these low loss E and Z terahertz waveguides which are very interesting. So maybe something like that in an ultimate thing. And so, talking about an experiment now, the Casimir force experiments have always, their goal is to measure attractive and repulsive forces, the famous, sphere and plate measurements out of UC Riverside. And these more recent, these little nanomechanical structures that have attractive and effective repulsive forces. It's not a real repulsive force. You actually need an ionic liquid, I believe, to generate a repulsive force. But people have made, measurements. This is a recent paper by Jeremy Monday, who, by the way, I just wanted to point out, congratulations to Micah, who's now in Monday's group up at UC Davis, so that he's going to be continuing doing some very exciting work up there. I forgot to mention that on the first slide. So what we'd like to do is they never measure a motive force. They always measure an attractive or a repulsive force. We want to measure a motive force. And so we're working with Jim Jimjeski, a professor out of UCLA, one of the pioneers of STM, and has made many brilliant, beautiful measurements of different devices and biological systems, et cetera. So this is, the next step for us, because the theory is fine and good. We're predicting a force. The proof is going to be in the experiment. Do we actually measure that force? And so we have a set of experimental configurations that we'd like to measure as a function of orientation, up and down, and temperature, and some baselines that should not generate forces. Look just at asymmetric cavities and dielectrics alone. Then just a chemical potential with a doped semiconductor, so not adding any current into the system, just looking at what happens with a chemical potential, and then the resonant tunneling diode with a current. And so that would be a good first effort. And then following that, integrate asymmetric cavity and the coupler, and potentially a non-reciprocal interface would also, on one of the faces, would also be very interesting. And this is Jim's low temperature combined. I think it's below 4 Kelvin. I'm probably, I forget the exact number, ultra high vacuum, 10 to the minus 9 in his lab. There's also this beautiful lateral force with a vertical cantilever where they measure the disturbance of an evanescent wave, and they can get to sub-femtonewton forces, but our predictions say that we don't need that. And, can we make these things? Well, yeah, people have made diodes on cantilevers. This is back in 98, where they made some cantilevers for strain sensing. People have done it for mass sensors, integrated in, and there's, we can electrically connect it, so we can add a current. So we think this type of experiment is readily doable with a, with a cantilever and an AFM type measurement. So that's what we want to go off and do next. And this is what an experimental program like that would look like. I think that it would take about a year for us to build up both the experiment and build the initial devices. This would be a baseline of symmetric cavities, moving on through those first 5 things that I mentioned on the other slide. And so kind of like 18 months to fully characterize the resonant tunneling diode forces. And then a second phase would be the enhanced devices with the coupler and the non-reciprocal interface. So that's really the next step, and where we'd really like to take this program now. And I just wanted to end, with this thought about the energy of a thought and the power of the questions. And I think Sunny really motivates me to think about this because of all the questions he's been asking throughout his life. And, you know, if you just think about how far just a human thought can take us, and, you know, and then I think about conservation of energy, right? Because, you know, our brain uses runs about, 0.18 calories each minute. And, you know, how many thoughts do we have per minute? And some of those thoughts change everything. You know, from Faraday, if a magnet could be isolated, it should move constantly in a circle around a current carrying wire. To Medvedev, I'm butchering that name, I believe his name. You know, he saw it in a dream, and he woke up and he wrote down the periodic table. Really amazing. And, you know, going back to Newton, you know, which has led, of course, to general relativity, et cetera, et cetera. You know, he had a thought, and it changes everything. So I appreciate everyone on this team for all your thoughts and all your aspirations to really make a change, because I really believe in the abundance that we can create. And that's really our goal. And I feel like I went kind of fast because Sunny hasn't told me to be quiet yet. So I apologize if I went through some of that kind of quickly.
Yeah, Charles, your timing was perfect. The 3-minute warning came as you were on that last chart, and I kind of could tell it was your last chart, so I didn't want to mess it up, so I forgot to let you finish that.
Oh, okay, all right, that's great, thank you.
And we'd press on. So you want to go ahead and stop sharing your desktop.
Okay.
Awesome. Thank you very much for your presentation, Charles. Before we take some of the questions from the panelists, I think we've already got 3 hands raised. I just wanted to, you know, you talked about Micah is going to be joining Jeremy Mundy at UC Davis. I was talking with Micah a little earlier. We also have a point of contact, Rafaela Manzella. She came to our lab here and installed the atomic force microscope. And she's going to be going to UC Davis working on Jeremy Mundy's team. And so she's made, you know, her entire career, she's worked on atomic force microscopes. And so it's a small world, right? When Micah said he was out at UC Davis, and I asked him, I said, you know, Rafaela Manzella? He's like, yeah, she's my office mate, right? So,
that's crazy.
It's a small world. And then I wanted to talk about, you said the power of a thought. Does, you know, one thought have more energy than another, right? Because of its impact. Maybe Newton really did get hit on the head by an apple. That's what enabled the thought to actually be manifested.
Right.
External energy.
It's like, come on.
Okay. All right. So with that, let me switch gears into some questions here. Look at the hands that they were raised. Phil is up first.
No, I think Kelvin was first.
Oh, sorry, Kelvin, you are first.
Okay, thanks. I just had a point of clarification. Slide 15. Very, very interesting talk, by the way. I really enjoyed your talk last time. If you can go to slide 15, you've got the time averaged intensity, which is intensity as a function of the square of the electric field. But then you've got the pressures twice the intensity. That's the peak. That would correspond to the maximum electric field. So have I misunderstood that? So in other words, I don't know if your force could be higher. I'm not sure if you calculated your peak as a function of your.
Yeah, I would say that
average.
That is correct. We've only considered one single mode, and you know, and the average value also of the field. You know, and the actual temporal sampling function, you know, we used what Ford used. And so we don't really know the actual, you know, we need to experimentally determine that. So that's another thing that we're not really, you know, we've made some assumptions on, and we're assuming that it's long enough that the transit time of the wave through the device is shorter than the time it's coupled to the vacuum. I don't know if Michael or Yuval, you had any other.
Okay, well, I guess maybe we'll just press on to the next question. So I think I think Phil and Richard were next in the queue, but I don't know who was next. So I'll whoever opens the microphone first.
Go ahead, Phil.
Phil, if you're talking, you're on mute, bud.
The answer is 42.
Yeah, right.
Okay, I apologize. I was just saying that was an absolutely wonderful talk. And I really mean that. I started out as a field theorist myself, and I just love this idea. I have just a very simple question for you. The Casimir force is scaling for flat plates like 1 over the separation to the 4th power, if I understand correctly.
Yeah.
I did the math myself as we were talking, and yeah, you're right. It's around a bar at 10 nanometers or so. So here's my question. It's a very simple one. I can take 2 plates and grind them flat to, much less than 10 nanometers, and I can metallize them or not metallize them, and I can bring them within 10 nanometers of each other. And I don't think I will see them being blown apart at 1 atmosphere. So here's I guess just a basic question for you. I mean, when we do this in optics, for example, we make resonators. Like Fabric Pro is a good example. You take 2 plates, you put them together, make a Fabric Pro. I mean, an atmosphere would be, 15 psi for those of us that are, in English units, and I know what 15 psi is on a glass plate. It's pretty big.
Yeah.
So could you just comment on that?
Yeah, I think, there's something that happens when we transition to the van der Waals force, which decays as a 6th power. And we no longer, your question has confused me as well, I must say, because, there's some boundary between where we start thinking of van der Waals forces, and then we start which are much smaller. And then we think about Casimir forces, where you have the retarded wave entering into the calculation. And I'm not sure I have seen anything where that boundary is well defined or characterized, nor have I seen anyone making Casimir force measurements below, I think, 90 nanometers or so, which I'm just going by my memory, so I could.
I think on that. I think you're right on the scale there, Charles. They haven't got much fun. It's not 2 plates in that case. It's a sphere and a plate. Typically.
It's a sphere and a plate, which also changes that a little. But Phil, your question is really a good one, and is something that has bothered me.
Well, and it's not blowing the plates apart; it's pulling them together, right?
Yeah, it's pulling them together, right? It's pulling them together. But we do transition to a van der Waals force, which has a different dependence than the Casimir force at some point. And I don't know if anyone has ever looked at that transition in detail or not.
Yeah. Okay. Yeah, thanks. I mean, I'll try to get in contact with you. Maybe we can bounce around some thoughts here.
Yeah, that'd be great. Thank you.
Phil, I'll connect you via email, right?
Thank you.
You guys have a good conversation. I think next up we have Richard.
Hi, hey, that really nice talk. I really enjoyed it as always. So I actually have a question, because we had also chatted on offline before about these Casimir experiments, and you knew that I was also trying to see if we can do something kind of very different, but the idea is doing these superconducting Casimir forces also with this STM kind of thing. And one of the things that we were running into lately was you have this scanning probe, which really only sees kind of 100 nanometer patches, and then we got to go find these devices on these chips, so it's kind of like trying to find a little patch of 1 centimeter in a big desert, and you've got to scope this small. Is this something that you guys are kind of going to run into, or have thought about that, kind of maybe a way to mitigate this thing, because it's something what we're still kind of figuring out?
Yeah, so we were going to use, a cantilever and AFM measurement so that we don't have to find it because it's going to be on our cantilever. But I wonder if Jim, I know he was a participant earlier. I don't know if he's still online, but and maybe you guys could connect also offline. But he is an expert on that kind of stuff.
Jim Jamzewski, you're available to talk if you want to unmute.
Yeah, we might just see his pretty picture. But I mean, I think that's an issue he's run into. And so why don't I connect you guys to talk about that?
Okay. Yeah, really, really interesting talk. Thanks, Charles.
Yeah, thank you.
Okay, we got 2 more questions.
There's Jim.
Hi, sorry. Is there a question?
Yeah. So the question is about, Richard's been doing some measurements with Casimir forces associated with superconductors and using an STM. And he was wondering about actually finding the right spot. And, I'm kind of paraphrasing his question. I think
It depends. Are you working at 4K or millikelvin or
1K thing?
The system we have, you can move the sample, like millimeters, so you can move around and look for things. And then, with the scan thing, you have a limited range because of the low temperature with the piezos. It depends on the microscope you've got,
Yeah. Okay.
But we can do that, no problem.
Yeah, so maybe you guys could connect offline and talk about that a little bit.
Happy to.
Yeah, this is what these events are for. It's great. Yeah.
It's fantastic. Let's see, I think we got Adam K next up on a question, and then one more question from Creon, if we can keep them short.
Try to keep it short. Thanks for this great talk. I think it was your first slide. You said that the 0-point field could also be explained and interpreted in terms of radiation back reaction. I'm wondering what the physical picture is in that case, because I think that the general story is, in empty space, you have the 0-point field fluctuating around, which may or may not be visualizable for different people. But for the radiation back reaction, do you have an explanation of what the supposed 0-point field might look like, what it might be caused by in empty space in that story?
Yeah, so in that story, there is no vacuum fluctuations. And the force is caused by the back action of, when something radiates, there's a force in the opposite direction. And, so Maloney, for example, in his textbook on the quantum vacuum, explains how, and I'm not a QED guy, so I'm really limited, but he talks about how it's the difference between normal ordering and not. And it's how you order the operators, and then you can interpret it in a different way. And then that guy from MIT, I'm sorry, I forget his name, also published a paper that showed how just using radiation reaction, you can come up with the Casimir force without invoking vacuum fluctuations at all. So his point was,
That's Kadar, right? Yeah.
Yeah. So his point was that, well, Casimir force, fine and good, that exists, but that is no proof of the vacuum. You cannot use that to say that the vacuum is a thing. And the same with the Lamb shift. You can derive the Lamb shift. And again, I'm not an expert on any of this really.
I see. Thanks. Yeah,
yeah. So, and I don't have a great physical picture for you.
Well, no, you answered my question, because it does basically say that, the physical effects can be explained from a different source. And so we don't need the vacuum fluctuations.
Don't need the vacuum, but you do need the vacuum for a consistent QED or quantum or relativistic quantum theory. So without the vacuum, those theories don't work.
Yeah.
So it's telling us something and we're not sure what. Either our theories need improvement, or or it's something real we can do something with. I don't.
The theories are incomplete. Got time for
Incomplete.
one?
Yeah, they're not wrong. Of course, they're so right.
It's incomplete.
They're beautifully right, but yeah, they're not. They're incomplete. And
Yeah,
maybe John will tell us how to complete it in his next talk.
That's good. That's a high bar, Charles. Appreciate it.
We got time for one more short question. We're kind of already into the break, but we had a good conversation going. Creon, if you could keep it short, bud. You're cleared hot.
Yeah, I want to get in touch with you offline, Charles, because I would like to have a 45-minute discussion about Maloney and Barut and electrodynamic paradoxes and all that sort of thing. But obviously, that's not my short question. My short question is a short question, might require a long answer, and we can just defer. I thought that van der Waals forces are often thought of as induced dipole-dipole kind of forces, and that's why they have a higher inverse power. And so they're really somewhat of a different animal. I mean, yeah. So that I don't know that that's such a mystery that the Casimir and van der Waals are different.
Well, but see, with fluctuation dissipation theorem, where you can completely model, that's what, a lot of the modern day predictions of the Casimir force uses. That's completely based on fluctuating dipoles in the materials and the fluctuation and the dissipation of those dipoles. And you can generate all the sort of Casimir forces that occur through that theory. So, I think kind of the picture people have is that, it is associated with the fluctuating dipoles. It's just that now you have to take into account the time it takes the field from the dipoles to propagate across the gap, whereas with the dipole to bipole interactions, you don't take into account the field. That's what I understand. And, I'm sure Richard could probably correct me if I'm wrong with that sort of thought.
You know about Jeff and Manco?
Yeah.
Okay, good.
Thank you.
Thank you, Charles. Fantastic talk. Really enjoyed it as always. And I'll connect you, Charles, with Creon, and I'll
thank you.
With Phil Lubin as well. I think at that point for the schedule we have a baked-in break that's supposed to go from about 8 minutes previous to now. So let's go ahead and take a short break and get back at it it's going to be 3:10. So I guess it's a 12-minute break. So 12-minute break, and we'll come back. John Bush will give us a wonderful talk. So thank you, everybody. Give us just 10, 11 minutes to get water or coffee.
Hey, Sonny.
Hey, John. Just bringing it back up, just to chit chat and so forth while we're waiting for everybody to get back. Just got a few minutes.
Should I make sure that my system works?
Oh, sure, if you want to. Yeah, feel free to share if you want. Check it out.
Probably a good idea. There are a couple of new and exciting mishaps.
Yeah. It's the beauty, technology is amazing, but it always has little tiny speed bumps here and there, right? It's funny, even during today's meeting, we've had a couple of internet instabilities, right?
Yeah.
We've had I've been listening to somebody talk, and then on slide 4, you'll notice that. Right.
Yeah, right. How's that look?
Looks great.
I can just hide the video panel, and
you don't have to move the video panel. We can't see your video panel.
Oh, you can't? Oh,
No,
you can't. Oh, okay. All right.
Correct. That's the beauty of Zoom, right? It
Okay,
it
good.
shows you, but that's not it blits a different piece of the memory to the viewers.
see. Okay, so we're good. We're good here.
Yeah. You can see everything just fine.
Wait, what did I just log out?
No, you're still here.
Well, why can't I see you? Oh, escape.
Yeah, sometimes Zoom gets wonky. You minimize it or something. You might go down to your taskbar and try and hover over the little blue square and see if you can't make whatever you want reappear.
Gotcha.
Whenever you share, it minimizes everything for you. So
Yeah.
we can see you just fine. So don't panic.
Yeah, maybe I should. Yeah.
If you unshare, it'll take you back to the normal interface.
Oh, if I do stop share, I see. Oh, yeah, okay.
It should make everything reappear the way it was. So.
I've been hesitating to, they've been asking me to, update Zoom, but Lord knows what mishaps await there, right?
Oh my gosh, right? Yeah, and sometimes if you update these iPhones these days, sometimes they get really wonky, and you can have Monday it works great, Tuesday it's dead, and Apple's like, what can I
They had some Keynote update at one stage, and I lost all of my videos. It's like, great. Now I just have to go digging around through 10 years of work to find them again.
Nuts. So Kelvin, you enjoyed Reid coming and talking to us after lunch? Yeah,
But it was brilliant. Yeah, really good. Love his energy.
Yeah, he's an authentic guy, right? You just really and you can see why he's the head of the astronaut office. I mean, he's a good leader. He's got a servant mentality. He's a team guy. He's a we, us, our kind of guy, as opposed to I, me, mine, right? He's really good, right? You just like being
very
around.
personable, very like you can have a beer with him.
Right, definitely.
I guess
Exactly.
With a lot of military people, you get that. So
As soon as this meeting is over, I'm going to watch I haven't seen the William Shatner interview after the flight. I saw his interview with Anderson Cooper before the flight, and that was great. I mean, it was clear that at 90 years old, he was 10 times smarter than Anderson Cooper.
I hope I look that good when I'm 90. I'm like, when I'm 90, I'm going to probably look like an avocado with eyeball. And it just, he's got like that whole, hi, I'm William Shatner. I just,
Yeah, John, what happened is when he came out of the capsule, they was all celebrating bottles of champagne. And it was just Jeff Bezos, him and a lady and the cameraman.
Mm-hmm.
And you could barely hear him. And none of the others were quiet. But eventually Jeff Bezos was quiet, and he also realized he needed to listen to what his man was, and he was crying, and he was expressing very poetically what he experienced, and it was beautiful, really nice.
Yeah, nice. It's almost like it took a while for Jeff to realize he needed to stop and pay attention, because William was trying to get his thoughts together. You could tell he was just overwhelmed with it. Right?
I felt kind of proud of him, because I know he's an actor, but you kind of, as a science fiction fan, you want to say, see, we told you Captain Kirk was real.
He's a proud Canadian, he was a very famous actor in Canada up at the Shakespeare. They have a, what's it called? What's the big Shakespeare festival in England?
It's England. It's like they probably have,
because there's a town right near my hometown, which is named after that place.
Where Shakespeare comes from.
Pardon me?
Stratford-upon-Avon, Shakespeare's town.
Stratford, yeah, that's right. Because there's a Stratford in Ontario where they have the Canadian Shakespeare Festival, and he was a big star there, Shatner.
Yeah, well, the guy who plays Jean-Luc Picard, what's his
Patrick
name?
Stewart, yeah.
Patrick Stewart, he's a Shakespearean actor for 20 years before he had his first TV role.
Really good. Yeah, the first time I saw Patrick Stewart was in a Shakespeare thing long before I saw him in the TV show. Yeah.
Yeah. Have you ever seen a Shakespeare play like live?
Oh yeah, yeah.
It's amazing.
Yeah, we have in our one of our human exploration architecture teams, one of the stress guys, Dr. John Zapay. He is a Shakespearean aficionado, and he would play in all different kinds of these plays. He's really good. He was a fantastic thespian, if you will. Anyway, good diversion there. It's 3:11. I'm going to be a good time hawk. We got our last two presentations for the day, last stretch. So we got two more to go. And first up, we have John Bush from MIT going to be talking to us about assessing the viability of vacuum-based propulsion with hydrodynamic quantum field theory. And John, I'll start your timer as soon as you get started and give you your 3-minute squeak.
Very good. Thank you. Okay, are we good?
We can see it. We can hear you.
Good. Excellent. Okay, well, it's great to follow Charles, who gave a very nice discussion about the quantum vacuum. And following his introductory remarks, I think while we all aspire to groundbreaking new ideas, I think there's also value in revisiting old ones. Indeed, my feeling is that there are many good ideas that come up again and again, mainly because they haven't been brought to fruition. And here, in some sense, we're advancing the ideas of Louis de Broglie from the 1920s, and as we do so, we're informed by a new hydrodynamic system and assisted by modern methods of applied math and numerical simulation. So really, this idea was recycled by Frank Wilczek in his book, The Likeness of Being, which is something I think after winning the Nobel Prize, one is invited to say what one really thinks, and this was his take on quantum mechanics. He says particles have an internal oscillation at the Compton frequency, which you get simply by equating the energy associated with relativity with that associated with quantum mechanics. So he says a particle has an internal frequency. Every particle at this Compton frequency, and this interacts with the quantum vacuum and gives rise to sort of wave effects that emerge in quantum mechanics. And this is precisely the physical picture that Louis de Broglie suggested almost a century earlier. And his idea was simply this: particles have an internal vibration at the Compton frequency. They excite waves which propel them along. So they basically move in resonance with the guiding or pilot wave. Okay, and so this physical picture is also evoked by this hydrodynamic system, which was discovered by Yves Couder and Emmanuel Faure in 2005. And I'll show you some examples of it, but it's basically a particle moving in resonance on the surface of a vibrating bath. And so it really is the first macroscopic realization of the pilot wave theory of de Broglie and its modern extension, which is stochastic electrodynamics, where they look for de Broglie's pilot wave in the electromagnetic quantum vacuum. And lo and behold, this system exhibits many features of quantum systems, which were thought to be exclusive to the microscopic realm. So the questions are, what are the key dynamical features of this system? And we've basically answered that now. What are the potential and limitations of this hydrodynamic system as a quantum analog? We're still exploring that. And can it guide us towards a rational theory for quantum dynamics? Of course, that's a work in progress. But also in the context of LSI, can it form the possibility of vacuum engineering, that is to say, extracting energy from the vacuum for interstellar propulsion? Okay, so the hydrodynamic system, you have a vibrating bath of fluid and a millimetric drop. It will bounce in place on the surface of the bath if it's the right size. And in a certain parameter regime, it will destabilize and start moving in resonance with its own wave field. Okay, and so the key feature of the system is the resonance condition. That is to say, the drop is bouncing at the frequency of the most stable wave mode of the bath. Okay, so that ensures that the wave mode, which is excited, is effectively monochromatic. And the other key feature, so basically this particle generates a wave field and then explores the potential associated with its self-generated wave, okay? And the other key features, the dynamics is hereditary, which is to say, so it instantaneously, of course, everything's local here, it's a hydrodynamic system. The particle is but the particle is moving in response to the slope of the local wave field, and calculating that slope requires that you integrate backwards in time to get the effects of all the waves generated along the particle's path, okay? And so basically in this system, the vibrating bath plays the role of the electromagnetic quantum vacuum in stochastic electrodynamics, or the pilot wave in de Broglie's mechanics. Okay, and so we have characterized this hydrodynamic system backwards and forwards, and we have now this stroboscopic model, which describes the motion in a frame. We call it stroboscopic because you basically imagine you grab a frame. In this video, we actually grab a frame, one frame per bounce, so you see the particle being basically sliding along the surface. So instead of having to take into account a number of discrete impacts along the surface, we can basically have an integral description of the wave field. So the particle inertia changes in response to this resistive drag and the propulsive wave force. So it's proportional to the gradient of the wave field, and the wave field is expressed here as being generated continuously along the path of the particle. So you then have, instead of having an infinite sum, you have this integral differential equation, which you can analyze. You can look for a steady solution, so steady bouncing, steady walking, and stability of orbits and so forth. So we really characterize the hydrodynamic system completely. And from this, in conjunction with the experiments, we've really seen what the three paradigms are for the emergence of quantum behavior in this macroscopic system. So first, all of them depend critically again on this resonance condition between the drop and the wave. And this is something that de Broglie stressed in his pilot wave solution. So the first is orbital pilot wave dynamics. Here you basically have quantized dynamical states generated by emerging as a result of the dynamic constraint imposed on the drop by its pilot wave. And then when the system becomes chaotic, it switches between unstable orbital states. And so the result is these sort of multimodal quantum-like statistics. Another mechanism is you see that there are these inline oscillations this is sort of a preferred state in certain parameter regimes, and these can give rise to very robust quantum-like statistical signatures, such as Friedel oscillations. And then there's also the possibility of, there's a regime in which the system becomes chaotic and you get sort of random walks, and so you get a diffusivity which scales with the average speed of the particle and its guiding wavelength, and that then looks something like Nelson's stochastic dynamics. But these are all features of the hydrodynamic system, which can happen in certain parameter regimes. And so there's now this growing laundry list of hydrodynamic quantum analogs, and we're forever tacking on new ones. The latest one was spin lattices, which was in Nature last month. We just super radiance we've just done, and we're sort of tiptoeing towards entanglement, and I'll mention that at the very end. But we know that this hydrodynamic system is limited. So in particular, all of the quantum features happen when you're closest to the when you're closest to the Faraday threshold. That is to say, the waves are very persistent on the surface. So the Faraday threshold is the vibrational acceleration at which you excite waves in the absence of the drop. We're always below that, but the quantum features emerge when we're very close to it, okay? And so that makes clear that viscous damping is our enemy. So these waves are being killed by viscosity. So let's think about moving into a parameter regime where these are where viscous damping is not terribly critical. And also we know that drop inertia can dominate the pilot wave force. And so there are certain states that you can't get in the lab that you would like to get if you're trying to get a model of quantum dynamics. So what we do then is generalize. So we now take our hydrodynamic system and we imagine an arbitrary parameter space. So we can then go beyond what's achievable in the lab. And this also allows the possibility of connecting to quantum pilot wave theory. So this is basically the non-dimensional trajectory equation, which we've just seen. So here we our wave function, we're basically imagining 2D. So we have a Bessel function generated by each impact. And since there are three terms, they're two-dimensionless groups. One is basically the memory, which prescribes the proximity to the threshold. And this is the term, basically the dimensionless is kappa naught. Here's the dimensionless inertia. And that in the lab is very limited. It sort of goes between 0.6 and 1.4. And but of course, in a generalized framework, you can set it to 10 to the minus 16 or 10 to the 42. And you might imagine in what parameter regime can we get most quantum-like behavior. So for example, taking this approach, we know that you have the possibility of a spin state, which is an object zipping around, confined by its own wave field. Those are just unstable in the lab, but you can find them in this generalized pilot wave framework. So we've actually characterized this completely in 2D. So here are the various regimes. You basically, these are, we indicate here in green, in the sort of turquoise and light blue, the response to inline perturbations. So you get overdamped. If you perturb it, it'll quickly go back to its free walking speed. In this region, you'll get underdamped response. So you get these inline oscillations, which can again leave an important signature. Then you get this sort of erratic regime happening in the very high memory, low inertia limit. Okay, and then we also have these spin states and and a few variations thereof. So these wobbling and quasi-periodic states. So this is all in 2D. So the same sort of geometry as in the hydrodynamic system, but with an arbitrary parameter regime as prescribed by these two parameters. Okay, and so what we're going to do here is basically extend this to 3D, and doing so will allow us to connect to the quantum pilot wave theories, in particular those of de Broglie, Bohm, and stochastic electrodynamics. And it's also sort of informed this approach has informed the development of an extension of de Broglie's mechanics, okay, which we call hydrodynamic quantum field theory, which was done first with Yuval Degan, and we're currently pursuing it. And so the idea is just to take this physical picture that de Broglie proposed and develop it. So he said, a particle is an oscillator at the Compton frequency, and it forces a wave which evolves according to the Klein-Gordon equation. So we did precisely that. And sure enough, we find that, so we basically have a guidance equation where we have the particle moving in response to gradients of the wave field. And when you do that, there's a critical coupling constant at which the particle will start moving, just like the hydrodynamic system. And when it does, it will move in such a way that P equals h bar k. And you also get these characteristic inline oscillations, which we've seen in the hydrodynamic system. And if we extend this, so this is 1D motion along the line. If you go to 2D, then you get a pilot wave, which looks quite different from the hydrodynamic case, but it looks like plane waves. And this is sort of what one wants if one is going to look at diffraction through slits. So we are continuing to look at this, and ultimately by developing the 3D generalized pilot wave framework, we'll see how we can extend this hydrodynamic quantum field theory. Okay, so the sort of big picture, we started with classical and quantum mechanics, and never the two shall meet. And then we have this pilot wave hydrodynamic system, and it's begun to intrude into quantum mechanics. And that sort of spawned the development of this generalized pilot wave framework, which has captured features of quantum systems that the hydrodynamic system can't. And then we've extended that. So sort of, it's just really going from the generalized framework to the hydrodynamic quantum field theory, simply changing coefficients on equations, really. But we see when we make that jump into the hydrodynamic quantum field theory, we see some familiar features emerging, in particular P equals h bar k. That's the momentum of the particle is related to its associated with the wave number of its guiding wave. Okay, and so the goal being here to extend things to 3D. So this is the sort of physical picture is that of a particle as a pulsatile source of waves. And in 2D, we have the bouncing drop. Here we have the thing pulsing, but if perturbed, it can become unstable and start moving. So just as in the hydrodynamic system. So we now have a pilot wave, which has a spherical Bessel function. instead of cylindrical Bessel function, but otherwise the formulation is the same. And again, we have two dimensionless groups, which are the dimensionless mass or inertia, and then we have basically the memory term, okay? And so as in the hydrodynamic system, there's a critical memory at which this pulsatile stationary object starts moving in response to its own wave field. And it turns out that the wave speed scales as the dimensionality, the square root of the dimensionality. So 3D walker goes at square root of 3/2 times faster than the 2D walker. And here's the pilot wave field for the 3D walker. And so we can do basically the mathematical machinery we've developed in considering the hydrodynamic system can be brought to bear on this generalized pilot wave dynamics in 3D. So we basically look at the response of the system to inline perturbations, and we find that there are regimes, distinct regimes in which you get overdamped oscillations, underdamped oscillations, and then erratic response. So basically you get exponential growth of disturbances, and so the thing starts moving along randomly. And so, for example, you'll get a trajectory in this. So this is in the limit of small drop inertia and high memory. You get this sort of structured random walk. And again, this is sort of evocative of Nelson's stochastic dynamics. But anyway, so we basically then characterize, if you just look at the response to inline perturbations, you get the following regime diagram. You basically have a region where you have overdamped response, so it quickly returns to a walker. And then there's underdamped response where you get these inline oscillations. Then you get this region in the high memory, low particle inertia, which is characterized by erratic motion. Okay, and so, but what about these spin states? So we think that the possibility of spin states in 3D is very interesting because there are a lot of quantum features that one needs spin for. Spin needs to have spin as a basic feature in order to demonstrate them. So are these 3D spin states stable? So these are possible when the trajectory equation, that is to say the force balances, the two components of the force balance are satisfied. And so we basically substitute this form of motion into the trajectory equation. And one can indeed find that spin states exist for a broad range of parameter space, but the fact that they exist does not mean that they're necessarily stable. So we haven't actually found them numerically. And so we're trying to prove that they don't exist in 3D, or perhaps they do, and we just haven't found them yet. This is, of course, I think I failed to say on my opening slide, this work is all done by Adam Kay, who's with us. And I, of course, don't deal with numerics, so he's fully responsible for all of this. Thank you, Adam. Okay, and so in terms of the 3D spin state, so if you initialize with a spin state, as you see here, it basically goes unstable and drifts off. You can see a rectilinear motion with sort of inline oscillations, so it doesn't like being in a spin state. But you get some sort of interesting features when you initialize with a spin state, as we see here in the green orbit. So it basically jumps to an outer, so it's basically by moving on a circle, it structures the field around it, and so that will then jump to a larger orbit and then to another one, but then it will eventually destabilize into a walker. So you do see the sort of structuring of the field in some order emerging, even if you don't have stable spin states. But Adam discovered these helical spin states, which we're quite excited about. So these happen again in the high memory, low inertia regime, where you can also find the sort of erratic motion, but it's intrinsically 3D, and this is kind of a key feature. And so as with one of these spin states, the spin vector is basically processing around the direction of motion. Okay, so the two aren't perfectly aligned. It's basically processing, and the pitch of the helix depends on these two control parameters in the system. Okay, and so we can now look at the stability. So we can first say, when do these, we'll get a solution of this form, provided these three equations are satisfied. And so indeed, one can find that solutions exist. And of course, we know they do because we found them numerically, or Adam found them numerically first. But you basically have a discrete, so you can basically get helical motion with these discrete radii, which are quantized on the guiding wavelength. And so these are the existence curves. And again, we're currently basically going to characterize all of these helical spin states. So characterize, for example, the pitch as a function of these two parameters. So it'll allow us to sort of tile that parameter regime plane. Okay, and so these will spontaneously emerge. You can be in this erratic regime, and then suddenly it'll lock onto a helical spin state. And you can also have they can also destabilize. And here again, we have something zipping around in a circle, and it's basically structuring the wave field around it. And then we'll leap off and maybe it looks here like it's moving along a spherical shell. So there are all sorts of possibilities. And here, initially moving along the inner helix, and then it structures the field in such a way that when it flies off, it then moves along an outer helix. So plenty of opportunities. So really, right now we're refining this regime diagram to see precisely what's happening here. So we should soon have the boundaries of these helical spin states, and also we'll be able to say how the helicity changes as a function of these two parameters. Okay, and also we'll be able to settle once and for all whether we can have stationary spin states, that is, they say something moving along a circle, or only these dynamic helical spin states. Okay, and so these are the various possibilities that we found in this 3D setting. And it sort of introduces, particularly these helical spin states introduce a lot of possibilities in terms of new quantum analogs in 3D. So in particular, we can use this, there's the nice connection between the Coriolis force and the Lorentz force. So the Coriolis force acts on a mass m in a uniform rotating frame, just as the Lorentz force acts on a charge q in a uniform magnetic field. This is an analogy that we've used in many other HQAs. So you can imagine doing a sort of analog Stern-Gerlach experiment. So you start off with one of these helical spin states moving in one direction, and it'll be deflected in one direction or the other according to its direction of its spin relative to the background rotation. Also, you expect Zeeman splitting of orbital motion in a rotating frame. And also, we can characterize orbital dynamics in 3D. So the response to Coulomb force. So Coulomb force is hard to do in 2D because you have a logarithmic potential. But in 3D, we can really see if we can get an analog hydrogen atom. So, and the response, so the other force to consider is the response to applied simple harmonic potential. And this is what you get in 2D with the hydrodynamic system. You get in these orbits, which are doubly quantized in basically mean radius, which is a proxy for energy, and angular momentum. So you get this emergence of doubly quantized orbital states, and then when the system becomes chaotic, it switches between them. So there's a probability of being in one state or the other. When we take this to 3D, we get here, we see a trefoil basically relaxing to a circular orbit. Problem is the orbit is confined to a plane. Similarly here, so we have this is a circular orbit in our 3D generalized pilot wave framework. And the sort of physical picture you have here is the thing is building up its background potential, which is its own wave field. So here we see how it evolves as the thing moves along a circle. It basically generates this axially symmetric potential. So then it's going to be trapped in the troughs of its own wave field. It's a sort of physical picture, and that's the basis of the quantization. And so better understanding this, seeing how this can work in 3D is one of the things on our list of things to do. And here we have, so for example, so this is a lemniscate, motion along an orbit, again in response to a central force. And the problem here was that things are basically staying within the plane. So if you perturb the orbit out of its plane, it will simply adjust to a new plane. And so you just get this sort of reorientation. It's a bit annoying because you've gone to 3D and you don't want only 2D effects. But the way to break this, the two ways to break it, one is you go into the regime where you have this sort of erratic motion. But this fact that we have these helical spin states will also break the symmetry. So I think it introduces a lot of interesting possibilities. So if you have something moving along a helical path, it's intrinsically 3D, so you'll break the symmetry. So that's really what we want to do as we move forward. So we're going to complete the characterization of the free particle in 3D. So so we'll complete the stability analysis of both the planar and the helical spin states. And this will submit to Procroy-Salk. And then we're also going to look at a characterization of the orbital dynamics in 3D. So use these helical spin states to break the symmetry and basically impose three-dimensionality on the problem. And then again, this basically will allow us to extend the results to 3D hydrodynamic quantum field theory. And so we can then look, because when you make that translation from the generalized wave framework to the HQFT, you're basically dealing with quantum numbers. So then are these spin states, can we get spin states in this hydrodynamic quantum field theory? And if so, do they correspond to the classical models of the electron? The classical model of the electron is a charge zipping around the Compton radius at the speed of light, okay? And also we can think about pair interactions. So in either the generalized framework or this hydrodynamic quantum field theory, we can look at how particles interact and look at their correlations. And we've been doing this in a different context and think in terms of violating Bell's inequality with the hydrodynamic quantum field theory. I wanted to add, so this is related to what we're doing, is we have managed to violate Bell's inequality with the hydrodynamic system. And some people may say, well, that's impossible, but it's evidently not impossible. So we've done it with numerical simulations, and we're also looking at doing it in the laboratory. And my view on Bell's inequality, people always think, oh, don't work on hidden variable theories. That's Bell's theorem proves that it's impossible. Well, Bell's theorem says, consider two particles moving freely, right? And so as far as I'm concerned, you should stop reading right there because particles interacting through a common wave field are not moving freely. And so that's what we aim to show in when we violate Bell's inequality with its hydrodynamic system, and therefore show that entanglement, at least local, that is to say, when the things are still communicating with each other, is possible in a hydrodynamic setting. Okay, and so I want to thank Adam, especially, who was definitely doing all of the heavy lifting here. He was supported by Matt Dury, who's an excellent applied mathematician working the group, and Yuval is our go-to guy on HQFT, and we're hopefully going to continue our work in that direction. And depending on Adam's trajectory, he will hopefully be able to smoothly pass the baton on to Nicholas Liu, who's a graduate student working on this class of problems. So thank you all for your attention, and especially thank Sunny and the LSI for their support. Welcome any questions.
Hey, thanks, John. You had like 4 seconds left, man. That was like perfect timing, man. You were just like, that was beautiful. That's a thing of beauty. If you would go ahead and stop sharing your screen here.
I have to figure out how to do that again. Oh, there we go. There it is.
Yeah. It's neat to see that Yuval's also helping you guys. I know you have some connections with him, but I know he's also involved with Charles Chase's team as well. So I think in a lot of these discussions, it is a small community, right? And even though we're on a global stage, if you will, there's a number of us that are in the kind of in this tent, if you will, or this club, thinking about things. Hey, Yuval, how's it going, bud? Before I get into questions from the panelists, I actually had an immediate request from Creon to put a question in there. So Creon, I've got you allowed to talk. If you could speak up, but just keep your question short, if you would. We got some more waiting in the queue.
Oh boy. Okay. Well, John, thanks. It's neat to see all that stuff. I guess I have like 5 questions, but since Sonny won't allow this, and neither should he, I'm going to just I'm going to ask the first one and the last one. The first one is, how much of this chaos and these qualitative complex dynamics? I presume the answer is, of course, you have your professionals. This stuff is really sensitive to how you integrate and what kind of integrators you use and what kind of step size you use. Is this like a generic phenomenon? How much does it change if you fool around with the time steps and the integration style?
So I would have to deflect, technical questions about the numerics to Adam. But much of what we see, in terms of the hydrodynamic system, we see it in the lab and we see it in our theoretical models. So in terms of modeling in the generalized framework, we certainly insist that things be resolved. That is to say, we crank down the resolution until they converge. Adam, do you have any specifics?
I would just say that when you look through the papers, most of the numerics are done within Adam's Bashforth linear multi-step method, which is what I'm using as well. But there are other papers that are using other methods, which also get consonant results. And Nicholas,
that's really all I need here. So in the interest of speed, I want to zoom forward to my last question, which kind of is the entanglement that you briefly alluded to. I mean, it's not going to be good enough to just get it when the two things are time like when they're in communication. To really get quantum mechanics, as you know, you have to get entanglement of space-like separated events, and that is very going to be difficult with something that's just a three-dimensional model, right? So of course you've had this question 100 times, but I want to know the answer to that, and I also want to know, and I don't mean to be a jerk here, but it's kind of the shorthand is who cares about any of this? And what I mean by that is I love de Broglie-Bohm and all these things. However, Sonny, why do you care about this? Why are you funding this? I'm not trying to get in your face. I'm just saying, what is the connection between this and going to the stars?
I'll answer I'll answer it last. John, you go ahead and take the
okay. So I'll talk about entanglement. So one doesn't actually need to go to 3D to get entanglement. So we were looking at bipartite tunneling. And so basically there's some probability you have two particles confined to a pair of chambers, and there's some probability of their tunneling, and you can find, and basically the measurement settings are the geometry of the, so I should point out that these things, although they're confined to a pair of cavities, they're communicating through an internal, basically a cavity which is between them, which carries the waves. So there are wave mediated forces acting between them, and this is what's responsible for this either synchronization or anti-synchronization. And by the measurement settings in this in our system basically correspond to the different geometries. So by choosing 4 different geometries, you can find situations in which you violate Bell. Okay, and so you're right. So that's what we call a static Bell test. And there's the sort of there's the issue of if you separate these chambers off to light, outside of the light cone, will those correlations persist? And so one can do that numerically, and we intend to do this. Basically, once they're established, you basically separate the two. So you just put a wall in the middle. And the point is the correlations can be established, because again, the whole notion of light cone for me is out the window when you have systems with memory, because they have a mutual memory of their time spent together. All of these entanglement experiments, the particles start together and then they're separated. But what is a light cone when you have a system with memory? I think this is sort of an important conceptual feature. And so there is a possibility that we can do things even when they're arbitrarily separated. So you can have correlations persisting despite the fact that they are no longer communicating.
Well, I really look forward to seeing some details on that, because that would be amazing. I love the idea that we could get out of Hilbert space and back to 3 space, but that's going to
I would like that idea too. And your other question was much more difficult for me to answer, and I'm not sure it's going to be any easier for Sonny to answer. But
yeah, it's a fantastic narrative, right? In my mind, this has to do with what do we know about physics today, right? In terms of what are the standard models from macroscopic to microscopic, right? It really consists of 2 things. You got quantum mechanics on the microscopic level is our standard model of how we understand things, works really well. And then you got general relativity on the other end of the scale for the macroscopic. But those two theories are not compatible, right? And we haven't figured out a way to kind of connect the dots between the two. So that certainly tells us there's a fundamental amount of work for us to do to go try and carve out what that mathematics is. I mean, what is dark energy? What is dark matter? I mean, if you kind of look at the percentages, in some ways, it's like, imagine telling everybody that really doesn't understand science that much, hey, 97% of what the universe is made of, we don't even know what it is, right? So in my mind, that there's just, it's a big unknown, right? And so in terms of trying to figure out alternate ways or different things, right, we're going to have to work on the frontiers of physics. As you know, if you think about it as a Venn diagram, you got two circles. You know, John had a bunch of nice pictures that kind of showed those Venn diagrams where you're trying to show how this new model incorporates this. Oh, and it might kind of reach outside over here into classical mechanics, if you will. And so in my mind, there's a lot of value in trying to understand what's the mathematics that pieces that together, because that's going to help us figure out how to do new things. I mean, think about just what quantum mechanics and general relativity enables us to do from that physics. Quantum mechanics gives us transistors, digital technologies, cell phones. General relativity gives us unbelievably accurate global positioning satellites, right? We have to correct the atomic clocks for general relativity and special relativity corrections. And so just those two standard models of physics touch our lives every single day because we use our phone to go navigate to go see a friend at a restaurant, right? And so I think it's very important as we try and tackle this huge challenge of going interstellar, right? We need to be looking at the frontiers of physics and try and figure out, are there new ways to do things? And so when you do that, what are potentially the most credible paths, right? And that's where we look at some of the things that have a lot of shelf life. A lot of people have looked at it. A lot of rigorous work has been done. And so when we go through our peer review process, those things bubble up as something that says, hey, I think we do want to put some resources onto that and see if we can't move the ball.
I hear you. It sounds like you're saying, you know, we have a lot of unknowns in physics, and if we can make a breakthrough in our fundamental understanding of what quantum mechanics actually is, like this QHD stuff, then it's got to have applications all over the map, including to the stuff that Limitless is doing. But what I suspect is that you, at least, Sonny, have some idea in your mind of a rather direct path from quantum hydrodynamics to, you know, interstellar drives. And, you know, someday I hope we will hear about this.
Well, so think about and we need to avoid making this too deep of a discussion because we're taking time away. We need to get to the next speaker. Think about what John Bush is thinking about. John Bush is trying to think about in his process of trying to understand this new perspective of the field. Is there some way to maybe extract energy from it or generate a force by pushing of it? Think about also what Charles Chase said, right? If we can figure out some mathematical models that provide those mechanisms, those obviously have a lot of appeal from a mission planning perspective. But
great,
I'm gonna have to put a push pin on it. I think do we have any other questions? There was one more. Charles, your turn, and if you could keep it short.
Yeah, great. Yeah, thanks, John. Love your talk as always, and your work. I just had a question about the helical spin states, and you know, I know you mentioned the classical view of the electron, but what about the spin 1/2 electron, where it's 720 degrees essentially for the phase and the solution to return to the same thing? Do you think you can create a helical spin state that takes 720 degrees somehow to get back to its starting point, or have you thought about that?
Yeah, I thought about that one stage, but it was a long time ago, and I remember speaking with Yves Couder about it, and he seemed to think that there is a possibility of having that symmetry, but I need to think a little bit about it. But to begin with, there are many possibilities. I'm just happy we were able to find one, which is basically the intrinsic attraction to this helical spin state, and we'll see, you know, what new degrees of freedom have to be added to get more.
Yeah.
But you're right. There are sort of funny features of the quantum spin states that we need to think about in terms of symmetries.
Yeah, I just wanted to comment on your chart about the different states that you exhibit in the 2D system, you know, the memory versus inertia. And at the high memory and low inertia state, you get the erratic behavior, right? So that's kind of like us, right? That's my only comment. We live in that little corner up there of the longer term memory. And I don't. Anyway, thank you again.
Awesome discussion. Thank you, John, for your presentation. It's fantastic. I think Creon had another comment he had typed into the comment section. Creon, for your awareness, John, I think hosted like a whole pilot wave conference in the summer. So I think Creon would love to be involved in the next one next year as well. So we have somebody who's very interested in it, just like we are. So let's go ahead and push on forward to our final talk of the day. Ray is going to take us home, right? Ray Sedwick from University of Maryland is our final presenter for today. Thank you, Ray, for just waiting. I've been the last guy on the docket many times, so thank you, sir. You're going to be taking us to the finish line. Ray's going to talk to us about his work with centrifugal confinement direct drive fusion propulsion. Ray, once you get started, I'll set the timer and I'll squeak it 3 minutes. You have the stage, sir.
All right, can you see the full screen?
Yes, we got you full screen.
Okay. All right, well, thanks everybody for hanging out for the day. Sonny in his wisdom has saved the last for last. So I'm Ray Sedwick, and I'm going to be talking about the work that we've been doing on the centrifugal confinement direct drive fusion propulsion. And I want to acknowledge my contributors to this, Jerry Carson, Ella Vicente, who are both students in the Aerospace Engineering Department, and Adil Hassam, a colleague in the Physics Department, who really his work is what a lot of this is based on. So just a quick outline. So I'm going to overview the technology, what exactly is that we're looking at. And some of this is going to be review from the midterm with a little bit of extra information. Then I want to talk about a design case that we decided to look at. So we took the exercise from the 2021 Planetary Defense Conference. And so we decided to sort of design a system around intercepting and deflecting an asteroid, just as a way of trying to use that as the basis to size a system. So I'll talk a little bit about that and then wrap things up. So review of the concept, I'll call it C2D2 for short. So the centrifugally confined fusion plasma we're burning DT and producing 3.5 MeV alphas. The energetic alphas in the system and the centrifugal confinement system are not actually confined because they're more energetic than what can be confined. We're really targeting at the fuel as the confinement. And so prompt alphas leave through the loss cones, through the ends of the mirror. The alphas that are outside of the loss cone, staying in the reactor, provide some heating of the plasma, although we recirculate quite a bit of power back into the plasma through the rotation. So the overall driving concept is that we want the reactor to be highly transparent. So operating in space, we don't need a vacuum chamber, and so we want to have a lot of open space to intercept as few of the neutrons that are produced in the DT reaction as possible. So downstream of the reactor, the prompt alpha loss is used to heat a bypass propellant flow, and so instead of just ejecting the alphas as the means of producing thrust, we mix that with the bypass propellant to generate a warm plasma, reducing the specific impulse and increasing the thrust. And so this gives us a tunable performance. And it also allows us to consider a broad range of propellant options. So we can choose propellants based on things that are convenient to either find or to store. Upstream, then, we use direct conversion of the upstream prompt alphas to generate electrical power. So the design to date has been baselining the standing wave direct energy conversion technology, which is an outgrowth of the more familiar traveling wave version. So the idea is we expand the B field to convert any remaining azimuthal motion to axial. The alphas are decelerated by a radio frequency oscillating field. We can then couple this to, for instance, a Cockcroft-Walton charge pump to create a high voltage at a relatively low current to feed back into the reactor to drive the rotating plasma. So this can also, of course, provide power to the rest of the spacecraft. And the idea with using the deck is that we don't need to have any large radiators for low temperature heat rejection. Although we are considering alternative deck concepts beyond the SW deck. Oops, and I forgot. Okay. All right. So next we'll talk a little bit about the centrifugal confinement. So the system is fundamentally a magnetic mirror. It has a very simple axial coil geometry. There's a radially applied electric field, and that generates through the E cross B drift a rapid azimuthal rotation. Typically, we would put the negative electrode at the center line and ground the perimeter. Simulations demonstrate or indicate that Lawson criterion can be met around Mach number 4 to 5. The centrifugal acceleration pulls the plasma away from the center line and towards the mid plane. Right, so shown here is the mid plane of the device. This is the center line. This is an example of the pressure profile across that mid plane. And so we have zero rotation at the axis and at the outer limit, and then there's a peak rotation where we also see the peak pressure and temperature in the system. And of course, this is where the majority of the actual fusion is occurring. So this move of the plasma towards the mid plane gives us good axial confinement by moving the plasma away from the ends of the mirror. It also introduces a rotational shear, and the rotational shear has actually been demonstrated both numerically and experimentally to stabilize a variety of sort of the natural instabilities that plague these types of systems. And also the rotational shear provides a mechanism to heat the plasma. And so we take the alphas, we generate electricity, we pump that back into the system. And so we actually have a mechanism for heating the plasma without having to consider things like neutral beam injection or microwave heating or something like that. Okay, so then downstream of the reactor, we have the mixing portion. And so here's where we mix the energetic alphas with some sort of bypass propellant. So what we had done previously is basically just to assume first that the alphas in the warm plasma are mirror trapped and co-located in the same volume. And so initially it was just considering under these conditions, then what sort of timescales do we have to observe thermalization versus momentum scattering of the alphas? Because if the alphas momentum scatter, that means they can scatter into the loss cone downstream. And so ideally, the momentum scattering happens more slowly than the transfer of energy between the alphas and the propellant. So if you look at that ratio, ideally we would want the ratio of the momentum to the energy scattering to be much less than 1. But of course, the best you can do really, if you're looking at the target propellants, just based on availability and storability. So for water example, this ratio is 1/3, and for carbon dioxide, it's 1/6. So neither of these numbers are obviously much less than 1, but they are less than 1. And so we really want to do some more detailed numerical analysis, which actually a student is working on momentarily, to determine what exactly the level of energy transfer we can successfully get is. So there are other possible avenues of inquiry we're looking at. So one is considering non-adiabatic mirror configurations. So we treat the mirror as sort of a classical mirror, But if you consider instead implementing high field gradients relative to the Larmor radius, then you can get nonlinear effects that are not captured in the usual theory. There's also the possibility of introducing a cusp field region. So this is sort of a way to generate intentional mixing of the pitch angles, possibly in a desirable way, but that would have to be modeled to determine. One possibility to consider is using ion cyclotron heating to artificially increase the perpendicular energy of the ions so that they remain captured longer until more of the natural parallel energy is transferred. So this is maybe not necessarily the most efficient way to do it, but we in principle do have more power available, and so we can consider doing something like that. And so we're also looking at the application of the centrifugal confinement in this region as well. And that's actually something that I'm going to talk about right now. So if you consider the this mixing region, so we have, first of all, inside the reactor, what exactly are we doing with the centrifugal confinement? So the prompt alphas, as I mentioned, are not actually centrifugally confined. So 50% are 50% of the alphas are less than a certain pitch angle, and they enter into the direct energy converter upstream, right? And so I say 50%. So it's basically the ones that are born traveling to the left and falling within the loss cone. The other 50% then go to the mixer on the right, so representing up here. So they are the ones that are born and leave the system to the right. And then above a certain pitch angle, then the rest of those alphas are mirror trapped. The deuterium and the tritium and the alphas that have thermalized are then confined centrifugally in the system. We can sort of look at the same thing inside the mixing region. So again, here, less than an ideally small pitch angle, the alphas are going to just directly leave the exhaust without having an opportunity to really transfer their energy to the propellant. But above a certain pitch angle, the alphas are going to be mirror trapped. And the mirror trapped alphas are actually going to go back and enter the reactor, which is not necessarily problematic because they're not very collisional, and so the mirror time scale is much shorter than the collisional time scale. So those alphas will actually cycle back and forth between the reactor and the mixer many times as they thermalize. But some of those will actually end up going back to the deck as well and being lost through the upstream mirror. And so those then that are outside of a certain pitch angle then are going to be mirror trapped. So by doing this, then it gives us the opportunity to increase the amount of time that the alphas are going to spend in the mixing region, transferring energy to the propellant. And the propellant itself, we can keep mirror trapped in this region. And only as the propellant becomes energetic enough to leave through the downstream exhaust end of the mirror, will it do so. And so that means that we can actually use the rotational rate of the centrifugal confinement in the mixing region to set the mass flow rate and the specific impulse. And so at a certain rotational rate, only the energetic particles that can leave the centrifugal confinement are going to be able to exhaust. And so they will carry with them an average energy that is above a certain value, and they will be limited by the density of propellant in the system. And if we reduce the rotational rate, then it's easier for the propellant in the energetic tail to leave. And so that will bring the specific impulse down. So this actually gives us a way of varying the specific impulse without having to actually try and change the mirror ratio, which is very desirable not to have to try and do. So then we also looked a little bit about the plume detachment, and we don't really have too much to say about this. Really, in this area, what was done is a pretty detailed review of the literature. And what it indicates is that there are a variety of theories on plume detachment, but there's no real consensus on the mechanism or the conditions when it happens. So the majority of the results you can find in literature are really from simulations, but of course, those results are only as good as the model that is being used. And so some models don't capture certain levels of physics. And so, if those types of physics are really, impactful for the detachment to occur, and then you're not really going to get results that are realistic in that case. So there have been a few experimental data sets that exist with sufficient detail to assess detachment. And so there are some indications that the detachment is actually related to the Kelvin number, or essentially the Alfvén-Mach number. And that implies that there's field distortion is a mechanism for detachment. And that is a mechanism that has been cited in literature. Collisionality would be another mechanism. And so that sort of also supports the idea of making a purely fusion alpha exhaust, which is highly collisionless, almost unable to detach. And so by this reasoning, the fact that we're mixing these alphas to a higher density but lower energy plasma should actually also aid in the detachment process. So we are currently adding some modeling results from the literature as well, with the caveat that the results of these various analyses are going to be highly model dependent. So then upstream, the standing wave direct energy converter. So the SW deck operates sort of the opposite to what a particle accelerator would. And so the idea is that ion bunches are periodically decelerated by comparatively low potentials at high frequency RF, as opposed to trying to do a single electrostatic deceleration. So in the picture here on the near right, you can see that as the ion approaches the first ring, and so I point out that these rings are connected to an external resonant circuit. And so alternating rings are connected together. So let's say in this picture, rings 1 and 3 would be connected and rings 2 and 4 would be connected. And the sort of turquoise line here is indicating what the instantaneous potential profile along the center line looks like. So as the ion is approaching this first electrode, is seeing this decelerating potential. As it passes through the electrode, the potential is now flat. As it passes from the first to the second electrode, it again sees a decelerating potential, and so on and so on. And so in doing this, the ions are continuously decelerated, and the image charges that are induced in the electrodes are transferring this kinetic energy into the amplitude of the resonance of the circuit. So in the far right here, the center line potential is shown at a sort of a higher ringing state. And you notice that the electrodes have to be bunched closer together as you go downstream, because the frequency remains constant across the entire system, but the energy is being pulled out of the ions. And so they move more and more slowly as they go to the right. And so this is the basic idea behind the SW deck design. So as I mentioned, we're sort of assuming that we have these pulses going through, but that's not how the centrifugal confinement system works. The alphas are coming out essentially in a continuous stream. And so in this simulation, it actually shows a continuous ion beam being injected from the left. And the first thing that it experiences is a set of modulator electrodes. And the modulator electrodes then can actually be seen to cause the ions to bunch together, forming these bunches. And so this modulation mechanism is actually a pretty effective way to create ion pulses. And so the fact that the alphas are coming out as a continuous stream is not necessarily problematic for the SW deck. The larger issue is electron removal. Because this simulation on the top assumes that only the ions are coming out, no electrons. But of course, the prompt alphas that are coming out of the reactor are going to be dragging electrons along with them, maintaining a quasi-neutral flow. And so the need to be able to separate out electrons from ions is a pretty standard direct energy conversion, problem that has to be addressed. And so, like other proposed solutions, one thing that we can do is to introduce a cusped magnetic field. And what this does is it leverages the large ratio of the ion to electron cyclotron radii. So the electrons are going to be tightly held on to the magnetic field lines. And so they're going to be pulled away from the main beam and can be collected at these electrodes. Whereas the alphas having a large Larmor radius, they are not as affected by these cusps and can pass through the system. So this is a mechanism for separating out the ions from the electrons. So at lower B fields, a cusp like this will actually introduce a rotational motion, an azimuthal rotational motion to the alphas. So one way that this can be counteracted is rather than just introducing a single cusp, having a reversed coil that introduces two cusps. And while this might not produce an exact cancellation, depending again on the level of the magnetic field, this can pull a significant portion of that azimuthal rotation back out of the system so that they are again moving primarily axially by the time they enter the SW deck. As the B field increases, this explanation is sort of less obvious physically. And so at the levels of magnetic field that we're operating at, we actually have to do a little bit more detailed analysis to see what the impact of these cusps on the system would really be. So another thing that we've been considering, and this is a pretty old idea, is that of direct electrostatic conversion. And so this is an alternative approach that we're considering because it might result in a lower mass system than the implementation of the SW deck. Now, this approach is normally considered only for low energy ions, and so it's certainly not the case we have. But the interesting thing is that in the C2D2 system, we actually need megavolt level potentials between the inner and the outer electrode to be able to drive the rotation of the plasma. And so this type of system, if we're directly converting electrostatically the energy of the alphas, so the alphas are coming out at 3.5 MeV, so since they are doubly charged, that means that in principle, we can directly generate an electrostatic potential of about 1.75 million volts. So the approach here is similar in that, again, the first thing you have to do is to be able to separate out the electrons from the ions. One thing to note is the center line of the system is here. The plasma comes out of the reactor in an annular region. And so as shown here, the idea would be to have some sort of permeable material like steel. You don't necessarily need a high permeability. What you need is something that has a very high level of saturation because of the high fields. And so the idea is that permeability draws the field lines in without having to put an additional magnet. Then the same argument, the electrons are tightly tied to the magnetic field lines and would be absorbed into this structure, which would then be grounded or would become the negative electrode. The alphas would pass through. And then one of the issues with using direct electrostatic conversion is that if you don't have monoenergetic ions, then you can't get multiple potentials on this. And so you either have to set this at some average energy And so that maybe you're losing half of the ions because they get deflected, or you set this at the lowest energy to capture as many ions as possible. But now you can have the situation where ions are coming in at a very high residual energy and impacting the electrode. And so you can certainly have tens of keV of energy difference in the alphas coming in around that 3.5 or below that 3.5 MeV energy level. So what we're proposing is, instead of using a solid electrode, is maybe using an ionic liquid to avoid sputtering of the electrode itself. Now, of course, there are all sorts of questions of feasibility this introduces, and we're very early stages in thinking about how something like this might be implemented. But it's something that we're maybe going to investigate a little bit. Okay, so I want to talk just quickly about this design case. And so the PDC exercise was an asteroid intercept and deflect mission. And basically, you can see sort of the geometry. At April 20th, 2021, the asteroid is detected and is predicted to impact in 6 months. So on October 20th, 2021. And so the idea of this concept is, upon detection, maybe the system is already, it has to already exist. And is maybe parked in a high Earth orbit or maybe around the moon, and so it would set off to intersect the asteroid in its orbit. And notionally, about 1 month it would take to reach the asteroid, and then it would spend the remaining 5 months trying to change the velocity of the asteroid. And it doesn't have to change it by very much. Basically, we just want it to reach the intersection point of the orbit, maybe 2 to 3 Earth radii, sooner than it would have otherwise. So in this particular scenario, the asteroid is estimated based on albedo to be about 120 meters in diameter, which means it's a 1.8 million ton asteroid. And so we can't move it too much over the course of 5 months, but we might be able to move it enough. So the implications then for the system study. So basically, we sort of look at the phase 2 first. We consider the system to be primarily a power plant, which is just basically the engine and the propellant. And you can go through an optimization and find that the overall system mass is going to be minimized basically when those two masses are equal to one another. And the masses of the two can be seen to scale proportional. So n is the number of Earth radii you want to move it, so that's linear. The mass of the asteroid itself, and then the square root of the specific mass, the alpha, divided by the time to the third power. And so the system favors low alphas and maximizing the deflection time. And then in the phase 1, you're basically looking at the race to get to the asteroid to start pushing it. And so you can do similar optimization on the phase 1. And then when you look at the entire system, right, these are the specifications that you get. And so the system ends up optimizing for a jet power of about 22 megawatts. You can see some masses that are in here. So the total system mass is 58 tons, 14 tons of propellant for the outbound rendezvous. And then sort of the interesting thing here to point out is that the two legs have different requirements in terms of specific impulse and thrust. So the first leg out optimizes to just over 9,000 seconds of ISP, whereas during the asteroid push, it's a little over 16,000. And so the first leg is a thrust of 45, and the second is 272. So the thing that this demonstrates, thank you. The thing that this demonstrates is that that you want a system that is sort of tunable in its operation. And so this is sort of the design point then that we came up with. So for this 22 megawatt jet power, so for a beta of 0.15, I won't read through all of these numbers, but various designs on the mirror ratios that we want to get. So we're basically looking at a field strength in the reactor of about 4.5 Tesla. And then that leads to a plasma volume in the reactor of about 18 cubic meters. And sort of the important things that come out of this are some estimates for the masses of these large mirrors. So the mirrors on either side of the reactor are 3.5 and 3.2 tons each. And these two mirrors are separated by about 3.4 meters. They would need some sort of supports to keep them separated. Those are estimated to be about 0.5 ton each. And then the neutron shielding of these mirrors is then estimated to be about 2 tons or about 1 ton of shielding per coil. In terms of thermal management, so it's estimated about 3 megawatts of neutron power is going to be deposited on each of the coils. Of course, that is the consequence of assuming that you're going to be using DT. So of course, this would be much easier if you could use an neutronic fuel that would give you the same triple product as you can get from DT. So then downstream, I mentioned using centrifugal confinement for the mixing. So just point out to the overall system. So this is what the central B field variation looks like. So downstream, we need a strong mirror to keep the alphas confined until they have time to actually transfer their energy to the propellant. So we'd have a 16 Tesla field. This would be another 3.8 ton magnet with a little less shielding. It's farther away from the reactor, so about 0.8 tons. Thermal management, not quite as bad, but still not great, 400 kilowatts of neutron heating. And I already mentioned sort of the impact. So you do get direct loss of alphas even at this mirror ratio. And so instead of getting the 22 megawatts of jet power that it was designed for, you would end up only getting a little over 20 megawatts. And so in an iterative design, you would put more margin into the system to account for the losses that are coming out of the end. Okay, so just to wrap up, centrifugal confinement. So it offers improved confinement in the simplified field geometry, natural ohmic and viscous heating, and suppression of instabilities. The downstream mixing with the bypass propellant gives us the ability to trade off thrust and specific impulse during operation. Allows us to use a broad range of plentiful storable propellants. And our focus is really on the energy coupling and the plume detachment in this region. Upstream for the direct energy conversion, so using DEC, potentially higher conversion efficiency, no need for large and massive radiators. And this not only powers the rotation of the plasma, but also other spacecraft functions. So we're baselining DT, but quote, ignoring the neutrons. So DT is obviously a much easier fuel to burn, but the thermal loading is of course significant. And that presents a real engineering challenge. So if you're paying attention, so the mass buildup, we made it up to about 13.5 tons, but that is missing the power conversion system and the thermal management. So we've got another 8.5 tons that we can allocate if we want to hit the alpha is equal to 1 kilogram per kilowatt that was assumed in the mission study. All right, so this is our team. And with that, I will take any questions.
Thank you, Ray. Appreciate it. Great presentation. It's always fun to hear about the progress you're making on this fusion concept. I love the acronym, the C2D2, man. That I think you win the acronym award for the day. That one's awesome. That's really good. That's really good. All right. So I think at this point we can open it up to questions. And for the panelists, let's see, Seth. Go ahead, bud.
Thanks, Sonny. Hi, Ray. Great talk. Thank you. Just a quick question. You're assuming DT fusion. How are you going to source the tritium? And because for propulsive purposes, the burn fraction is pretty low, so most of the tritium will go out the back.
Right. Yeah. So, I mean, the answer is don't know. We're certainly not trying to, breed it in situ. So, so operationally, part of the ConOps would be that you would have to, produce and preload the system with any tritium you're going to use. So, yeah, it has all the usual downsides, and it's certainly quite possible that after this brief foray into planting a flag and saying, darn it, DT is so easy to burn. That's where we're going to baseline, but there's just, for all the obvious reasons not to use it in space, that's probably at some point going to drive us back there. But we want to at least make a concerted effort to sort of see if we can engineer our way around some of the technical challenges. But yeah, that's sort of a supply chain issue that would be very important to have to deal with.
What else we got? What other kind of questions? I have one while we're waiting on the ionic liquid. What if you took an approach where you had some kind of a porous medium, right? I'm thinking of the the microspray thrusters. They've got those. It's basically a porous. The whole surface where they put those little tiny cones that you can't see, right? Yep. That's all like a porous medium. Maybe that could be a way for you to, trap it there where you wouldn't have to do anything else other than just rely on surface tension to kind of hold it there. And maybe you have some small amount of flow, right? That as stuff gets kind of burnt off, you just, to replace it at a certain point or something.
Yeah, it's a great idea. It's like I said, it's very early stage. I don't even know what the deposition distance through the ionic liquid is going to be. So, if the alphas make it, the whole way through, does that damage things? We're trying to keep from sputtering, but, is it basically going to splash the ionic liquid out? Can you recapture it in the way that you can with like a hollow cathode, so that you're not actually using up the material? You're going to be accumulating alphas. What do you do about the alphas that are getting accumulated? There's at least a dozen questions just off the top of my head that, we haven't even scratched the surface on.
What other kind of questions we got, either from the attendees or the panelists? You can tell it's getting late in the day now.
Poor Kelvin. He's really hanging in there.
Yeah, it is.
Trying to keep quiet because my kids are next door asleep. So.
Hey, I do have one question, and maybe we'll shift gears. But so you talked about the magnetic field strength of about 4.5 Tesla. I've talked about this before. Commonwealth Fusion, just a few weeks ago, whatever, their latest Reedco coil for their spark. It's not the final coil for the reactor, but it's like 98% there. 20 Tesla does that do anything for you, or is it immaterial? That's actually a secondary type of thing from the knobs you have on your equations.
Well, yeah. So in this sort of the design case we did, which I had to blow through kind of fast, but the farthest upstream coil was a 14 Tesla coil, and the farthest downstream exhaust coil was a 16 Tesla coil. So those fit right in there, with those levels that they're demonstrating.
So wish granted, it's already incorporated. Very
exactly,
awesome.
Exactly. Yes, that's the way I like it to happen.
Awesome. Okay. Cool. Anyone else?
Folks are tired.
This has been a long day, right? I mean, this is a lot of technical, gritty stuff, and we've all been talking and questioning and so forth. So I think let me shift gears and just make sure I kind of dote on you guys and show LSI's appreciation for you, right? This is our inaugural Interstellar Initiative grants solicitation, and you guys are our inaugural Interstellar Initiative grants class. So you guys will always be I2 grant fellows. We are very proud of everything that you and your teams have done. It's a lot of difficult, gritty work. It's been tedious at times and so forth. And, thank you all for your willingness to, communicate publicly in this other aspect that we're trying to do as part of our mission to inspire and educate. I mean, you do that by making sure you engage and talking to people of all different types of walks, if you will. So, very, very proud of everything you've done. This is fantastic. You guys should be proud of yourselves. So, there's a little kind of a golf clap, if you will, because Kelvin's kids are asleep. That's right.
Sonny, can I ask you a question? So thank you, by the way, for facilitating all of this. You've been, shown outstanding leadership. I'm sure everyone agrees, and not just you, but LSI in general for facilitating these grants. I think the only regret for me is not getting to meet people face to face. So do you think next year there could be an opportunity for some of us to get together?
Absolutely, no question. We definitely wanted this final briefing to be in person, and we were planning kind of a big to-do over at Space Center Houston. And so we still want to do a face-to-face where we pull everybody in and we're nose to nose. And I mean, there's going to be great conversations that's going to come just from that. And so, but because of the zombie apocalypse and the blip they had here recently, we kind of tapped the brakes a little bit, but it looks like it might be trending in a good direction here. So maybe we can do something, have you guys come into Houston, make sure you guys get an opportunity to have some of our fantastic either barbecue or Tex-Mex. And technically speaking, Houston's a world city, so any kind of cuisine you want, you'll find it here, right? So yes, we're definitely going to want to have you guys here at some point in time. Question is just when. We have a couple other things we're trying to connect to it to make sure it's good. It's a good trip for you guys to come and talk to us about it, but maybe we can also have some neat people in the room for you guys to dialogue with, right? The other thing about this is communicating with stakeholders and helping them see the value proposition of this thought process and the real gritty work that's going on. I mean, this is a hard domain, right? I worked at NASA for 19 years before I did this, and I routinely had to deal with trying to educate stakeholders to the value proposition of Hall thrusters, right? As edgy as that is, right? That Hall thrusters have a lot of value for some of the spaceflight architectures one would think about. So, it's hard to communicate with a lot of people about the bold vision that we have because of where we are today and where all of us on this phone call or Zoom call are thinking about this is where we want to be, right? And so it's, thank you guys for telling your story in a crawl, walk, run type of mentality, right? In terms of there's this endpoint that we're all kind of looking at, but always trying to remember to help the community that doesn't live, eat, sleep, and drink this stuff like we do, right? Help them kind of, all I care about is this, and help them maybe kind of start to broaden their point of view, right? This is a little bit of an educational process. So, and that requires passion, dedication, and determination. So you guys all have that in spades. So again, kudos to all you guys for doing that. And I had sent you guys a little quote in an email from a poem that one of the several poems that I'm very fond of. But there's a poem by John Masefield. There's a line in it that always kind of comes to my mind. I think it's actually, I might have actually been introduced to it from Star Trek, ironically. Maybe so, I don't know. But it goes like this: I must go down to the seas again, to the lonely sea and the sky. And all I ask is a tall ship and a star to steer her by. So it just always kind of makes me think of somebody sitting on the bridge of some futuristic thing, some point in the future, thinking about some bold things. So the Captain Victor Glover and Captain Reid Wiseman, they're on the ships of their ship. They're heading out into the cosmos doing some amazing things. So anyway, just wanted to say thank you guys for everything you've done. So with that, if you don't mind, I'd like to maybe pause and then ask you guys to maybe give me some feedback on, experience. Just take a couple minutes, right? Let me know what you think.
Well, Sonny, on behalf of HelicitySpace, Caltech, UMBC, and so on, we'd like to thank you very, very much for the support, the vote of confidence, and the follow through with all the work that we've been doing. We're very excited and humbled to be part of this community of really exciting work done by everyone around here. Some of them I've known from before, others I've just met, and extremely excited to to see that we're all working towards this dream of interstellar travel. So, you know, thank you so much for having us as part of this community.
Our pleasure. Thanks. Thanks, Seth.
Well said, Seth.
I'll go next. I'll just say, thank you so much for this opportunity. You actually kind of saved our lab. So we, doing fusion is really hard to do full time because the funding comes and goes and the interest from others comes and goes. And you constantly just kind of accept that the general public mocks the whole fusion is always 30 years in the future sort of thing. So it's really hard to kind of keep grinding through it. So basically this kind of helped to keep our staff employed until we could kind of get to the next contract on something that's really, really stable. It's led to a full-time job and a good collaborative relationship with the company. Samantro, he's got a full-time job with this company. We're still working with them. And that's all moving forward. Now we have a lab we're moving to, and we'll have a much more stable, I think, funding stream now in order to kind of keep going. So I just really appreciate this opportunity. It's unique. The reporting requirements were very reasonable, not too severe and not too encumbering. So I thought everything was really well balanced. So thank you.
Thank you, Jason. Appreciate it.
Yeah. Can I just follow up with something Jason just said? So one of the things I always wanted in this field was a steady stream of investment. So I've been involved in forming lots of companies, some of which completely failed, some of which have been marginally successful. But in particular, Interstellar, I was involved with the creation of Icarus Interstellar in the United States. I was one of the co-founders of that. I was one of the co-winners of 100-year Starship, the DARPA NASA competition. Unfortunately, we didn't, that went wrong. I won't go into the details. And I was also the co-creator of the Institute for Interstellar Studies in the UK. And one of the things I always wanted was investment. And I didn't have enough money in the pot to actually produce that investment myself. And it's the thing that's been missing from Interstellar. The talk with Reid earlier about, what makes space things happen, like the competition in the past, the conflict, or the disasters. In Interstellar, it's been, 2011, we had the government, NASA, the DARPA got involved, injected a little bit of money. 2016, Breakthrough Initiatives got involved. And that is a steady stream of funding, investments going into the community, to the universities, to the academics who are doing the research from Breakthrough, and now from 2019, LSI as well. So I think between Breakthrough and LSI, you have the potential to really move this field forward through your very smart funding schemes. What I would say is keep an eye on the little guy, because there's lots of very smart people out there who don't have access to that kind of funding at any level, because they're not affiliated with an institution, but I know many of them. And it would be good to see a smaller kind of grant available, like 5,000, 10,000 kind of student level grants, maybe, just for people who want to do some really cool studies. But congratulations to you and LSI, and also Breakthrough, who continue to also push this vision. So,
thank you, Kelvin. Good comments. Appreciate the thought process on maybe some smaller types of things as well. Now we actually have some discussions going on right now in that category.
Yeah. So I just wanted to, comment on your funding of the sort of research that's very difficult to get funding for, as you know, through the normal agencies. And as you're well experienced, especially with something where the physics isn't well known and very uncertain, there's not a lot of papers on to build upon, very difficult to get the traditional agencies to fund that kind of work. And so, your funding of the sort of things that you're funding is really needed in the community. It is so essential, and just really appreciate you championing that and seeing that that's a possibility. So thank you.
Thank you, Charles, for the comments. And back to what you were saying, Kelvin. We're going to continue to try and do Interstellar Initiative grants, keep going, right? So summer, as I said, the summer of 2022 is when we're looking to put the next solicitation out. Maybe we can make the next pool a little bit bigger too. We'll see.
Hey, Sunny, just wanted to comment also. Yeah, really thank you. Thanks from the team at TU Delft and for the Netherlands. for the support. I think for us, it's been really a very nice experience to not only just do the project and, you know, really be able to get the freedom to do this kind of, this kind of research, which is hard to get funding for in general. But also I think I had to, you know, my hat's off to you for kind of building this really nice community all online. You know, this has all been done over a pandemic, right? Online. And I think I feel like I've gotten to actually make connections with quite a few people, which is kind of amazing to do over internet, really, over Zoom. So and I think that's really been been tied by you, and you know, you've really been able to build that that kind of nice feeling amongst us all. So I think that's really really nice job on that. And in general, I had a really so it was a real pleasure, I think, doing this entire project. So yeah, thanks for that.
Oh, sure thing, Richard. Thank you for your comments, bud. You know, I was going to suggest one thing. This is part of the way we've been doing these public briefings, right? I was thinking if we had like another set of briefings that we were going to do it at some point in the future, and we're actually going to probably do something like that, but it'll be a closed event, right? We'll have you guys come in and do a face-to-face and have a VIP thing. We won't broadcast that, but and those might be a series of 10-minute speed dating type of things. But in terms of this, what we did today, right? We did 30 followed by 10. And I'm wondering if it would be more effective, and I'll tell you why I'm thinking this. It'd be more effective to do 20-minute presentations followed by 5-minute Q&A and kind of keep it tight on that cadence. Because I'm trying to get it because we went all day today, right? And I wonder if we had a session that was, right in the 4-hour range, right? Where we got a half a day of a long haul. We have one keynote, a 20-minute opening keynote, and then we just slog through with a reasonable break in the middle of that. And that's the whole thing. I think we might have maybe a better chance of capturing more people on the Zoom webinar that'll stay throughout the duration, right? Because when people look at their calendar and they see this all-day thing, they might be like, I don't have time for that, right? So whereas if you got something that's a piece or something like that, maybe. What do you guys think about that? 20 minutes talks versus 30, because we did 30 minutes today, right? 20 minutes versus 30.
So, Sonny, I think IT issues aside, I definitely wouldn't have wanted less time. I would have wanted more time today. I think maybe a compromise might be 2 sessions where you have an in-house session only, where it's more technical for us. So maybe we could have like 45 minutes talks or something. And then you could do a public event where it's like 25-minute talks, overview of what we've been doing. Because a lot of the stuff is very detailed and maybe it's like difficult to follow anyway. But I mean, I would like to have had longer, but that's not going to happen. And I struggled with the time I had, so.
Good input, good input. Yeah.
Sonny, I just want to say one thing. I want to thank you on behalf of myself and Adam, and you're an excellent MC. Above all, I should thank you for answering Creon's probing question. But I did want to mention
Creon's a thinker. He's a thinker.
Yeah. No, but in terms of the like the funding cycle, because so the next one's coming up next June, and so in terms of continuity of personnel, it's a little more tricky, right? So if they, for example, went, because they're 1-year grants, if they came up annually, it might be a little more convenient in terms of keeping people on them. I don't know if others feel that way, maybe, but in any case, that's something that.
That's something that I've thought about as well. Is that the continuity would be. Is very difficult, especially in a small enterprise. Cash flow is always tough, and there's not other things for people to do all the time. And then they have to go off and do something else. And then you can't regather the resources. So, the gap between the calls I don't know. I didn't think that was the best thing.
No, because I think just in terms of continuity, because especially if you have a postdoc, it'd be nice to, so you don't lose the knowledge.
Yeah, I was the great feedback, and I think even during even after the initial solicitation went out, we had some discussions. We got some similar comments from other folks about 2-year types of things. I think one of the things that we're rolling about in the sandbox right now is can we do 2-year graduate fellowships or something like that? Or maybe that might be a different program from I-squared grants, right? So we have I-squared grants could still be one thing, and then we'd stand up another thing, I-squared fellowships, graduate fellowships, where it could be a 2-year thing, right? To address this continuity, right? Where you get a situation where somebody goes, I like, that looks like a juicy meal. I'm gonna go chew on that for a while, right? So that's definitely something we're thinking about.
Sure.
Yeah, I think I guess I would also agree with this continuity thing, and maybe even this 2-year thing is an important one, because I think a lot of the projects we're also working on are really high risk, high gain ones, where it is really helpful for someone who is doing a lot of these projects to say, hey, I'm doing this high risk, high gain thing, and it's for a little bit longer. So I think it does make a big difference for sure, especially with the type of projects that we're pursuing.
Okay, cool.
Yeah.
Thank you, Richard. Any other questions, comments?
Yeah, I just want to say thanks also, Sunny, because the support from LSI has been really critical for my work, especially in being able to join the HQA community and a lot of other things. So it's been really great, and I really appreciate it.
Sure thing, Al. Yeah, no problem.
Sonny, do you expect that there will be something like what you were planning for yesterday happening in the future? Maybe your board or the members that have funded this will come together, or not?
Yes, yeah, we do want to have something like that where this one won't be a public briefing. This will be just a closed thing that we do. But we'll have all you guys come into town, and then we'll have you guys give maybe 10-minute talks as opposed to 20-minute talks. I know that's like, I can't do that. But we'll probably have to do it at that kind of a cadence, if you will. But provide opportunities to also network and meet some people that might be useful in other ways as well, right? So just like we have, this networking with the Brady Bunch display that we all have on our Zoom screen. Right. And so I get Richard in my screen, Richard, you're Alice, right? So sorry, but this is the technical networking, but maybe we can also provide some networking that would fit into other categories, right? So.
Actually, Sunny, I wanted to ask a technical financial question. So we have a couple of $1,000 left in the LSI coffer. Can we ask for a no-cost extension, which we can then use to fly down and spend on barbecue?
Yes, you can. Yes, you can.
Okay,
yes,
excellent. Done.
Yeah, I think we're gonna be covering travel for you guys. So. All right. Well, this is great, guys. Thank you, everybody. And so thank you, everybody on the webinar that's listening, and the 2 or 3 people that are still on YouTube that are sticking with us this entire time. This has been an awesome opportunity to talk about all this stuff. This is gritty stuff. It's been a long day. So thanks, everybody, for keeping the noodle up and running. I got lots of notes I've scribbled down in my notebook. If anything comes up, you guys want to chit chat with me about, feel free to send me a note. And I know we're all going to continue to dialogue. I think there's one thing I need to mention. I almost forgot. Roman Kishrasvili is going to be doing let me pull up the thing he had in the Q&A, put some kind of note about a special session there it is. He's a guest editor on a special edition of the open access journal Universe. with a focus on interstellar space concepts, science, missions, and so forth. So he wanted to invite everybody that was part of this Interstellar Initiative grants. If you have a paper you want to submit for publication, he would love to put it into the heap for this special edition. So Roman is the chair of the physics department up at the City University of New York. Fantastic human being. Kelvin, myself, and a couple others did an interstellar conference at City University of New York. It was 2017, right, Kelvin? We did that, the FISW 1.0, right? Roman is a fantastic guy. So it might be a good opportunity if you got a paper in the hopper, you've been thinking about where you might try and put it. Might be a good thing to connect with Roman. So anyway, just want to make sure I did that. And then I think I saw a couple comments come in on the chat. Rob Swinney said, thanks for everybody, your presentations today. It was really impressed with that. Rob Adams and Tom McGuire, everybody's kind of giving you guys the kudos, man. You guys did a fantastic job. So I was just the guy that was handing the microphone to different people. That's all I did today. So good job, guys. And I'll give you more golf clap. Right. And then after that, I'm gonna bring down the YouTube live and shut everything down. So thanks everybody.
Thanks so much, Sonny.
Take care, everyone.
Thanks.
Take care.
Everyone, thank you.
Have a good evening. Thank you.
Thank you so much.
Thanks, Sonny.
Thank you,
Thanks,
Sonny.
Ed.